packaging. This workshop is co-hosted by the Spokane River Regional Toxics Task Force, Northwest Green Chemistry, and Washington State Department of Ecology. I'm Lisa Daly-Wilson, and I'm going to be facilitating the workshop today. I want a little shout out for a couple people who aren't in the room but are with us virtually. Dr. Amelia Nessler with the Northwest Green Chemistry is in Portland, and she's going to be facilitating the WebEx breakout groups and chats. And Amelia was a huge help and heavy lifter on getting this workshop pulled together. I wish she could be here, but she's about to birth a baby and she can't fly. And then also to Maria Blackshear, Department of Ecology, who's administering the WebEx in Lacey. I'm assuming, Maria, you're on right now, right?
Yes, I'm here.
Okay, thanks. So a short side note about why we're all here in this room right now is I participate in the Spokane River Regional Toxics Task Force, which I'm going to refer to as Task Force from here on out. And we have a work group called the TSCA Work Group. And we were all just sitting around one day trying to brainstorm how we were going to overcome this conundrum that we have where the level of inadvertently produced PCBs and products appears to result in levels in the water column that are higher than the water quality standard. So with that, we were addressing some TSCA elements from a regulatory standpoint, but we also thought, well, why don't we just get everybody who has something to do with this in the room and start talking and telling each other our stories. Perhaps there's a way to get to solutions. So this is the first time we're trying this, and I think it's probably the first time we've pulled everybody with these types of interests together in the country around inadvertence. So I want to thank you for coming, especially those of you who came from the East Coast. I think we have someone from Hamburg, Germany, who's going to be presenting virtually, so there's interest everywhere. So with that, I want to say welcome and thank you all for making the trek here. A couple logistics, and I apologize if you walked around this building a number of times before you found your way in. But the restrooms are in the big hall, the big open hall over here. You go out to it, turn right, you'll find the restrooms. Coffee, Amelia wanted me to make sure you knew that coffee would be here all day, both days. That was very important. And also that lunch will be served both days. And we have some snacks this morning, and we won't have them tomorrow, so make sure you do have breakfast tomorrow morning. So with that, I want to introduce Mike Peterson to welcome you formally. Mike has worked for the Lands Council here in Spokane for nearly 30 years. He's a founding member of the Toxics Task Force, and he has a Master's of Science in Mechanical Engineering from Colorado State University, which is probably why he's so good at talking to engineers.
Thanks, Lisa.
Sure, and he has a mic for you.
Yeah, I'm mic'd up. You can all hear me, I guess. Well, welcome, everyone. This is indeed an interesting moment because we have people who are experts from the pigment and ink industry. We have the Toxics Task Force, and I'll talk about how that came about in a minute. We have regulatory agencies, and we have our beautiful river right outside the window here. And the photos that I have here, I'm not going to have any dialogue on the PowerPoint, but upper Spokane Falls at high water. And it rages at about 40,000 cubic feet per second during some springs, minimum of 20,000. And this is the historic homeland, native homeland of Spokane tribe of Indians, and they're a very important player in this whole PCB discussion because they are impacted by PCBs that accumulate in fish, and so they're downstream up here right now. The reservation is, but this was their historic lands around here, and we always keep that in mind, especially at the Lands Council. Before I start in on the Toxics Task Force, I have a confession to make. Years ago, 1990, I was on the three-person Earth Day Committee, Inland Northwest Earth Day Committee, and at that time, there was no paper recycling going on. And so a few of us hatched up this hoax, if you will, to put on a 1990 Earth Day recycling party. We invited everyone to show up at the Spokane Review with all their piles of paper, and we said, Spokane Review is going to start recycling paper, so please bring all your newsprint down. Well, a few days before Earth Day, the newspaper clarified that this was a hoax indeed, but they were looking into recycling. Well, and so we showed up on Earth Day, brought all this newspaper, and about 2 weeks later they announced, yes, we are going to start recycling paper. The irony being that recycled paper has inadvertently produced PCBs in it. And so Doug Croft is here of Empire Paper. We'll talk about that quite a bit, and we're great friends now, but that's my confession to start off our meeting. So the Toxics Task Force got going in about 2011. We started coming together, and we did it voluntarily, which is pretty neat, and it's a collaborative effort. And I think that's what makes it so special. I consider that Spokane is kind of the hotbed of research into PCBs, inadvertent PCBs, and finding unique ways to reduce those. There's been a lot of efforts. Inland Empire Paper has tried different ways to trap out the PCBs. The Lands Council has used spongy to do that. There's going to be some ultraviolet work to break down PCBs at Kaiser. And those are all members of the Toxics Task Force. In addition to all the dischargers, the City of Spokane, the county, Post Falls, Idaho, Liberty Lake. So we have a great group of people, Coeur d'Alene, that come together and work on problems. We have invited the pigment manufacturers because we've determined that, for me, it's that yellow stripe on the road. Every time I see that now, I can't help but think, oh man, that's wearing out and it's running off into the river eventually. So I think of PCBs in a very personal way. Oh, I should switch to a different picture. And I also get out on the river and enjoy things. This is the upper Spokane River, and that's about what it looks like right now. Pretty low water where you got to dodge rocks, and it's a beautiful stretch of river. And during the high runoff part of the season, the ponderosa pine love to just park themselves in the river, and I don't know if they have anything to do with PCBs, but they love the river as well. So the Toxics Task Force has a bunch of different subgroups. We heard about the TSCA subgroup. There's also the green chemistry subgroup. There's kind of a business and administration. There's an outreach subgroup and a technical subgroup. And all of these are volunteer efforts by people working together to solve individual problems and to get the public involved. You know, we all know what the words or what the letters PCB means, but most of the public, like, what? And so we need to continue to outreach to the public because it's not like anyone's intentionally polluting this river. And you can't call the discharge, I don't like calling the dischargers polluters. I insist on calling them dischargers because our clothing is adding to those PCBs. The dyes coming off, all the stuff we use, some of our laundry detergent. I found out it's in titanium dioxide, it looks like, and that's in things like sunscreen and toothpaste even. And so lots of places it's coming from. And what I appreciate about this group of people and the task force is that we're all working together to solve this. And we're doing it collaboratively, and we do it hopefully without having to sue each other and all that kind of stuff, and we come up with creative solutions. So I'm going to kind of wrap it up here, show a couple more pictures. Hangman Creek is one of the major tributaries, actually, of the Spokane River. And floating down Hangman Creek in a boat, that's the high bridge, the interstate that goes over it. Not so many PCBs coming out of Hangman Creek. A lot more come out up out of the Spokane River itself. But there are some, and you go, wow, where is that coming from? Is it aerial deposition? Is it, you know, the one or two little wastewater treatment plants? Is it some of the pesticides that get sprayed on the fields up there? The hunt for PCBs, the search for it it's harder than it was to find the entrance to this building this morning. And that was pretty tough. So I'm going to wrap it up with a couple of pictures. The Devil's Toenails, an amazing rapid downstream, and a very frightening one to go through. And I've gone in a couple ways, and I've done it swimming in, not intentionally, but unintentionally in my little inflatable kayak. So I want to leave it at that, and I want to really welcome, I guess I would call her the queen of PCBs, someone who's been involved with our task force, but is a professor at Rutgers University. And there's probably a whole bio that I could read on her, but I'll just tell you the story. She has helped us with our Budgie project that the Lands Council did to interpret the results. She has responded to our call in Spokane to come out and help us with PCBs and has some really interesting stuff. So I would like to welcome Lisa Rodenberg up here.
Thank you, Mike. And there is an official bio, but that was much better. And so, but Dr. Lisa Rodenberg she's a bachelor's degree in chemistry from Wittenberg University and a PhD in environmental engineering from Johns Hopkins. So she's been at Rutgers studying PCBs since 1998. And I will say she is serving as an expert witness on behalf of the city of Spokane in their lawsuit against Monsanto right now. She'll let you know what she can talk to you about and what she can't as a result of that. Lisa also has made the trip to Spokane a number of times to help us in our efforts with the Toxics Task Force. Most recently at our data synthesis workshop in May. So she's back, and we're glad to have her.
Can you hear me okay? So thank you for inviting me here today. I'm excited to be here. I'm really excited to be in a room with a lot of people from the pigment industry. I've been wanting to talk to you guys. Hope that we can have a really great dialogue today. I would like to tell you that I dyed my hair pink in your honor, but in fact that was just an act of rebellion because I turned 50 this summer. So they asked me to kind of do an overview, and they asked me to put a lot of stuff into this presentation, so I'm just going to launch into it. So first of all, what are PCBs? Maybe we all know, maybe we don't. So PCBs are two benzene rings stuck together, and then you put some chlorines on them. And depending on where the chlorines are on the rings, you can have 209 different congeners. And we number them from 1 to 209. So PCB1 has 1 chlorine, PCB209 has 10, and as the numbers increase, the number of chlorines increase on the molecule. And so I, as a person who does fingerprinting, I look at individual congeners, and those individual congeners can often tell me something about where the PCBs came from. And then, of course, a group of congeners that all have the same number of chlorines we call a homolog group. So PCBs in North America were manufactured by Monsanto and sold under the trade name Aircore. They were used in all kinds of electrical equipment, transformers, capacitors, but as you probably know, they were also used in carbonless copy paper. They were used as pesticide extenders. They were used in caulk, sometimes in fireproofing. They were used in all kinds of building materials, adhesives sometimes. So they have ended up kind of everywhere. And we know that PCBs have been quote-unquote banned under TSCA, but it also turns out, as I think we mostly know, and I think Dave Dokes is going to talk about this some more, that the Toxic Substances Control Act does have kind of a loophole that allows for the inadvertent production of PCBs. So it was known back in the 70s when TSCA was written, it was known that PCBs were produced inadvertently during a number of different chemical processes. And so they included this thing in TSCA that says that your product can have inadvertent PCBs in it as long as they are average less than 25 ppm and are no higher than 50 ppm. Where those two numbers came from, I honestly don't know. I'm not sure anyone really knows where those two numbers came from. And back in the 70s when TSCA was written, that was probably very realistic. It was probably close to the lowest you could measure with some of the techniques that were available at the time. But flash forward, 25 years, 30 years, and those numbers look really high, especially when we're talking about trying to meet a water quality standard in the river here of, 2.7 picograms per liter. So that's many, many orders, 2.7, no, just 7. Okay, 7 picograms per liter, still ridiculously low, many, many, many orders of magnitude lower than the parts per million there. So the other thing we should remember is that under the Stockholm Convention on Persistent Organic Pollutants, There are some controls on inadvertent PCBs as well. Unfortunately, the United States is not a signatory to that treaty, but most of the other countries around the world have signed the Stockholm Convention and have their own way of approaching this problem. So PCBs, as I said, were mostly produced in the form of aerochlores. There we go, aerochlores. And so I'm going to show a lot of graphs like this, where this is the PCB numbers across the x-axis, from PCBs with only 1 or 2 chlorines all the way up to PCB 209, which has 10. And then this is just the percent of total. So this is what I would think of as a fingerprint. And so this is the typical one. This is aerochlor 1254. And it has sort of this bell curve shape because they made the aerochlors by just adding chlorine to biphenyl. And they did it by weight. So the 5,4 means it was 54% chlorine by weight. So for PCBs, first of all, when you measure them, it's very difficult sometimes to measure each individual PCB congener. So sometimes they coalute, and you can only measure them as the sum of 1 or 2 or sometimes even more congeners. So PCBs with very few chlorines tend to be lighter in molecular weight, obviously. And because of that, they have a higher vapor pressure, so they're more likely to end up in the gas phase. They're also more likely to dissolve in the water, which allows them to sort of wash away. They're usually a little bit less bioaccumulative. And then the heavy ones over here with more chlorines, they're going to tend to stick to solids more. So they're going to stick to sediment, and generally that means they're not going to move as fast. The sediment doesn't wash out of the river as fast. So in places like the Hudson River, General Electric was using PCBs. They stopped using PCBs in 1977, but we still have this legacy of PCBs in the sediment, because that's where they stick, and then they don't tend to move too much. The main aerochlors are shown here, and I just want to point out aerochlor 1232 is much less than 1% of U.S. production, and that'll become important later because there are some inadvertent PCB sources that look a lot like aerochlor 1242. But again, the last 2 numbers are the chlorine percent by weight, and then 1016 is kind of an anomaly. They came up with 1016 when they started to realize that PCBs might be an issue. And what they did is they took 1242 and they tried to distill it to remove some of the really high molecular weight PCBs. And then they started they had to come up with a new number. So they called it 1016. When I do my fingerprinting, I can't tell the difference between those 2 aerochlors. And then there were some other aerochlors that are not shown here, 1270, 1272. Again, very, very small percentages of the total U.S. production. But they mostly consist of PCB 209, which can also be an inadvertent congener. So that's a little bit of a confusion. So how I got here, I was in New Jersey, here in the center of the state, in Rutgers, New Brunswick. And right when I started my postdoc at Rutgers, there was a TMDL for PCBs going on in the Delaware River. And then over here in the Hudson River and New York, New Jersey Harbor, they were doing a thing called CARP, the Contamination Assessment and Reduction Project. And so in both of these systems, they were starting to collect the first really high-quality data sets on PCBs where they were using this new method 1668, so they were getting really high-resolution measurements of PCBs. And I was sitting there in the middle and thinking, well, look, I have all this data. I should do something with it. And very, very quickly, we discovered that there was something very strange going on in the Delaware River that we finally were able to track back to the production of titanium dioxide. They were making titanium chloride, which involves chlorinating things, and then the titanium chloride gets converted into titanium dioxide, which is used as a pigment. And this was producing a lot of PCBs 206, 28, and 209. So these are the ones with a lot of chlorine. And they were discharged down here, and with the tidal action of the river, they kind of are all along the river. And because they're in the sediment, they're not going anywhere. So we started finding all this stuff, and that was one of my first introductions to the whole idea of inadvertent PCBs. And then in the New York, New Jersey Harbor, there's a wastewater treatment plant up here in Newark that was taking pigment waste, taking waste from a pigment manufacturer, and what was coming out of that plant was almost entirely PCB11. And so that was another big wake-up call that we were saying, wow, we had no idea that there were other sources of PCBs. Sorry. Trying not to rub against my sweater, but I can't help it. So that's how I got started looking at inadvertent PCB sources. So I've looked at data from all over the United States, You can just all kinds of places, groundwater, stormwater, surface water, sediments, atmospheric deposition, biofilms in the Spokane River. I've looked at lots and lots of data now from all over the United States. I think I've looked at more PCB data than the people who generate the PCB data. And so in most watersheds, the main source of PCBs is still aerophores. And that's important to remember. Some people use the term legacy when they talk about aerophores. I don't particularly like that term because I think it's a little confusing, what's legacy and what's not legacy. But aerophores generally in most places are still the main source of PCBs. But then you also have inadvertent PCBs. And then you have things that don't look like aerophores anymore, but they probably came from aerophores. And that can include reductive dechlorination, where the bacteria take off a few of the chlorines, but they still are leaving behind PCB molecules. And then biota can metabolize the PCBs and change their fingerprints a lot. So I'm just going to point out really quickly what dechlorination looks like. Dechlorination produces, again, these are all the different congeners, and this is the percent of total. And the red is PCB4 and 19. Those are two really characteristic congeners that say dechlorination is happening, and also 44 and 45 here in the green. So that's one way that I can tell just by looking at the congener patterns what's going on. And you can see this is 4 different places: Delaware River dischargers, New York, New Jersey harbor, the dischargers to the harbor, and the Portland Harbor Superfund site. So at least 4 different places where I've seen dechlorination happening. Okay, so the main inadvertent PCB sources that I see when I look at data from all over the country is the stuff from the organic pigments. This is primarily PCB11, but there are some others. And then, of course, in the Delaware River, I'm seeing a lot of this stuff, which is, at least in the Delaware, is probably from titanium dioxide. And I'm starting to see PCBs coming from chlorophenylsilanes, this is the building block of these polymers that are used to make silicone. So I've got a little picture here of silicone caulk. And this will have very low molecular weight PCBs in it, like 1 and 2 and 3. And then I'm also starting to see PCBs coming from silicone rubber. And apparently what happens is you cure the rubber using this peroxide molecule that has a couple chlorines on it, and it can decompose and form certain PCB congeners as well. And one of the main points to remember here is don't use silicone rubber tubing if you're going to be sampling water for PCBs. They do make silicone rubber tubing that is PCB-free, so you can use that, but be very careful because that can contaminate your samples. So this is sort of the top 4 inadvertent PCB sources that I have seen. That doesn't mean that there aren't a few others, but these are the ones that I tend to see when I look at data from all over the world. And just here in Spokane, we did a study of the lab blanks because, lab blanks are a big issue in the Spokane River because the concentrations in the river are fairly low, and so the blanks are a significant contributor to that. And what I found was that in the lab blanks, about 1/3 of the PCBs in the blanks themselves are from inadvertent sources. And that seems to be, a lot of that is silicone. I think they're probably using silicone caulk. They may be using silicone rubber tubing in the lab, and so that is contaminating some of the samples, some of the blanks. So that's one thing to always keep in mind. If you're finding inadvertent PCBs in your samples, you should at least check your blanks first and make sure it's not a blank contamination issue. And this is a paper that we wrote, Mike Hermanson and Amy Sumner and I wrote this paper, and it's in review right now. I hope it'll get accepted any day now. So this is the question. You see a bunch of PCBs in your sample. How do I know whether they're inadvertent PCBs or they're intentional PCBs? PCB209 in particular is kind of a tricky one. It could come from titanium dioxide. It can come from phthalocyan and green pigments. It can come from foundry wax, which is something they used to use back in the 1800s. Or it can come from some of the really high molecular weight aerophores. So how do you know where it's coming from? Same thing for some of these medium molecular weight PCBs. They can come from aerophores. They can come from those peroxide cured polymers I talked about, like silicone rubber tubing, or they can come from microbial dechlorination. And then the low molecular weight ones could be coming from dechlorination, could be coming from the silicone, or they could also come from aerophore 1232. So how do you tell? It's tricky. So you have to kind of first of all, I do a lot of fingerprinting where I use computer models to figure out what's going on. And I also always have to look at spatial and temporal variations. I think about the history of the site. You know, was somebody manufacturing silicone rubber at this site? Was somebody manufacturing pigments? That would be a big clue. And sometimes you have to use your professional judgment to figure out what the sources are. So, for example, in the Delaware River, we're pretty sure that the PCB-209 is coming from that titanium dioxide production because, again, we know the history of the site. And when you find it in hydroseed, it's probably coming from the green pigment, that sallow cyanin green. When you find it in very, very old sediment in the New York, New Jersey harbor, like pre-World War II, it's probably coming from foundry wax. When you find it in Los Alamos, I think it's coming from an Aerochlor because I know that Los Alamos was using Aerochlor 1262, which is a very strange Aerochlor that no one else used. And I think, well, maybe they were also using 1270, and maybe that's where the 209 is coming from. So again, you have to know something about the history of the site. PCBs 1, 2, and 3 might be coming from adhesives. I have a Superfund site where I know they were manufacturing adhesives. But in the Upper Hudson River, I know they're coming from dechlorination of Aerochlors. So again, and then here's, again, the medium molecular weight. These have 5 chlorines. They could be coming from Aerochlors, they could be coming from this peroxide cured silicone, or they could be coming from dechlorination. So you have to really think these things through, which is why I use this fingerprinting. It works best when you have a lot of data to work with, you know, a fairly large number of samples. And hopefully you have good high-quality data using method 1668 to measure the PCBs. That's just the EPA method. That's kind of the highest quality and, of course, the most expensive method. And if you do this kind of fingerprinting, it can usually tell you which Aerochlors are present, which inadvertent sources are present, and maybe it might be able to tell you whether dechlorination or metabolism of PCBs is occurring. But you have to keep in mind that sometimes PCBs travel together even though they come from a different source. So, for example, in the Delaware River, which I think is my next, that's the factor analysis equation. So, you know, I don't want to bore you with math, but it's just it's an equation for a line, right? Y equals mx plus b. If the problem is, okay, so x here is your data, all of your information, and then the program is trying to describe it as just a combination of some fingerprints, which would be what we would think of as the x terms in our regression, multiplied by their coefficients, which is like their weight in each sample. And so the only difference between this and a regular multiple linear regression is that you don't know what x is. So the program has to not only do the regression, but has to make some guesses about what x is until it finds a stable solution. But here's an example of that. So this is the dischargers to the Delaware River, and we found 7 factors, seven fingerprints that would explain what was going on. 3 of them look like Aerochlors. And so this is the fingerprint that was spit out by the program, and then we compared it to Aerochlor 1260, and you can see we got a really high R-squared. So that's clearly an Aerochlor. And then in the Delaware River, we also found 2 non-Aerochlor factors. One is that 206-28209, which is related to titanium dioxide, and the other was dominated by PCB-11. I always like to say the cheese stands alone. PCB-11 is always out there by itself. For whatever reason, it just doesn't track along with the other PCBs. In the Delaware River, we think that PCB-11 is a tracer for treated wastewater and combined sewer overflows and stormwater runoff because this factor gets more important at high flow when we know that there's a lot of CSOs overflowing into the river. And so this obviously is the PCB-11, but this part of it kind of looks like Aerochlor 1254, and that's why I think it's a mixture. They're traveling together through the sewers, but that doesn't mean that they're from the same primary source. Probably the PCB-11 is from pigments, and probably this rest of it is just the other schmutz that's in the sewer that's moving with the PCB-11. And then, as it turns out, in the Delaware River dischargers, we also had a bunch of dechlorination happening. There's PCB4 and PCB19, and here's 44 and 45. So, very complex system, but by doing the fingerprinting, you could figure out what was going on, and you could identify that these are coming from dechlorination rather than from pigments or anything else. And then the other thing you have to keep in mind whenever you're looking at PCBs is that biological systems, higher organisms, you know, everything from clams up to mammals, do metabolize PCBs, and they primarily use this thing called the cytochrome P450 system, which we abbreviate as SIP. And it likes to add oxygen, so here it's added a little oxygen, and it adds it at 2 unsubstituted places on the ring. So that's how the enzyme works, and then once it adds this oxygen, that can split open to just a hydroxyl group, an alcohol group. So some PCB conceners have those 2 open positions, like PCB 149 has them, but PCB 168, notice both of these have 6 chlorines, but 168 doesn't have 2 adjacent unsubstituted positions, which means this will get metabolized and this will not. And so that's one of the ways that you can look at the fingerprints and tell what's happened. So here's another example of some fingerprints. The one in blue was what was spit out by my computer program that is looking for covariant congener patterns, and the orange is what was in the original air core. So down here you see the 2 orange bars are of equal height. This is 147 and 153. 147 can be metabolized, 153 cannot. And so in the original air core, they're 50-50. One of the fingerprints that was spit up by the program has them at 50-50, and the R-squared comparing this to the air core is 0.84. So this is pretty clearly unweathered air core 1260. No problem. But then here's another fingerprint where the 153 is still big and high, but the 147 has fallen off almost to nothing, and that's an indicator that there's metabolism going on. So the things that cannot be metabolized are getting bioaccumulated, and the things that can be metabolized are going away. And so this is, first of all, one of the ways that you can tell that PCBs are being metabolized. Second of all, it's a way that you can tell, okay, even though this fingerprint doesn't look exactly like 1260 anymore, I mean, the R-squared's not great, but I can make an educated guess that this began life as 1260 and just got metabolized by the fish. And so I can track it back and say, yeah, there must be a source of 1260 in the watershed. And by the way, this metabolism looks the same everywhere. Here's the Portland Harbor Superfund site in blue, the Duwamish River in orange, fish from the Hanford site in gray. They all look about the same. So all of these systems, all of these organisms, from clams to worms to gooey duck to crabs, including fish and even osprey, all of these different organisms metabolize PCBs pretty much the same way. And all the species are similar. The light purple here is that metabolized 1260, where some congeners have been metabolized, and the dark purple is the unmetabolized version. And you can see, again, all different kinds of organisms, benthic organisms, fish, shellfish. They all do some kind of metabolism. Some species, like this brown rockfish, is metabolizing the PCBs like crazy, and the gooey duck, not so much, but everybody is doing some metabolism. And then there's, when you get down to what's left after all the metabolism has happened, there's not much left. You get these 4 groups of congeners that are kind of all that's left after all the metabolism has happened. And this is what you see in things like otter scat. So the organism, the otter, has metabolized almost all of the PCBs. They're either metabolized or they've been retained within the otter and gone nowhere. And this is what's coming out in their scat. Okay, so bioaccumulation. This is important because we want to ask, what is the potential for inadvertent PCBs to be bioaccumulated? So this is a fairly recent paper from Pitt et al. Where they looked at bioaccumulation in 4 different species. This is the log of the biota sediment accumulation factor. So it's how much of an enhancement in the PCB concentration is happening in the organism. Excuse me. Versus the log KOW. So that's a measure of how hydrophobic the chemicals are. And generally speaking, for PCBs, hydrophobicity increases as the number of fluorines increase. So you could roughly think of this as PCB1 up to PCB 209. And what you see for all of these organisms is that there's sort of a peak in their bioaccumulation potential around a log KOW of around 7. So up to a log KOW of 7, bioaccumulation increases as the size of the PCB increases. And then it starts to drop off. And what we think is happening is that, the PCBs, as they get more hydrophobic, they're more and more likely to want to stick in your fatty tissues. So if you eat them with your food, they will get absorbed into your body and stay in the fat and not go anywhere. But as you get up to these really what we call super hydrophobic PCBs that are really huge and have lots of chlorines, they're so hydrophobic that you can't get them off the food in the first place to get them into your body. So they just go right through you. And where are the inadvertents? Well, here's PCB 209. So it's kind of on the downward end, downward tail of the bioaccumulation curve. And PCB 11 is actually a little bit off scale here, be about here. It's got a log BSAF of around 1. A BSAF of around 1, so the log is about 0. Which means that, it does bioaccumulate a little bit, but it's not huge. So I think that this is good news, right? Because the two most common inadvertent PCBs are at those two ends of the bioaccumulation scale where they don't bioaccumulate as much as some of the others. And then they also asked me to say a few words about toxicity. I am not a toxicologist, but I will tell you what I know. So most of the study of the toxicity of PCBs, of course, is centered on the aerocolors. That's what people have studied because that's what was important. And so it's only relatively recently that people have started to really focus on these inadvertent PCBs and think about their toxicity. So at this point, we don't know as much about their toxicity as we do about some of the other PCBs. But even as far back as 1995, there was this paper that said that there are some neurochemical effects from PCB11. And then I found two very recent papers from this last year saying that PCB11 can affect liver development and act somehow in the AHR pathway. That's the aryl hydrocarbon, I forget what the R stands for, but it's the pathway that destroys PCBs in your body. It's related to the cytochrome P450 pathway that I was just talking about. So PCB11 does get involved in that pathway. It has interactions and can change the toxicity of other compounds and act as a toxic agent itself. And then there's been a lot of study of the neurotoxicity of PCBs in general. And so this paper by Pradeep was looking at all of the different PCB congeners and calculating neurotoxic equivalency factors. So you may be familiar with the idea that PCBs have dioxin-like toxicity, and so they have these things called toxic equivalency factors. Well, these are sort of like that, except they're for neurotoxicity. So this is kind of a new thing in the toxicity of PCBs, where they're starting to calculate these neurotoxic equivalency factors. And for PCB11 was in the top 20% among the PCBs that they measured as having a neurotoxic effect. So it's there. It's not the worst of all the PCBs, but it is in the top 20%. And then the other thing that's really important to remember is that, remember I talked about the cytochrome P450 and how it adds a hydroxyl group. Low molecular weight PCBs are the ones that are most easy for the organism to hydroxylate, because they have lots of open positions where there's no chlorine, so they can add the hydroxyl group. And the hydroxylated products of those PCBs tend to be more toxic than the parent. So that means that they're, let's say you are accidentally ingesting some PCB11, it's being hydroxylated in your body. You no longer can measure it, which is part of the reason why it has a low bioaccumulation factor, because you can't measure it anymore, it's gone. But it has turned into a hydroxylated product that is toxic. But on the other hand, the hydroxyl group makes the whole thing more polar, which makes it easier for you to eliminate it from your body. So the people who do this work in toxicity have started to call this episodic toxicity. So whereas other PCBs will just get in your body and stay in your body forever, these low molecular weight things like PCB11 get in your body, get hydroxylated, might cause some toxicity, but then they get eliminated. So that's why they're episodic. They come and they go. So in conclusion, most of the places we're looking, aerocolors are still the main source of PCBs. The only place I could say on a watershed level where something other than aerocolors is the main or one of the dominant sources is the Delaware River, where they have that big problem with the titanium dioxide. But having said that, inadvertent PCBs are showing up almost everywhere you look. Air, water, sediment, biota, clams, biofilm. Everywhere I look, I'm seeing at least some. I'm becoming more and more aware, though, of the problem of light contamination. and starting to be much more careful about how I blank correct all of my data before I look at it. And it's not just PCB11. There are a lot of other inadvertent congeners that are out there. Some of the most common unintentional or inadvertent PCBs are not bioaccumulated as effectively as the others, but we really don't know that much about the toxicity. And what we do know isn't great. So reason to be concerned and to look at this issue and tackle this issue. So there, I'm even under time.
You are under time. I don't know how you did all this slides.
I talk very fast. I'm from New Jersey. I talk really fast.
So we have 15 minutes for question and answer, and I encourage people to ask questions.
Somebody in the back there?
Yeah, you mentioned in your research that we see higher PCB levels when there's a storm event, if it's coming from the sewer system. Is that because it's being created in the sewer system, or it's being washed off somewhere into the sewer system?
I think that's being washed off. Yeah, I don't think that there's any generation of PCBs going on in the system.
Is this on now?
Yes.
Heather Trim, Zero Waste Washington. And two questions. One, I think I missed it if you talked about the Spokane River in specifics, which was in your title description.
Yes.
And so if you don't mind addressing that. And then secondly, so you talked a lot about the PCBs that are metabolized, meaning that they've moved into a different form and they've moved into a species. So that doesn't mean they've gone away. And I'm wondering if you could address sort of that, because, like, I work in the Duwamish a lot.
Sure.
And so, yeah, they may be metabolized, but they're still in the system. And then what about their half-lives and things like that?
So the reason I didn't say anything about the Spokane River is because I am an expert witness in that case. So I'm being very careful to specifically not say anything about the Spokane River. As far as the metabolized PCBs, so first of all, there's the PCBs that are left over after the metabolism is done. And those are in feces, for example, and those are going into the wastewater collection and treatment system. I've looked at a lot of wastewater data, and I've never seen any indication that feces and that metabolized powder is particularly important in wastewater, but that's probably because there's a lot of PCBs in wastewater. I think any metabolism just gets swamped by the fairly fresh sources of PCBs going into wastewater. And then the metabolized...
I meant in the river, like in the river.
In the river.
Yeah.
Yeah.
The species metabolizing in the river.
So the species metabolizing in the river, I mean, yes, they're definitely doing that. Again, the low molecular weight PCBs, as I understand it, are the ones that are more readily going to be hydroxylated and have toxic effects. But the hydroxylated products of all that metabolism, my understanding is they get excreted fairly readily, and then whether they're still hanging around in the environment doing a number on the environment, I don't know. I have argued with a guy named Isaac Wirgan, who's at NYU, that he needs to go measure hydroxylated PCBs in the Hudson River, because if you can't find them there, you can't find them anywhere. And I think he's going to do that. But right now, so measuring hydroxylated PCBs is really difficult. Measuring PCBs is very, very difficult. Measuring hydroxylated PCBs is even worse. So I think the short answer is we don't really know what's going on with those hydroxylated products.
And Heather, we have a presentation that Dave Dilks is going to give just in short order that will talk a little bit more specifically about the Spokane River as well. So we get a couple questions answered then. So I think Lauren Hines has.
I have the exact same question as Heather. I have it. And just was wondering, what are the metabolites and are they stable, and what happens to them? How far does the degradation go? And it sounds like that's not well known.
Yeah, and I'm not the expert on that. There's other people who would know better than me.
When you do this is Gary Jones. When you're doing the measurements in the water for the PCBs, the method that you're using is the EPA method.
Yeah.
And
per liter per congener. So for each congener, it might be around 0.2 picograms per liter if you're doing a really good job and being very careful. But that's just the raw detection, okay? So can you detect a PCB or not? The problem is, so for example, in the river right now, you're running somewhere around 200 to 300 picograms per liter of total PCBs, but in the blanks there's like 80 or 90. So of that 200 to 300, maybe 80 or 90 of it is blank contamination. So that's the tricky part. The detection is not a problem. We can detect these things down to incredibly low levels. The problem is the blank contamination, and how do you tease that out of whatever else you're doing? Most of the other places in the world, wastewater, fish, sediment, the blanks are not important because the PCB levels are so much higher. But it's in the water that it gets really tricky. Does that answer the question? Not really?
If you're measuring such a small amount, error rate of, say, 5% would be rather significant in terms of understanding what that is.
Yes.
What's the error
So
rate?
when I estimate uncertainty for my models, I'm usually somewhere between 5 and 20% for each individual congener. And to a large extent, sometimes those kind of cancel each other out so that by the time you're doing the sum of PCBs, the uncertainty in the sum of PCBs is probably on the low end, maybe somewhere between 1 and 5%, I would guess. But again, that's in that 200 to 300 picograms per liter. Then you have to talk about blank correction, and that's a whole other issue.
Other questions, comments? You published your message for blank correction.
So that paper I was just saying that's, I hope, going to get accepted any day now, is all about blank correction. It's all about the Spokane River and you try a bunch of different ways to do blank correction and try to see which one would work the best. Hopefully that'll get accepted any day now and be out.
One other question.
Yeah.
Sources of PCB11 besides pigment, what are the common sources?
As far as I know, the only source of PCB11 is the pigments. I have not seen it coming from anywhere else.
But when you see a peak of wastewater, like you said, in Saltwater, you have storm.
Right. So that's where there's a difference between the primary source, which is probably pigments, and sort of a secondary source, which could be this, how does that primary source actually get to the river? So the wastewater treatment stream could be a secondary source. I think that, as far as I know, the only primary source of PCB11 is the pigments. And then how it gets transported to the river, could be through the wastewater stream. And then when it does that, it's traveling with other PCBs, could be through stormwater, could be through atmospheric deposition, could be through a number of different pathways. Does that help?
I mean, if you're saying the primary source is pigment, I'm trying to imagine how you're getting pigment. We don't rank pigment right out of the air, and get picked up by this.
Well, so we did some leaching tests in my lab where we just used, yellow printed cardboard like cereal boxes and stuff, and the PCB11 did leach out of those pretty readily, so it would get into the wastewater stream. We didn't specifically do clothing, but I have every reason to think that it would leach out of printed clothing as well. So if we had SpongeBob, because he's yellow, so we had pajamas with SpongeBob on them and stuff, and that when you wash it, I think, the PCBs can get out and get into the waste stream. And then because PCB11 is fairly low in molecular weight, has a high vapor pressure, it will volatilize, and then it can potentially come back down with atmospheric deposition. So it cycles through the environment. All the PCBs do.
And I think it's Doug Croppers was in the room. I think he stepped up. There you are. Do you want to add to that?
I'm sorry, I just walked in.
Okay. Well, Sarah, do you want to ask your question again about how PCBs and pigments get into the waste stream? That was your question.
Well, I'm just curious, not the waste stream, but what she was saying is she detected a high, interesting to me, it's a high level PCB11 after result of storm. I'm wondering what's the source of PCB11 in the storm?
Yeah, I think that was specifically for the Delaware River, which has combined sewers, throughout Philadelphia and Camden. And so during storm events, the combined sewers start to overflow. Therefore, wastewater with no treatment is going directly into the river. And that's where we think, that's why we think, we have these, the PCB11 factor would get more important during these storm events because of this washing off of, street runoff as well as wastewater getting combined in the sewers and then pouring into the river with no treatment under high flow conditions. Does that make sense?
Yeah, I understand that situation. I just can't fathom why pigments are the primary source. How are pigments influencing that result?
So I'm going to ask that for the sake of the folks on the WebEx that they can't hear the mic, that mic, they can only hear this one, and they're also listening here.
Yeah.
Can you repeat the question?
So I think what we're talking about is how does PCB11 get from pigments into the water column? Really, that's the crux of it, right? How are they getting from pigments into the river? Is that the crux of your question?
Correct.
Yeah. And so again, this is where I want to talk with you guys about how the pigment is bonded to the substrate and stuff. Like I said, in my lab, we did do tests where we were able to see PCB11 leaching out of paper that has been printed with yellow ink. And I think that it's reasonable to surmise that it comes off of clothing when you wash your clothing. I know every Thursday I get a newspaper delivered to my driveway, whether I want it or not, full of sales circulars in printed ink, all different colors, and it rains, and these newspapers disintegrate and run off. And, so I think that there's some pathways, and I have a question back here.
My name is Robert Bott. I just wanted to make a point with regards to the comment about clothing.
Mm-hmm.
Mass coloration of clothing is not done with pigments.
Okay.
PCB 11 containing pigments or otherwise. And therefore, I think you should be careful about the representation that children's clothes are a source of PCB contamination in the children.
Okay. I'm not saying that they're the source to children, but we did, go to Target or whatever and buy children's clothing and pajamas and stuff and ground it up and measured in the lab, and we were able to find PCB11 in the printed clothing. And there's a difference between, dye clothing. A dye is something that goes all the way through to both sides of your clothing. That's dyes. As far as I know, dyes do not contain PCBs. But when you print something on the surface that doesn't run all the way through the garment, that, as I understood it, could be printed using the same four-color printing process as everything else.
We had another question, Ken.
Thanks, Lisa. Ken Zarker, Department of Ecology. Since this conference is focusing on solutions, one of my questions is, are there researchers out there that are looking at other colorants that are not sort of based off this molecule, and has there been any information about any concerns or impacts from those sources?
Yeah, I've been talking with my pigment expert, and he tells me, and I want to hear from you guys, that there really has not been much done in terms of dreaming up new colorants, new pigments. There's a lot of work done in how to apply them better, how to make them stick better, how to make them color fast. But the actual, for example, diarylic yellow molecule, as I understand it, there's not a lot of work being done into what would be good replacements for that. But I would love to hear from the pigment people whether there is more work going on in that area. I know that in general, there's a move all across industry to try to remove chlorine from solvents and other things that are used to manufacture the pigment, and that should help the problem, but might not eliminate it completely.
So we actually have a little time left if people want to respond to Lisa's question, or we also have a number of the pigment manufacturers and potential folks who are going to be presenting this afternoon. Might also be a chance to ask those questions. You guys folks have any response now regarding that? Regarding the question of new procedures with respect to some of the pigments that are being produced?
say wait until 10:30 in my presentation, because it'll cover a lot of the pathway.
Okay.
Information, at least relative to our facility.
All right. And do people on the WebEx want to hear the questions even if we're stating it into the second mic? Okay.
I'm very essential here.
Okay, great.
Lisa, you mentioned, and I haven't seen the data before, the PCB 209 was found in the green pigment for the hydroseed. Was that thoroughly tested, or was that more speculation, conjecture? I've never seen the test data.
That's based on the data from Spokane County, right? Where's the Spokane? City of Spokane, excuse me. So City of Spokane had measured hydroseed and found PCB 209 in it, and I'm surmising that it probably came from the green pigment.
Yeah, that's the part.
Yeah.
I've seen the test data on the hydroseed.
Yeah.
I've never seen the conclusion where the PCB was coming from.
Yeah, so you're right. And again, that's why I said probably on my slide.
Does the city wish to speak about that now? Okay. All right, so take a pass on that. Any final questions for Dr. Rodenberg? Okay, thank you. So before we move on, there's been a suggestion that we just introduce ourselves. There's a lot of folks in the room who don't know who each other is, and we have a little extra time because unfortunately one of our speakers just alerted us that would not be able to attend. So John Sroy from Upper Columbia United Tribes will not be here for the 9:55 slot. So with that, I thought we could just take a moment while we're loading Cheryl's PowerPoint. The master over here. But just to go around the room and state your name and the entity you're affiliated with. Don't give us a bio because we'll be here all day. So just your name and your entity, and that way, if you want to talk to specific people at the break, you actually know what they look like. So Ken, you want to start?
Yeah, we're going to take a pass. Yeah, good morning. I'm Ken Zarker with the Washington State Department of Ecology, and I work on our hazardous waste and toxics reduction program.
Mike Peterson with Lands Council and the Toxics Task Force.
Lisa Rodenberg with Rutgers.
Daniel Chizik with the Gonzaga University Law Clinic.
I'm Emily Griffiths from WSU.
Doug Kroppus, I'm the Environmental Manager for Inland Empire Paper Company here in Spokane, Washington.
Ben Carlton, also of Inland Empire Paper.
Steve Kaminich, BASF.
I'm Dave Dilks from Lemnotech and also technical consultant for the task force.
Lauren Hine, Northwest Green Chemistry.
Anna Montgomery, also Northwest Green Chemistry.
Sunday Delgado, and I'm with DES, Department of Enterprise Services.
Dave Darling, American Coatings Association.
Yeah, hi, George Fuchs with the National Association of Printing Ink Manufacturers.
David Wauer, Color Pigments Manufacturers Association.
Jeff Donovan with the City of Spokane.
Mark Vincent, representing the Color Pigments Manufacturers Association from Toronto in Canada.
Katie Olson with the City of Spokane.
Marlene Weiss, City of Spokane.
Jeremy Schmidt, Department of Ecology Toxics Cleanup Program.
Heather Church, Department of Ecology Solid Waste Management Program, focusing on recycling.
I am Brad Barnhart with NCASI.
Ken Lindrum with the Hayden Area Regional Sewer Board.
John Cummings, Gonzaga University Environmental Law Clinic.
I'm Kat Compton. I work for the EPA out of the Seattle office, Region 10, and I work for the Pollution Prevention Program.
Joel Brings, Vista Utilities.
Steve Jones with Hamilton Manufacturing.
Matt Smith with Hamilton Manufacturing.
Craig Manahan with Department of Ecology, Haz Waste.
Scott Etheridge, Bartech Compost Manufacturing.
Roger Crawford with Kaiser Aluminum.
David
Paul with the Kaiser Aluminum.
Gary Jones with the Specialty Graphic Imaging Association.
Cheryl Niemi with the Water Quality Program at Ecology.
Robert Mott, representing CPMA, and I came from just outside Charleston, South Carolina.
Scott Schofield with INX International.
John Calhoun with Sondra.
Laura Goff with Spokane County Water Resources Education Outreach.
Amy Sumner, Spokane County.
Tony Taylor, Spokane County.
Mike Hermanson, Spokane County.
Justin Meyer, Department of Ecology, Hazardous Waste and Toxics Reduction.
Nick Wegener, Washington State Department of Transportation Stormwater Monitoring Program.
Elsa Pond, Washington State Department of Transportation.
John Petrush, Consulting Engineer, Varela and Associates, here in town.
Heather Trim, Zero Waste, Washington.
Tanya Reynolds, Novalex.
Michael Oger, representing the Titanium Dioxide Stewardship Council.
And Mike Anderson of City Coeur d'Alene.
Bruce Williams, Spokane Regional Health District's Pollution Prevention Program.
Vicki Bartels, Spokane Regional Health District Pollution Prevention Program.
Carl Raines, Department of Ecology, Water Quality Program.
Adrian Borges, Department of Ecology, Water Quality Manager.
I'm Dan Redline with Idaho Department of Environmental Quality and the source of water for the Spokane River.
Brian Crosley, Water and Fish Program Manager for the Spokane Tribe.
Amanda Parrish with the Lands Council and ACE Board Member of the Toxics Task Force.
Jim Kilday with Hewlett Packard Incorporated in Corvallis, Oregon.
Good morning. I'm Rob Lindsay. I'm with the Water Programs of Spokane County.
Rob's also the treasurer of ACE for the Spokane River Regional Toxics Task Force. Okay, well, thank you all for coming. There's a number of people I want to talk to at lunch all of a sudden. I want to introduce our next speakers. We're going to hear both from Brooke Beeler and Cheryl Niemi from the Department of Ecology. I'm going to give you both their bios now. Brooke has been working on the Spokane River with ecology since 2005, and she's worked in the arenas of stormwater, stream flow, and supported the agency on complex regulatory issues. And she is now the regional director of the Eastern Region of the Department of Ecology. Cheryl will follow up with her presentation on, she's from the Ecology's Water Quality Program, and she's the lead staff for development of water quality standards for toxics, which is very pertinent in our watershed in Spokane at this moment. Okay, thanks.
Thanks, Lisa. How's my sound? Is that okay, everyone? Okay. Well, good morning. I'm glad that we did that round robin so we could hear from folks and where people are from. So what I have to tell you isn't just what you already know. Pretty high-level conversation that I'm going to kick off with you all related to how in Washington we can get after PCBs and regulating them in our environment. So our framework really lies with a few different regulations. We have chemical action planning, which allows us to work with the Department of Health, and that's where we can identify a toxic and what their pathways are for reaching people or the environment. And then that has a goal of reducing the risk for people, and we work with manufacturers to try and identify safer alternatives and potentially go down the path of eliminating those chemicals for use. We also have cleanup standards for soil and groundwater under our Model Toxics Control Act, and those are set in a way where we work to reduce the pathways for people. So depending on what the use of a particular property or space is for, then we can set certain cleanup levels for PCBs. Then we have the water quality standard, which is what Cheryl's really going to dive into for you all and get into some detail. We have them for fresh and salt water, and they're based on several different factors, but one of the major drivers is the fish that people eat. So in Washington, that's what's driving our work. That's what's getting us down to these tiny, tiny levels. So you might hear several different numbers thrown out over the course of today of what the standards are. But for PCBs, the current state water quality standard that must be met by our dischargers is 7 parts per quadrillion. Dr. Rodenberg showed us earlier today that the inadvertent component is parts per billion, up to 50. So we have a lot of work ahead of us. So I also, there's a lot of things happening outside of this room over the course of this year and past years, but our position is that that state standard is our goalpost. So no matter what that number is, 177, or we have a sovereign nation downstream, as you heard Brian Crossley is here today, their standard is 1.3. So we have a lot of work ahead of us. And so since we're driven by managing wastewater discharge at the end of the pipe, because it's the water quality standard that's really driving the work here, we recognize there's really a broader approach for tackling PCBs to meet those strict standards and ultimately get to our goals. And as Mike mentioned this morning, this community's been on the leading edge. So they've studied where the sources are. They've studied different new ways to get rid of them. And so hosting this meeting here today is just one more reason why the Spokane community is a really important driver in this work to reduce PCBs. And whatever's done here is really going to help us throughout the state of Washington. It's not just about Spokane. It's going to help the state's effort to save southern resident killer whales. It's going to help the federally led Columbia River Toxics Working Group. So we're just really glad to see such a variety of stakeholders engaged in today's conversation. It's imperative to our success that industry is here today. So I'm really, again, glad we went around the room so I could hear all of the different industrial leaders that are here. A little example, several years ago, there was this thing called phosphorus that we were trying to get rid of out of our wastewater discharge. And a tiny little community, Ruby Lake, just west or east of here, decided if we can reduce what's coming into our plant, then we don't have to eliminate that during that work. And so they banned phosphorus in their tiny community. And it started sort of trickling this way. And then the city of Spokane worked to eliminate or ban phosphorus detergent. And then a couple of counties, they went to the legislature, and a couple of counties had the ban. And all along the way, we had the manufacturers coming to these tiny towns saying, you can't do this. Phosphorus isn't bad. Don't worry about it. And before you know it, the state of Washington banned phosphorus in dish detergents, and 15 other states followed along. That's difficult for industry, and we get that. But that's the example of the willpower in this community to make change. And now it's been changed nationally, and there's no phosphorus dish detergent anywhere. So we are grateful that you are here with us today so that we can identify the solutions, as Ken mentioned, and get PCBs, those inadvertent PCBs, out of our waste stream. This bright yellow folder probably makes Doug incredibly nervous, and I didn't realize it until I brought it in this morning. But I want to get the inadvertent PCBs out of this folder because I love color. Color makes me happy. It drives Doug crazy, and I don't want to drive Doug crazy. I want us to have a cleaner flowing river, and I want us to be able to find a way to reduce PCBs in our waste streams. So again, in Washington, that's why the water quality standard is so important. It's because it's a small, tiny, tiny amount that we're trying to get to, and we're so grateful that you're here. So I'll let Cheryl give you the details of how it really works.
Got a cursor with the mouse. Yep. Okay, great. Okay. So, thank you, Ken and the rest of House Waste and the organizers for inviting me. Where are we doing this? Okay, there we go. Can everyone hear me? Okay, great. So thank you for inviting me. In my program that I work with in Department of Ecology, we implement Clean Water Act criteria, and we develop water quality standards that need to be Clean Water Act approved. So basically, we're focused in on implementing federal law and then also state laws that also require Clean Water Act processes, implementation, development. So what I want to talk with you about today is a little bit about kind of where the rubber hits the road in Spokane, because we talked about really low numbers, 7 parts per quadrillion, 170 parts per quadrillion, and then we talk about products, and we talk about all kinds of things. But what I want to draw the connection for you, I want to draw between the standards, the permits, what we're seeing coming into sewage treatment plants, and sources, so that you will know exactly why it's really important that we address PCBs pretty much anywhere we can get at them. Now, I know that this particular workshop seems to be focused on PCB 11. When we talk about water quality standards, we're talking about total PCBs, so it's all the congeners added up. So when I'm talking about PCBs, I'm not going to be focusing on PCB 11. It'll be the whole thing, but just so we have that perspective. And then we have people in the audience who can speak to exactly what congeners are found in wastewater treatment plant effluent and other types of effluent. Let's see. This page down is not going. Okay. So the organization of this presentation is, first I'll talk about our surface water quality standards. They're a little bit dry and they are a little bit complex, and Doug is laughing at me. And that's okay. So you'll get that groundwork. Then I want to talk about PCBs in the Spokane River, kind of what our situation is, and then I want to talk about sources of PCBs, and in particular PCBs that we see in products and why they're important. So what are our water quality standards? Water quality standards are state, tribal, and federal regulations. So they're in regulation, and they have a specific purpose, which is outlined in both the Clean Water Act and in EPA's federal regulations for water quality standards, and that is to protect public health and welfare, enhance the quality of the water, and serve the purposes of the Clean Water Act. So big statement, broad statement. Basically, water quality standards are, whoopsie baby, there we go. They are the basis of our implementation to clean water. They're the targets that we set. They're made of 3 main parts. The first is the designated uses. Those are things like harvest, aquatic life habitat, drinking water. We use waters for all of these different purposes, and so we need to protect them for those individual purposes. So what we do is we develop water quality criteria, and those are concentrations or levels of temperature, pH, PCBs, copper, different parameters that we can have in the water column that will be protective of all those different uses. And then we also have anti-degradation requirements in our water quality standards. They're really important because basically they play into the fact that we don't want to degrade water any further than it's degraded now. We want to protect it, right? So if you have to discharge a pollutant into the water column, we want to make sure that there is a reason for it. It has to be in the overriding public interest. It needs to be a necessity. And then the standards also have some other parts to them, other policies that affect how we implement the standards and how they're applied. And those policies include things like mixing zones, downstream waters protection. There's a whole host of other things. So if you go to our water quality standards, you will, it's a big, thick document about this big, you will see a lot of information. Now what we're interested in here today, because we're talking about PCBs, here at the Spokane River, is the designated use of harvest, fish consumption. How much fish can we eat and eat it without added risk of some type of health effect? Also, water quality criteria, we're focusing on the numeric water quality criteria. Some water quality criteria are narrative statements like no toxics in toxic amounts. That's a great statement, but you still have to have a target to go to, right? So we use the numeric target of 7 parts per quadrillion for our water quality standard for PCBs. That's based on human health protection, based on ingesting fish tissue. It's also based on water ingestion of drinking water from surface waters, but because of the bioaccumulation that Dr. Rodenberg discussed a little earlier, the part of the exposure you get from PCBs in water compared to what you get from fish is so small that it comes up to just about 0 in the equation. So really what we're focused on here is fish tissue and fish tissue ingestion and the number of 7 parts per quadrillion to protect that use. So really here's where the rubber hits the road with our water quality standards and Spokane River. Okay, water quality standards are the foundations of the state and tribal water quality-based pollution control programs. That means that they are translated into discharge permits. So the Clean Water Act sets up what's called the National Pollutant Discharge Elimination System, NPDES, and those are the permits that people or organizations, entities, businesses that discharge to the water column need to get in order to have a legal discharge. So within those permits, we have effluent limits. And we place those effluent limits in permits only when there's a reasonable potential to exceed the standard, for that discharge to cause the standard to be exceeded or to contribute to a standard being exceeded. So we're getting closer to the Spokane River here. So let's talk about freshwater PCB criteria. Water quality criteria for toxic pollutants are in most cases really small numbers. We express them in parts per billion. And so again, these are the numeric criteria. The specific criteria we have for PCBs for freshwater are human health-based, and they're also aquatic life-based. Now the human health-based criteria, that's that number, 7 parts per quadrillion. You can see how small it is when you look at it in parts per billion, and that's what you'll see if you look in our water quality standards. You'll see that really small number. We call it 7 because it's convenient, but we don't always do the crosswalk across the units when we're talking about different standards. So when we look at our aquatic life criteria, for acute effects, for lethality, to protect fish and other organisms from lethality, it's 2 parts per billion. To protect fish from chronic effects, reproduction, and growth effects in general, 0.014 parts per billion. So again, very different from the 0.000007 that we're focusing on for the human health protection here. And again, the basis, fish health, drives the calculation for the aquatic life criteria, but fish ingestion by humans drives the criteria for human health. Now, our downstream Spokane Tribe human health criteria is 1.3 parts per quadrillion. So we have a jump in the river where the standards change from 7 to 1.3. Let's see. So the area of the Spokane River that we are looking at when we're dealing with some of our water quality standards issues here goes from the Idaho border, which is right here, okay, all the way to 9 Mile Dam, which is right above Lake Spokane. That's about 38.5 miles that's the stretch of this river. In that river, we have 5 NPDES dischargers. 2 are industrial, 3 are municipal. Upstream of the Idaho border, we have 3 municipal dischargers. We have Lake Coeur d'Alene, which is the headwaters of the Spokane River. And so we're actually working pretty far up in this water system of the Spokane River when we're looking at our current water quality standards and permitting issues. Now, we also have 4 run-of-the-river dams here in Washington in this stretch of river. So I guess what I want to tell you is, and how you understand it, that it's fairly complex. We have a number of dischargers. We have upstream sources in Idaho. We have dams. And it's just an area that's got a lot going on. And in addition to this, it's not showing up very well in in this graphic, the river is very connected to the aquifer. So within the river, you have areas where the river is gaining, the aquifer is coming into the river, and you have areas where the river is losing, and so the river is going into the aquifer. So basically, you know, you got a lot of sloshing around out there, and that makes looking at this type of area very complex. So what do we see in the river? And again, I'm coming at this from a water quality standards and Clean Water Act and permitting aspect. You know, this is the permitting situation that we see from the water quality standards side. We see elevated PCB concentrations in the river. Elevated meaning they're above 7. Okay. We see elevated PCB concentrations in fish tissue, and the concentrations in the tissue are high enough on their own when not combined with other chemicals to drive our State Department of Health to issue fish advisories. So the fish advisories are a combined number of chemicals that work toward developing the fish advisory, but if you took away all those other chemicals and just had the PCBs alone, you would still have fish advisories based on the screening levels used by our Department of Health. So basically, the upshot is that in all of this long process of looking at the Spokane River, lots of monitoring, observing what's going on and comparing our goals and targets, which are our water quality standards, to what we see in the river, we've gone through the process of what's required under the Clean Water Act under Section 303D, and it's called the Water Quality Assessment, and we have listed this part of the river as impaired under the Clean Water Act. Now, when your water body is impaired, it's a big deal because it means a lot of different things. There's a rollout of actions that are required under the Clean Water Act when a river is impaired for a parameter. And so now we'll start talking about that because this is really where the river hits the road. Okay, rubber hits the road, not the river, sorry. So what does it mean? It means that there's no more assimilative capacity in the river for PCBs that are coming in discharges, right? No more dilution factor. That means that the standard of 7 parts per quadrillion needs to be met at the end of pipe. If we put in a permit limit, right, based on 7, that's what it would be. And there would be no dilution out there. Now, as we recently talked, we can't even really measure right at 7. We're talking total PCBs here. We can't even measure down there and quantify very well. So that is still our target, regardless of those technical difficulties. And I see some grimaces in the back. That is the world that we live in here. It really is. We are dealing with analytical methods that don't let us really get down to our target, yet that's what our target is, and that's what we're working toward. Luckily, we can go after things that are much higher concentrations and that we can analyze and feel confident about the levels in. So right now what ecology is considering, and we've entered rulemaking for this, so that's a very formal process. It's actually a modification of our water quality standards. We're considering the adoption of variances for 5 dischargers into the Spokane River who have given us applications, complete applications. So what a variance is, it's a new interim water quality standard. It's not permanent. It's only as long as it needs to be. And what it allows is for the standard to be based on the highest attainable condition in the effluent. So it's basically a standard that's applied right at the end of the pipe. It's not affecting the rest of the water body. It's really just at the end of the pipe. And so that new standard reflects the highest attainable condition of the discharge with the best technology that we can put in. And it also includes pollutant minimization plans as a requirement. So as long as you are at that highest attainable condition in effluent, and as long as you are making progress with pollutant minimization plans, a variance is a tool that can be used. Now, what that means is that, there isn't a time limit on variances. They could be 5 years, they could be 10 years, they could be 15, 20, they could be greater. The variances that our dischargers here have applied for range between around 13 and 20 years. But every 5 years, there's a big reevaluation. So the pollutant minimization plans are reevaluated, the highest attainable condition is reevaluated, and we see if it can be tightened down. It can't be made more lenient. It can only be tightened down at the 5-year reevaluation. And those would be paired with the new NPDES permit reissuances. So let's see. I'm going to push this button and hope I don't mess stuff up too much. Okay, all right, thanks. No, that's not going to help me. Okay, so PCBs are entering our river from many sources. And remember, from a water quality perspective, we're looking at total PCBs. Our criterion is actually based on the sum of aerochlors, isomers, homologs, or congeners. So we can look at a broad way of measuring PCBs to look for compliance with our standards. We have atmospheric deposition onto land and water. We have PCBs in stormwater, many sources, I think. We have PCB cleanup sites along the river, and also we have PCBs entering from industrial and municipal discharges. So PCBs are entering the river from all these sources, and some are what we would call legacy and some are current, and we're having an impaired river. So now I want to talk about PCBs in products because that's what you guys are here for, and I want to draw the connection back to our water quality standards and where that crosswalk is and why it's important. So sometimes PCBs are inadvertently produced during manufacturing. TSCA, Toxic Substances Control Act, regulates PCBs at 50 parts per million. So that's what it's been for a long time. It sounds like a pretty protective number. How do PCBs in products that comply with TSCA become Clean Water Act problems here in Washington State? So to get to that, to walk you through that crosswalk, I'm going to circle back to the PCB water quality standards. So again, here are the numbers we looked at before. And I'm putting things now in 3 separate columns. You'll notice parts per quadrillion, parts per billion, parts per million, because this is just how things, how we see things. The PCB criteria are set at very low concentrations, 7 parts per quadrillion and 2 and 0.014 parts per billion. Then we go down here and let's look at TSCA. So again, these starred levels are our regulatory levels and how we generally talk about them. We talk about them in different units of concentration. When we do product testing studies, we generally talk about things in PPBs, at least the product testing studies that I've looked at. So again, just what are these numbers? This TSCA regulatory level, once we start comparing it to 7, is huge. Okay, it's really huge, and that's the number that people need to comply with in products. But you can see how that number can get to be a problem if we're really focusing on 7. Now, here are some levels of PCBs in products. And I just want to go through this crosswalk a little bit. Again, here's 7, here's 50. I have motor oils and lubricants, road de-icers, unleaded gasoline. These are all things that you can imagine would fall out on the streets and go in stormwater. PVC pipe and 2 pipe repair materials. I don't know if they're going to be leaching out, but it's out there. Hydroseed mix down here at the bottom. That's commonly used. And so all of these things easily are meeting the TSCA levels, real easy meeting TSCA levels. And when we look at them as they are presented in product testing, they don't look very bad, right? They're pretty good. But when we start looking at them in these levels, when we at a water quality standards are looking at 7 parts per quadrillion total PCBs, not congener specific, we're looking at totals, we've got some really big numbers here. And you know, I don't know what the dilution is going to be because, of course, there's a lot of dilution in water, too. There's rain that falls on the ground. There's, you know, if you're looking at sewage treatment plant effluents, there's drinking water. There's infiltration into collection systems. But from a water quality standards perspective, when I see numbers like this, it's like these are important numbers. Now, I'm going to go down and show just some different things. These are things you see in your house. And so, again, 7, these are big numbers here. Laundry detergent, 1 dish soap, 3 toothpaste products, 5 clothing samples, 11 cosmetic and body care products. These are the ranges. 12 printed materials with newsprint. Big numbers, all of them in compliance with TSCA. And I have to tell you, you know, we're working with 2 federal laws here, Clean Water Act and Toxic Substances Control Act. It is not unusual at all to have things that don't really connect. We see it in the water quality world when we look at Safe Drinking Water Act. We see it when we look at Superfund. All over the map, we have different regulatory levels, and it causes issues all over the place with different projects that we're working, when we adopt standards, when we're looking at how standards should be developed. So right now, these are just numbers that we have. I don't know how they fit in with PCB 11 and how they fit in with pigments, but from a water quality perspective, these are big deals for us. We want to make sure that we can try to reach 7, and we want to reduce all sources. So these are sources that are in products. Seems like it's something we could focus on. Now, again, products matter. This is really the main message that I want to talk with you about, and I'm not going to go into it very deeply because I think this whole thing has led up to it. Products matter. Manufacturers are meeting TSCA requirements, but we need even lower levels of PCBs in products because we've got a standard of 7 that we're trying to meet here. Consumers need choices. Consumers don't even really know about this kind of information, but we need choices if we're going to work at all of this because this is more than just manufacturers. It's more than just dischargers. In fact, dischargers can remove a lot of PCBs, but guess where they go? They go into solids, right? So they go into sludge. That's not a good path for them either because a lot of them aren't destroyed at all. They just transport. What we need to do is we need to get at them upstream. And so I look upon this really as a shared responsibility. We all have to work together. That's manufacturers, consumers. I'm a consumer. Obviously, all those products I'm probably using, right? It's something we all need to do together. And also, in this process, sometimes, although we've got such a great process in Spokane, statewide, there's finger pointing going on, and this isn't really the place for finger pointing. This is the place where everybody really needs to get together and work. So that's kind of my plea to you. We have a goal of 7, and we have a lot of product information that says we got products going in at levels much higher than 7. We can use some help. And that is it. Thank you. If anybody has questions, I'd be happy to address them. Or Lisa, if you want to wait till later.
Thanks, Cheryl.
Can we go sit down?
You can.
Okay.
We're going to actually hear, we're going to do Q&A at the end of this section because we have a couple other presentations that are very relevant. So as I mentioned before, I'm sad to announce that John Sorois is not going to be presenting, so it was okay that Brooke and Cheryl went over a little bit. And then we're going to now hear from Dave Dilks. And I had asked Dave, you know, we weren't really sure what Dave was going to talk about. He can talk about a lot of things that are very applicable. But when we started putting this together, I said, you know, Dave, I would really like to hear how all this fits together. PCBs we're measuring in our water column, PCBs we're measuring in our fish in the Spokane River, PCBs in products, and TSCA exclusions. And how do these all fit together? And as he always does, he's put together a PowerPoint that I think really tells the story. So, I need to give your bio. Sorry. So Dave is works as the vice president at Limnotech in Ann Arbor, Michigan, and he directs water quality studies there.
And he's worked on water quality issues in the Spokane for 25 years, the last 6 of which he's been serving as the technical advisor to the Toxics Task Force. So thanks, Dave.
Thanks, Lisa. Can you hear me in the back? Little bit of selective redundancy with what Cheryl just presented, but we'll also drill a little deeper in terms of looking at inadvertent PCBs. So PCBs in our watershed products and toxic exclusions, putting it all together. 2 key questions I'm going to address are inadvertently produced PCB concentrations exceeding allowable levels in consumer products. Cheryl talked about total PCBs are in compliance. We're going to drill down a little bit deeper at inadvertently produced PCBs. And our inadvertently produced PCB concentrations at problematic levels in the Spokane River. So those are the 2 big picture questions I'm going to cover. Going to do that, drill down with 4 more detailed questions. How much inadvertently produced PCB is allowed in products? That's a selective redundancy. You've heard that, but it's important. We'll go over it again. How much and what form of inadvertently produced PCBs actually occurs in products? I'll talk about product testing, some new results. Looking at congener-specific details, not just total PCBs. How does that compare to what's allowed in the river? And then how much inadvertently produced PCBs are we seeing in the river in our sampling? So that's the outline of the next 15 minutes or so. So this you've seen, I'll cover this pretty quickly, selective redundancy. Under TSCA, you're allowed an average inadvertently produced PCB concentration of 25 parts per million and no higher than 50. In terms of compliance, the mono and dichlorinated biphenyls are allowed even higher. You divide the monochlorinated by 10 to determine compliance, the dichloros by 5 to determine compliance. So if we're looking at PCB11, a dichlorobiphenyl, if your product only had PCB11, you take the concentration divided by 5, you're actually allowed an average of 125 parts per million and a maximum of no more than 250. So those are the TSCA numbers. Overall, PCBs 25 and 50, but the bi and di and monos you can have even higher. I'm going to talk now about PCBs and products. Cheryl started on this. I'm going to talk about some newer data. We're going to drill down and also look at a congener level. I'm going to talk about 2 studies that I'm not involved with, so I won't be able to take detailed questions on these, but I'll share the results. They're pretty self-explanatory. I've got a link here to both of the one project report and the one presentation that was given to the task force if you want to dig into further details on your own. First one is product testing conducted by Ecology, summarized in a 2016 report. Cheryl touched on this briefly. I'll drill in a little more detail. And then some recent work that EPA has done, where Ecology looked at 201 products. EPA looked at 16 different products. We'll look at what was found, both in terms of total PCBs and the distribution of various congeners. So this is the Ecology 2016 report. The summary: evaluate whether consumer products contain PCBs, and if they do, evaluate the contribution from organic pigments and dyes using PCB11 as an indicator, and then also evaluate the range and amounts of PCBs that were found. So 216 samples from 201 different products, caulks, children's products, clothing. You can see a pretty wide range of products tested. Summarize all of those results in a fairly simple bar graph. PCBs are found at about 90%, the observable levels at about 90% of the products tested. So we did have 10% down here that were less than the reporting limit. 90% of the samples, though, did have detectable and measurable levels of PCBs. Biggest bulk was between 1 and 10. Oh, excuse me. We had 30.6 between 10 and 100. About 30.6 between 10 and 100, 36 between 1 and 10. We got out these higher levels. We had a few percent between 10 and 100, and actually 1.3% were above 1,000 parts per billion. So quite a distribution of PCB concentrations in the samples. Mentioned that 3 of those samples had 1,000 and greater than 1,000 parts per billion. Those 3 were cereal packaging. That was at 2,300 parts per billion. Yellow foam, also at 2,300 parts per billion, and then children's yellow sidewalk chalk at 1,060. Drilling down a little deeper at where those PCBs came from, For these three that had greater than 1,000 parts per billion, all of them, PCB11 was more than 99% of the PCB in the product. So pretty clearly a PCB11 product problem for these specific products. More recently, EPA has been doing some product testing to look at potential sources of PCBs. They're also evaluating different methodologies for testing it. I'm going to focus just on the PCB results. They looked at 16 different products, more color focused. So we've got modeling dough, art paint, finger paint, crayons, sidewalk chalk, wafers box, various chalks. So you can see the range of products. What they found was 7 out of the 16 products had detectable PCBs, higher detection limit than what ecology was using. So that's why instead of seeing 90%, we're only seeing about 45%. Measuring concentrations up to 325 parts per billion. 6 out of those 7 products, the only detectable PCB was PCB11. So again, looking at these products, it seems to be a PCB11 issue. We're not seeing other inadvertently produced PCBs at largely measurable levels. So here were the 6 that had PCB11. The highest was yellow glitter foam at 325 parts per billion. So we are seeing PCBs in products below TSCA levels, largely comprised of PCB11. Which I'm just hitting my conclusion slide. So most products that have detectable PCBs, PCB was the dominant congener found, especially in the ones that had high total PCB concentrations. Point Cheryl made, and that I'll reiterate, the observed levels were well within allowable TSCA limits. The highest observable concentration was 2,300 parts per billion, which is 2.3 parts per million, less than 10% of what the allowable level was. So there are PCBs in products, but they're not very close to TSCA limits. So that's good news. Less good news, how do these levels compare to what's in water quality standards? Just throw a couple numbers up here for comparison. You had heard Brooke and Cheryl mention the prior Washington water quality standard of 170 picograms per liter, or 0.0007 parts per billion. The current standard, consistent with the EPA criteria, of 7 picograms per liter. So let's just do a comparison of how much dilution you need in order to meet those standards for a given level amount of PCBs and products. As we've seen earlier, TSCA allows 25 parts per million as an average, 125 parts per billion if that's PCB11, 50 is the max, 250 if it's primarily PCB11. If you took the most optimistic case of the 25 parts per million and the older, less stringent water quality standard, you still need to dilute that product by 150 million fold to get that PCB concentration down to what the water quality standard is. You take a less optimistic case, you take the current standard of 7 picograms per liter and account for the fact that you're allowed more PCB11 in the product, you need to dilute it 360 billion fold in order to meet the water quality standard. So you get some idea of the level of mismatch of how much PCB is allowed in the products by TSCA versus how much is allowed in the water quality standard. A lot of water coming through the Spokane River. Is there enough to really dilute concentrations by that much? And that's what we'll get into next. So I've got an information-rich graph here from work we did for the task force, looking at PCB concentrations in water and fish in the Spokane River in the recent 2014 through 2018 water column data and 2012 fish tissue data. What we looked at were which 10 congeners were highest in the water and which 10 congeners were highest in the fish. So what we have here in the orange are water column concentrations in picograms per liter. What we have here in blue are the fish tissue concentrations, micrograms per kilogram. These were the individual congeners that were highest in the water column or highest in the fish. Some you'll see showed up in both categories. So what do we learn from this? First thing we see is, I don't know if you can read that in the back, that label down there is PCB11. Downstream of Spokane, the single most prevalent congener of the total PCB distribution is PCB11. So it's certainly showing up in the river. Other congeners associated with inadvertent production, not nearly as prevalent. This was not a full fingerprinting analysis like Dr. Rotenberg does, but if you look at PCB 206, 208, 209, or 123, some of the other inadvertently produced congeners, we don't see them showing up in this list down here either as being prevalent in the water column or prevalent in the fish. So it certainly looks to be a PCB11 problem and not other types of inadvertently produced PCBs. Of interest to note, PCB concentrations alone exceed the EPA criterion and the Washington State standard for total PCBs. You're allowed 7 picograms per liter of total PCBs, the sum across all congeners. Downstream of Spokane, we're seeing 16 picograms per liter of PCB11 alone. So certainly at problematic levels in terms of meeting water quality standards. Another interesting note, again, the orange bars are water column concentration for given congeners. The blue bars are what was seen in the fish. Even though PCB11 was the most prevalent congener in the water column, we're actually seeing very little of it in the fish tissue. So there's a lot of it in the water column, not unexpected from the physical chemical properties of different congeners. Different congeners bioaccumulate differently. PCB11 is showing up or not showing up in the fish. It's seen to not bioaccumulate nearly as much as some other PCBs. There's certain ones where we can barely detect them in the water column and we're seeing them in noticeable levels in the fish. That's because they bioaccumulate much more than PCB11 does. So to wrap up, what are the findings? Many consumer products detected had detectable PCBs. None of them exceeded the TSCA standards. You've heard that before. It's important to reiterate. New piece of data from the ecology and the EPA testing. PCB11 was the dominant congener present in all of those consumer tests. Occasionally saw hits of other congeners, but certainly the high ones were 99% plus PCB11. So okay meeting TSCA standards. TSCA standards are not protective of water quality standards. The allowable levels of PCB in products are 150 million to 360 billion times higher than what you're allowed in the water column. So you need a lot of dilution, more dilution than we have in Spokane to bring those down to water quality standards. Third point, PCB11 has the highest water column concentration of all PCB congeners. Dan Redline, you'll be happy to know that this is more of a Spokane-specific problem. I've put up data from downstream of Spokane. If you look at what's coming in from Idaho upstream of Spokane, you're hardly seeing any PCB11 at all. So the sources of PCB are coming in from the Spokane, or PCB11 are coming in from the Spokane metropolitan area. It's not an upstream Lake Coeur d'Alene problem being delivered downstream to the lake. PCB11 concentrations alone exceed EPA criterion and Washington State standards for total PCBs. There are levels right now, just the one congener is exceeding the water quality standard for total PCBs. And then finally, we're not seeing PCB as a large contributor to fish tissue PCB concentrations. We are seeing a lot of PCBs in fish, but very little of that is PCB11. So to wrap up with the two key questions I said I was going to address are inadvertent PCB concentrations, assuming allowable levels in consumer products, using TSCA as the target. No, they are not. Are inadvertent PCB concentrations at problematic levels in the Spokane River in terms of meeting water quality? Yes, they absolutely are. So at that point, we'll pause and take questions.
Yeah, we'll take questions for both Cheryl and Dave. And I just want to let folks know, as you're all snapping pictures and rapidly writing, that all the PowerPoint presentations will be available, and a recording of the WebEx will also be available if you would like to share your experience here. So no need to take copious notes. Okay, questions? Yeah, Cheryl, do you want to come up? Okay. Yeah. You should have sat in the front row.
Dave, right? Correct. I have a couple questions. On the, sorry, this is Gary Jones. On the PCB measurements upstream and downstream, the question, I guess, based on our previous speaker is, were those single one-time measurements, or those measurements taken over a period of time? In other words, did you just do a single sample, or did you do samples, say, after storm events, where there could be a spike in PCB11?
It's a mixture of both.
Can you repeat the question for the WebEx folks?
So the question was, the concentration data that I showed, was it a single sample? How reflective of it was it of overall conditions might have been influenced by a storm event? If anything, it might have been less influenced by storm events. So the water column data used there was data collected by the task force, and in 2014, 2015, and 2018, they did synoptic surveys going out over a week and taking samples every day or every other day at those stations. But that was summer dry flow conditions, so those were absolutely not influenced by any wet weather events. Then there were single monthly samples taken. In 2016, one sample per month. One of those events was a wet weather event. The other ones were high flow, just spring snow melt high flow events. So there were a few high flow events, but they were dominated more by low flow samples. So say on average maybe 25 data points went into any of those measurements, with 20 of them reflecting dry weather, low flow.
So your data represents the average of all that measurement?
Yes, I've got these data parsed out 87 different ways because there's multiple stations, multiple fish species. That was an average. The one I showed there was the average of all of the water column data at one station.
Okay, and my last question is, do you have a concentration gradient from the river? You said you start in Idaho, numbers are lower, and then by the time you get past Spokane, the numbers are higher. So have you looked at what occurs during that interim distance?
Yeah, and Cheryl had a good graph in terms of total PCBs. I mean, we look both at congeners and totals, but you're in the low double digits coming out of Idaho, and getting into the 100 to 200 picograms per liter as you're passing through Spokane, total PCBs.
I was saying, if you're low here and you're high here, what's happening in between? Do you see an increase, a concentration gradient in between the points?
Yeah, absolutely. On a total PCB level, you do. As you have various wastewater treatment plants coming in, you'll see a gradual. It's not a step function where it goes from 30 to 150. It's 30 to 80 to 110 to 120. You do see a step function building as you go downstream.
Well, Cheryl, did you want to add to that?
I think it was pretty much what Doug was going to say. We see a gradual increase, and then we also see a bump where we have some groundwater cleanup going on. So yeah, but it is gradually rising up as we go downstream.
And Heather, and then Mike.
Great, thank you. Probably for both of you, two questions. The first question is, basically, if you took PCB 11 out of the equation, how bad would it be? In other words, how much dilution would you need if you took PCB 11 out? The second, or how high is it if you take out PCB 11? The second question is, what about biosolids? Do you have numbers of what we're seeing in the biosolids, and then is that getting down to groundwater? What's that impact of stormwater runoff and that kind of thing?
And if you could repeat the question.
So first question was, let me know if I'm not stating it properly. How much dilution would you still need if we didn't have PCB 11? How are we comparing?
Yeah, so if you took PCB 11 out of the equation, how bad is it in terms of the water column and the...
In terms of meeting the current standard, is still bad. Because it was, at least the one snippet I showed, it was 16 picograms per liter, and the total is in the hundreds. So while PCB 11 alone is exceeding the standard, there's a lot of other congeners when you add them up that are exceeding the standard by a lot more. And then the other question was, did anyone look at PCB and biosolids?
Yeah, this might be more for Cheryl. So what info do you have about the PCBs going into the biosolids? What levels are you seeing? And do you see runoff, stormwater, or groundwater impacts?
Heather, I don't know the answer to that question. Right now, if we have sludge measures, the treatment plant operators or the sewage treatment plants may want to speak to that. I don't have that handy. That would then be composted and be in the product biosolids. And so we also have not tracked that I am aware of. That would be something for our solid waste program. And so I can get you in touch with the people who may have information on that, but I can't give it to you right now.
And we may have a couple people in the room that could quickly answer that. I'm not sure. Jeff Donovan or Mike Hermanson or Spokane County, City of Spokane. Mike Anderson. Anybody want to talk about biosolids? No? Okay. Okay, so Mike, you're next.
Thank you. I think this question is mostly for Cheryl, but the driver for the water quality standard was fish consumption, and as we've learned, different PCBs bioaccumulate differently in the fish. So, is there any interest in reviewing the standard for different, whether it's homologs or congeners or things like that? In other words, is PCB 11 in the fish? Does it make sense to have a 7 picogram limit when, if a lot of that is PCB 11, that really isn't ending up in the fish?
Yeah, that goes back to the development of the cancer slope factor for PCBs, and that assessment was done in 1996. And when EPA worked on that, they developed a sliding scale cancer slope factor. So a less sensitive number for drinking water, but a more sensitive number that reflected the higher level congeners that do accumulate in fish to give us our 2.0 cancer slope factor that is used in the PCB criterion. So whether that congener, PCB 11, is reflected very well in that cancer slope factor, I think it probably isn't. I mean, and that's speculation on my part, but it simply isn't. It doesn't seem like it would fit in the suite of congeners that were used in sort of it's kind of a fuzzy process when that happened. And I'll be right there because it sounds like you have the information. But whether there's interest in going back and looking at that, that would probably be something that EPA would take on, if anyone would. We use, as a state, the IRIS values or the EPA values that they used in their criteria development when we adopt criteria. And so when we adopted our criteria and then when EPA promulgated the 7, we both used the same cancer slope factor, and it's the one that was in IRIS. So I think that, the interest in that is a much bigger question than I can answer. And then, Lisa, you had...
Here, Lisa, I can give you this mic. I was just going to point out that she's talking about the cancer slope factor, right? And so at this point, the water quality standards are all based on cancer risk.
Just for, not all
PCBs,
but for PCBs.
For PCBs, it's based on cancer risk. And so I was talking in my presentation a little bit about some of the neurological effects and things and also the hydroxylated products, which are not considered at all in that. So I think you bring up a really good point that, it may be worth revisiting, but if you do, it's going to be very complicated and could open up a big, very complicated can of worms.
Yeah, and if it happens, I think that revisit is really in IRIS. It's at that program. Now, with regard to non-cancer effects, when we calculate criteria, we calculate them for both the cancer and the non-cancer effects, and then we choose the most stringent criteria, the lowest concentration. So when we looked at the reference dose for non-cancer effects, that's in IRIS, and that reflects immune responses. The criterion that was calculated from that is not as stringent as the one that comes out with the cancer values. And basically that's because with cancer with a 10 to the minus 6, 1 in a million risk level in that equation, it bumps those numbers way down. So.
Other questions? Okay, I'll do Ken and then Ken.
This is Ken Windrum. A simple question. With PCB 11 being so prominent in our system, do the fish or the invertebrates the fish eat, do they have the chemical capacity to convert PCB 11 into the higher stuff that we are actually measuring in the fish?
No.
The answer was no. The second question is, you mentioned the human health criteria. Can you explain what 10 to 6 really means?
I think so, yeah. It's 10 to the minus 6. It means 1 in a million. Okay, so we use scientific notation, phraseology to talk about 1 in a million. And that is the risk level that is included in the criterion calculation. What that means is that if you eat the amount of fish that's in that calculation, 175 grams a day, 70 years on a daily basis, your body weight is 80 kilograms, you have at the end of that lifetime a one-time chance. This is a one-time chance. It's not like a daily thing after you hit 70 years old. A one-time chance of producing a tumor, whether it's cancer or non-cancer tumor. So that's what 1 in a million, that's what the risk expresses.
Also included in that is that you're drinking 2 liters of surface water
And,
every day for 7 years.
right. Well, actually 2.4 with our new exposure factors. But as I mentioned before, the PCB exposure from water versus fish out of that same water body, or fish from any place, because that's what our criterion incorporates, is that big as opposed to the size of the risk that comes from the fish, because the bioaccumulation factor drives much higher concentrations and much higher exposures from fish than water.
So let me just make sure I understand. So over 70 years, if you eat the fish consumption number, so many grams, over 70 years, one person in a million might have a cancerous tumor.
Yes, you can look at it that way, or it could be your own individual probability, 1 in a million.
I'm going to take my
draw.
Harps hat off and put on my Washington residence taxpayer.
Yep.
What would society have to do to apply that same human health criteria to the roads and highways in the state of Washington?
Well, if you were involved in the human health criteria development, which was about, a 6-year-long process, we had a lot of discussions over that. For water quality criteria, we are talking about full protection of the resources, the uses that we protect under Clean Water Act, and we're following EPA guidance in those things. We're looking at involuntary risk, not the risk that you take if you want to go out and do something. If you want to go out and smoke cigarettes or something, we're talking about a risk that if you have to eat fish and you want to eat that much fish, you should have the right to eat that much fish and not be over a certain risk level. It is a very, very difficult conversation because even as we talked earlier, the different levels among federal laws like TSCA, Clean Water Act, Superfund, Safe Drinking Water Act, they're all different. And so as a taxpayer, I don't know what the answer is, but this is where we are, and we are looking for water quality that will be protective of everybody in the state. And that's just it. I don't know. Anybody else want to weigh in on this? Because I talked it for 6 years, and it's tough. I will tell you, it is tough.
Thank you.
So, Ken?
Yeah. Both excellent presentations. I like the way you summarize the data and also break it down in an easy, understandable way. I'm intrigued a bit with the pollutant reduction plan process, which I think is a relatively new tool in the toolbox. And, coming from a pollution prevention background, we often focus on source reduction, or in water quality world is source control. Yeah. Could you speak to how these plans will be developed, and are they voluntary or are they enforceable over time?
Yeah. And I will speak to this in context of variance development because that's the rulemaking that we're currently in. Would that be appropriate? So as part of our Washington state regulations, we adopted in 2016 new regulations that expanded the requirements and responsibilities that are associated with variances to the water quality standards. And as part of those regulations, there is a requirement that every variance be accompanied by a pollutant minimization plan. That's a little different than the federal regulations. The federal regulations only have pollutant minimization plans required with certain types of variances. With Washington, it's across the board. If you get a variance, you're doing a pollutant minimization plan. Now, at application, dischargers apply for a variance. They need to give us a schedule for development of that pollutant minimization plan, and if they can give us the plan at application, that's great. The next step is that ecology reviews the application, and then if we decide to go into rulemaking, which we've made that decision, we're entering this public process now, by the time we go out with the draft rule, we have to have a pollutant minimization plan itself as part of the rule. Now, EPA regulations require that the pollutant minimization plan be part of the rule of the new water quality standards that's developed. So it's not some adjunct, or it's not something that isn't written down specifically early on and then given as a permit requirement later on. It's actually a plan that's in the water quality standards, and then the permit requirements are based on what's in the water quality standards. So there'll be the new highest attainable condition, which reflects that highest attainable effluent concentration. That would get us to a numeric limit for PCBs in permits. And then there's the pollutant minimization plan, and that is a list of discrete activities that would stretch and be predicted, written down for the full duration of the variance. So say we did a 20-year variance, we will have a schedule of 20 years of activities that are associated with pollutant minimization that will be placed into permits. Now, the permits are enforceable, and so that means that, you've got basically another type of limit that has to be met, and it's accountability and enforceability built in to the permit process. Our pollutant minimization plans also from the state regulations are required to include adaptive management, because we know that as we work toward pollutant minimization, we have a lot of ideas. People are going to discover new things. There'll be new technologies. There'll be, bench scale pilot testing types of things. They'll be looking at products that we can, maybe look at better alternatives so we can reduce PCBs in products. All those things, along with education of the community, continued monitoring of the river, just all the work that goes on for the duration of a variance are parts of a pollution minimization plan. And as we work those, 5 years, for the first 5 years, we may have a pretty darn good idea of exactly what actions are going to happen. After that, it'll be that iterative process of, plan, test it out, evaluate it, and then does it work or not? Or are we completed with that? Adaptively manage, continue to roll out. That's basically the structure of how the PMPs would work under a variance.
Okay, thank you. So the question here, we'll take one more question after that.
You mentioned fish consumption is the driver in the setting of the water quality standard. What is the fish consumption rate?
Well, the fish consumption rate that's included in the criterion equation, and really, I will say that there are a number of different things that drive the number, but the fish consumption rate is just one of those things, and it is 175 grams per day. So that's, you get to eat a small-sized meal of fish every day. That's pretty much what it is. And the criteria account for the fact that the fish can come from just about any place. We want fish everywhere in Washington and fish that people consume to be at those low concentrations. But for the cancer-based values, things like PCBs or dioxin that are based on cancer effects, the risk level itself, that 1 in a million risk level, is a real strong driver in the equation. So it's a number that makes it small.
Hi. 2 questions. Do you know what the other levels of PCBs are around Washington? Is Spokane special in any way? And then also, what are the consequences for a community of being over the water quality standard? You went into that a little bit, and then the consequences for a discharger if they're over their
repeat them for the WebEx? The first one was?
Other levels around Washington.
All right, I'm not an expert. I'll give you my understanding. It should be at least be close. Water column-wise, levels in the Spokane River are generally low. Fish tissue-wise, they're generally high. So there's a disconnect, I would say, on an average level, on an average basis, lower than average, for at least for metropolitan-type areas, lower than average in the water column, higher than average in the fish. So maybe because of the lack of solids in the river, PCBs tend to bioaccumulate more, but at the 20,000-foot level, low in the water column, higher in the fish.
And then consequences of being over the limit.
So do you mean over the limit or over the water quality standard in the water column?
Over the water quality standard. Over the limit.
Yeah, okay, so first we'll talk about being over the water quality standard. So right now, the Spokane River is listed as impaired under the Clean Water Act. It's been assessed under a water quality assessment, and it's been impaired based on the old standard, based on 170 parts per quadrillion. So that's sort of where we are in a regulatory status. The rollout of being impaired is that there's no dilution available, right? You have to, now there's other rollouts there too. There is a requirement under the Clean Water Act to do a total maximum daily load, or TMDL, study. To go, and now in some cases we're using an approach called straight to implementation, which means basically, we kind of know what the solution is, let's just go out there and do it. But permitted sources need to be approached, when you have this kind of rollout. Now for permit limits, right now the permits for the 5 dischargers are the 2011 permits. That's correct, Adrian, right? Okay, so the dischargers are meeting those permit limits, but we have not revised those permits yet. We are planning to revise them after we do this variance process. So we have a date in mind. It's going to be like 2021. So that's when the permits come out, that's just the plan. And so with the permit limits, if there is a permit limit of 7 at that point, and that would be a permit limit that is not based on a variance, then the outcome of that is actually really interesting. Can you hold this for me, Dave?
Absolutely.
Okay. Where did oh, darn. Okay, I'm going to go back and get my notepad because I want to tell you a little bit about how compliance is set. Okay, great. So you guys, when we assess compliance with permit effluent limits, so say you've got a limit of 7, we're required under the federal regulations at 40 CFR 136 to use methods that are required in that regulation. So the method that we use to assess compliance is not the method that can measure down into, 10s, 20s, 100, down there where we're starting to feel like maybe that's a number, right? It's maybe a little higher than that. The method that we use under 40 CFR 136 is EPA method 608, and the quantitation level for that we would use to assess compliance is 50,000. So the limit could be 7, but the compliance assessment level is 50,000. We would not use numbers lower than that. We wouldn't use method 1668 for compliance. We would use method 608. So the outcome is that the dischargers, if they will be in compliance with permit limits. They will be putting in treatment processes and doing pollutant minimization program, work under a variance. They'll be in compliance, and they'll be reducing PCBs to the Spokane River.
I think the question, that might have been more detail than you were looking for, but your question, just for me to rephrase it, was given the concentrations in the fish that drive this river to be impaired and listed, what are the consequences
to the permit fees and have discharges. And that was a very deep, did you get the answer to your question? Okay.
That's right, yeah, but we are assuming that if we can work with the pollutant minimization plans, and, it's easier maybe to quantify up at the source end of it than at the discharge end of it. So, yeah, so we will have, a pollutant minimization plan isn't just, here's a bunch of actions. It also has to have ways to measure success.
So any last questions before our break? Okay. It has to be quick.
I was curious, is Washington's water quality regulations on PCBs more restrictive than other states because of the fish tissue issue, or are they basically the same across the United States?
There is a lot of variability in water quality standards across the country. A lot. States use different risk levels. Some states use 10 to the minus fifth. Idaho standards were just approved. The new human health criteria were approved, and they're at 10 to the minus fifth. And the fish consumption rates run the gamut. The old EPA values of 6.5 grams per day are still in place as the basis of calculations for some states. EPA upped that number to 22. Some states have used that. And that's for general population. Here in Washington, we're looking at high-end consumers, so we're using 175. But, yeah, there's a lot of variability in the fish consumption rates. And as far as state standards go, we're way on the low concentration end. Yeah.
Yeah, and I think both Dr. Rodenberg and Dave Diltz can speak to this as well, because they work around the country with PCBs and different standards for different states. Is that correct?
Yeah, so I'd agree with everything Cheryl said. The one other factor I'd add, in the Great Lakes, you'll see standards at this level, because the other variable is the bioaccumulation factor. So if you're in a system where things are very highly bioaccumulative, you've got a long food chain with fatty fish, that will also drive water quality standards down to the levels that we're seeing here in Washington.
I know that New York State has a water quality criterion of 1 picogram per liter for PCBs, and Delaware River is around 15, I think, picograms per liter. So the water quality criteria are not ridiculously low here. I mean, I think they're pretty typical of a lot of places in the United States.
We're slated for a break, and returning here if you could in your seats by 11, and we'll get rolling at that time the next session. Just a reminder, if you don't know, the bathrooms go up to the really large room out there and turn right, and coffee and tea in the back. Thanks.
Made it pink. All right, that's what we were shooting for.
Oh, I know. Yeah. So with can we try a PowerPoint really? Just put on her PowerPoint one more, or her PDF. And when you opened it, with Adobe, there was a double arrow over. I just want to see what happens.
No, it doesn't. So it doesn't try to open it in Adobe.
Are we mute? Should we mute her?
Oh, yeah, we're going to mute everyone on the phone, and we'll unmute when we start back up again. Thanks.
Okay. Hi, we just unmuted WebEx. You guys ready for us?
They can't talk. Maria could answer, but nobody else can
Okay.
answer.
Hi, Maria. Hi.
People could take a seat, please. We have our WebEx rolling now, too. So the next section of the workshop is Spokane River case studies. We're going to hear from someone that's going to describe the municipal wastewater pathway from household to river. We'll have Q&A after each speaker on this. Then we're going to hear from someone who's dealing with the waste stream from a recycled paper. And then lastly, challenges in navigating some of the purchasing policies with the components of certain manufactured products. So starting off the discussion is going to be Amy Sumner from Spokane County, and she's going to talk about the waste stream into the Spokane County plant. Amy's a water resource project engineer at the county, and she reviews and analyzes PCB data for the reclamation facility and has co-authored the county's 2019 annual toxics management report.
Okay, thank you. Can everyone hear me okay? Just to correct, I am not an engineer. I'm a water resources project manager. And I'm going to talk about the characterization of the PCBs in the Spokane County regional water reclamation facility. Our facility is a Class 4 facility providing tertiary wastewater treatment. Our service area includes portions of unincorporated Spokane County, the cities of Spokane Valley and Millwood, as well as portions of Liberty Lake. We currently have a capacity of 8 million gallons per day with the ability to expand in phases up to 24 million gallons per day. We have two influent trunk lines, main influent trunk lines. That's the North Valley Interceptor and the Spokane Valley Interceptor, which convey wastewater to our plant via two pump stations that are shown on the map. Under our NPDES permit, we have been sampling the influent at the two pump stations and the facility's effluent since October 2012. The county also completed a systematic track-down sampling program between 2013 and 2016 to help us identify potential PCB sources in our wastewater system. Our data analysis through our 2018 annual toxics management report made us pretty confident in three things regarding PCB sources. We know that PCBs appear to be coming from many small distributed sources throughout our system. Aerochlors and aerochlor mixtures are our primary sources of PCBs, and PCB11 appears to be the only non-aerochlor source to our influent. So when I came on board last year, we got together and tried to decide on what we wanted to look at for our 2019 annual report. And we wanted to specifically look at trends over time, as well as if we can glean anything more from our track-down sampling. This presentation, I'll go over the things that we've learned and the analyses that resulted in those conclusions. So what did we learn? PCB sources to our facility have not changed over time. Sources of PCBs differ among land uses. PCB 11 currently appears to be decreasing in our influence, and our effluent is really difficult to assess. So sources of PCBs are not changing over time. We know this first off by looking at the homolog patterns of our influent samples. This shows our homolog patterns for all of our samples for the SVI with the Spokane Valley Interceptor. As you can see, the dye PCBs are this orange color, pensive PCBs are this blue color, and the decas are this orange color. So it goes from low chlorinated homolog groups to the highly chlorinated homolog groups. And because of this banding, it's pretty apparent that those sources are not changing over time. The same thing for the NVI. There's a little more variability in our patterns, but generally they're pretty consistent.
Sorry, NVI?
The North Valley Interceptor. So if you go back and forth between these two, looking at the average homolog composition on the right, or left, sorry, you can see that the biggest difference between the NVI, or North Valley Interceptor, and the SVI samples is that more of those dye PCBs, this orange color here. And we'll talk a little bit more about the differences between the two throughout the presentation. You can also see from our positive matrix factorization analysis, or PMF analysis, that our sources have not changed over time. We can't really put our results in a time series because the county, each year it conducted a PMF analysis, used all of our data, all of our available data to do the PMF analysis. This was to ensure that we had enough data to run the model. So it's been cumulative over time. And because of that, each year we get slightly different results. But over the last 3 years, we've come across 5 main components. Those are Aerochlor 1254, Aerochlor 1260, Aerochlor 1248, or sometimes a mixture of the aerochlors, Aerochlor 1242, which also resembles dissolved phase, and PCB 11. So the PMF analysis does a pretty good job overall of reproducing the county's data, but the congeners associated with inadvertent PCBs generally do not have a good fit. What this means is that the sources may be different than those identified in the previous slide from the PMF analysis. But because of that, we don't know exactly where those sources are, and it's likely that they're coming from multiple sources. Lisa kind of went over this before in her presentation, but for example, the congeners 44 and 45 could be resulting from partial dechlorination or from as a byproduct of silicon production. In the process of doing all of these analyses throughout the years, we have not identified any other evidence of other inadvertent PCBs to our system. So we haven't been focused on those. So the other thing that we learned is that sources differ among land uses. We learned this by reassessing the track down sample sites by taking the current PMF profiles of those sites and combining them by land use. So we looked at residential, commercial, industrial, and mixed uses. The mixed uses were where the site uses were about equal, so we couldn't really put them into another category. And the other categories are where the dominant land use is 50% or more. And so you can see here for this particular crowd, PCB 11 is one of the factors, and it is higher in our industrial and mixed use areas. You can also notice that the SVI, or South Valley or Spokane Valley interceptor, looks a lot like the residential profile. And that's because 86% of the flow coming to the Spokane Valley interceptor pump station is from residential areas. So that signature is not really being diluted by any of the other uses in the lower Spokane Valley. The NVI, on the other hand, or the North Valley interceptor, doesn't look like any of these, and so it's likely that it's more of a mixture of uses that's contributing to the NVI. And that's partly why that NVI homolog pattern had a lot more variability, because there's a lot more going on. If I had the homolog patterns for these sites, there's a lot more variability in the homolog patterns for those types of uses, the non-residential uses. The next thing that we looked at was PCB 11, and we learned that it appears to be decreasing in our influent. This plot here shows the annual average of total influent PCB 11. So this is both our NVI and SVI samples combined and averaged on an annual basis. And you can see there's not only a decrease, but the standard deviation, or the variance in those levels, has been reduced. So we wondered if this was a statistically significant decrease, and we did a one-way analysis of variance, or an ANOVA test, and it shows that this is a significant temporal effect. So we are seeing a decrease at this time. We believe that this decrease is primarily due to a decrease in our North Valley interceptor basin. As you can see in the scatter plot, the SVI, or these orange dots, are pretty consistent around 300 and 550 picograms per liter, whereas the NVI is dropping from about 2,000 picograms per liter to about 500 picograms per liter. Currently, we're not sure why this is occurring. Possible reasons could be dilution, or a drop in dye-related industries in the NVI, or the reduction of the use of yellow dyes. So what does this mean for our effluent? As far as we can tell, our influent doesn't greatly affect our effluent. This is because our effluent is much lower levels, averaging around 100 picograms per liter when corrected at 10 times the method blank. So we think that there's a lot of uncertainty in the levels, in addition to there's problems with line correction, in addition to our facility operations being very complex. We are pretty confident that our effluent is primarily dissolved phase and low molecular weight PCBs. This has been confirmed each year when we looked at the homolog patterns, as well as the PMF patterns that come out of the analysis. Again, just high dissolved phase and PCB 11. But when you look at our homolog patterns over time, you do not see any consistency whatsoever. This is why we're thinking that light correction could be introducing artificial trends, or because the levels are being so low, we can't really figure out what's going on. And our facility could also, we could change processes or use different chemicals, and maybe that's affecting it. But so far, we haven't been able to link anything up. To help us better understand this, now that we have more data, we decided to do an effluent-only data PMF analysis. So when you look at our effluent-only and run it through that fingerprinting, you see that instead of the 5, we're only getting 4 factors. So that factor for PCB 11 drops out, and that's because it's accounted for in all 4 of these factors, with most of it being in this dissolved phase factor. So with this, our effluent looks a little bit more consistent, but we're seeing when our effluent goes above 250 picograms per liter, that's primarily accounted for by our floors 1254 and 1260. We also looked at the effluent PCB 11 concentrations, both the annual average and the total PCB time series. And again, there's no apparent pattern because this is greatly affected by blank correction. This data here has been corrected at 3 times the method blank, and even at that correction level, only 9 of our samples are detected for PCB 11. When you compare at the same correction factor our influent and effluent, we have a removal efficiency at almost 99% for PCB 11. And that's what I kind of want to end on, is that in spite of what's coming into our influent and the fact that we can't really explain what our composition of our effluent is, we do have a high PCB removal efficiency at about 99.7% on average, with a minimum of 98.7%. So if you have any questions, feel free to contact me, and if we have
Actually, we'll take Q&A right now if we can.
Hopefully I can answer things.
Questions? Oh, got all the wastewater people. Okay, hold on.
Uh-oh.
It's good. Ken and then Mike.
On your, the residential one, it's the SV one?
The SBI?
Yeah, that's the one that has a lot of residential, right?
Yes.
Have you seen an increase in flows from that area due to development?
Our influent flows are increasing. I can't remember if it's both in the SBI and NBI, or I just recall there being an increase in total. And that's why I was saying some of the decreases that we're seeing, too, could be due to dilution, since we're adding more water to the system.
And the other factor is, have there been any major collection system maintenance done to minimize the holes getting the surface water stuff into the pipe?
So far, we haven't noticed any infiltration into our system, and we do have a program that runs that. I don't know how often it's done, but.
I was curious to see your effluent with the Aeroflor 1254 spikes. Do you have any thoughts for that? What does that correlate with spike in influent PCB 1254 Aeroflor 1254?
Okay, so I did notice one thing. I was kind of checking this out when I got these results back from Lisa. And unfortunately, our track down sampling has been pretty sporadic. We didn't get a full snapshot of the system. And one of the times that we did have a track down sample site sampled at the same time as the effluent, I believe it was this October 2013, we did see a track down sample that came through with a heavy load of that Aeroflor. So, and then we did see it in the effluent. So there is a possibility. It's just a lot of our track down samples were not conducted at the same time.
Did that answer your question? Okay. Other questions for Amy? Okay, I'll just go up in a row here.
Mark Vincent. One of your, on the examples page very early on, you mentioned that the PCBs from TiO2 and blue and green. Was that test work you've done, or was that from the literature?
That was from the literature.
Okay.
This was just basically saying that since we were not getting these signatures as part of our PNF analysis results as a primary source, we don't know where they're coming from. And so if folks are dumping wastewater into the system that have these products, then possibly that's where it's coming from.
Okay. And just one favor, when we're talking pigments and dyes, they're very, very different.
Yeah.
And that just wounds me when you call a pigment a dye. It's just very wounding. And
I apologize.
Just from an education perspective, I don't know if it's for you or people in the room, where are the PCBs coming from in the residential sector? I'm just confused.
Most likely from building materials, I assume. If residential areas are undergoing construction or reconstruction, well, I guess not construction since that would be new materials. But if someone's refinishing their old hardwood floor or has an old upholstery item that they're cleaning and that water is getting dumped into the drainage, then it could be coming from that. Yes.
Yeah. There also, all the electrical equipment still could contain PCBs, and the building materials and adhesives and stuff in the buildings and stuff. So there are still, it surprises me too. I hate to think that there are still these PCBs in my home, but there probably are. My house was built in 1963. It's probably got some PCBs. I wanted to ask a question. Being from the East Coast, I know that your plant has really, really good treatment compared to the plants that I'm used to. You have terrific solids control. You have virtually zero solids in your effluent. And that probably explains why you get such terrific removal of PCBs. But is that true for other plants in the watershed as well, or is it just Spokane County that's as good as that?
I would have to leave that up to other folks who work at other plants because I moved here a year ago, and I've only worked at Spokane County, so I'm only familiar with our plants this time.
Yeah, so I can start to answer that question, and then I'm going to defer to a couple people in the room. But as a result of a DO-TMDL to address nutrients in the water, all of the permittees are in at different points in applying a next level of treatment. So that in part is affecting how well they're removing. I'm going to hand it over. Coeur d'Alene, you guys just recently finished. Do you want to say something about that?
Yeah, I can speak out loud. That microphone doesn't reach the webinar. It does. Oh, it is? So yeah, Coeur d'Alene just put in a membrane system as well, and I know many other people are doing something similar to that. And it removes, like you said, virtually all the solids. The membrane is smaller than smaller holes than the test method does. So that's where all of our PCBs are being removed as well.
Anybody else want to speak to this or this point? I will say that the Spokane County facility was one of the first, well, I'm not sure, Rob can probably put this in better words than I can, but it was one of the best facilities in terms of treatment when it was installed in 2011. Yeah. So now other folks are coming on board. Other questions? Okay, one last question.
Hi, so when you did your blank correction for your effluent, were you subtracting those blanks from your concentration, or were you censoring?
Okay, so that's a complicated question. For the PMF analysis, they were done by subtracting the max blank. So all of our blanks were put together and created sort of a maximum blank and then subtract it. The effluent data that I showed is all been blank corrected at 3 times the method blank using censoring. So if it were 3 times the method blank per congener, then that number went through and became the total. Does that make sense?
Yeah, so do you think, since you had to do that correction and considering that all of your influent wastewater has to go through your entire treatment system, including membrane filtration, do you think your PMF analysis of the effluent system, where you get the R chlors and things like that, do you think those might be simply ghost readings, or do you think there's actually, those R chlors really are present in your effluent, or are they just kind of showing up as a result of the mathematics?
Right. I think they're really showing up, but this is something that we actually wanted to talk to Lisa about, is now that we know the best method for blank correction is 1 times the method blank using censoring. We didn't know that when we did the PMF before, and we used the subtraction method because that's what was believed to be the best at the time. So we're thinking about redoing that to see if we get something different, but we haven't decided on that yet.
This is where I was when I gave my talk, I was pointing out that we have this paper that Amy helped me write that was looking at all the different ways that you can do blind correction, because we could literally sit in this room and argue all day long about how to do blind correction. And that paper was about the water column of the river, not specifically about the wastewater treatment plant. In the water column of the river, what it showed was that it doesn't matter how you do your blind correction, PCB 11 doesn't go away. That is definitely in the water column. No amount of blind correction will make it go away. In the effluent of the Spokane County plant, I'm not sure. We need to maybe redo some of those numbers. But the bottom line is PCB 11 is definitely in the river, and it's coming from somewhere.
Great questions. We are going to need to move to our next speaker. Thank you, Amy. Excellent presentation. We need to move to our next speaker. So if you still have questions regarding this, because I actually have one, but I'm going to have to ask later, reserve them for lunch. I also want to encourage people on the WebEx that if you have questions, you can put it in the chat, and Andy will let me know, and we'll voice your questions as well. We haven't gotten any to my knowledge to date. So our next speaker, most of you know, is also one of the reasons that we're actually having this workshop.
Don't blame me.
I am blaming you. And Doug Kropitz, he's worked in the energy and pulp and paper fields for over 34 years, not 35, and he's an environmental engineer. He's served as IEP's mill manager since 2004.
Environmental manager. I don't want the mill manager position.
Mill environmental, that's what it says, mill environmental manager since 2004, and he's also a very active member of the Spokane River Regional Toxics Task Force. He has a bachelor's of science in mechanical engineering.
Take it away. Can everybody, is this on? Okay, everybody hear me? Excellent. Like Lisa Bodenberg and my new friend Gary, I am from the East Coast, so keep up. Our company is the poster child for the inadvertent PCB issue, mainly because we are overwhelmingly, our source of PCBs comes to us as iPCBs from the recycling of newsprint and manufacturing our product. I think you're starting to gather that there are other sources of iPCBs that are coming into our watershed through municipal treatment plants, albeit we may not quite understand what that actual source is. I'm kind of surprised we didn't pick paints in our homes as a very obvious source. How many of us wash our paintbrushes, or we're just getting it through volatilization from the paints or whatever have you as well, too. We're seeing it in groundwater. We're seeing it in many, many places throughout our watershed. So I'll get into a little bit of that detail. Just a little bit of background on our company. We've been here in Spokane Valley since 1911, and much to your surprise, I was not here when we opened. But even though we're over a 100-year-old facility, we're the most modern facility of our kind in North America, and that's due to significant reinvestment by our ownership into our plant. We have the newest newsprint paper machine, and actually, because of the decline in newsprint, we've shifted more towards specialty papers. We're making over 50 different grades of paper on one paper machine, which is pretty unprecedented in our industry. Most of our competitors make one, maybe two, very rarely three different grades of paper. We're making 50. That's all because of the technological updates. We put in a lot of technological updates as far as the processing of our pulp fibers. We actually reduced our natural gas consumption at our facility by 90% over historical values and reduced our carbon footprint by about 35,000 tons per year, receiving an award from our governor on that effort. We have the most advanced wastewater treatment system of any pulp and paper mill in North America currently, and we are installing, as you've heard, ultrafiltration membranes. We'll be the first pulp and paper mill in the world that is actually treating 100% of its effluent with membrane technology. So these are significant investments that are setting us apart from everyone else. We're also a natural resource company. We own 121,000 acres of forest lands here in northern Washington and eastern Idaho. We do not use that fiber to support our pulp and paper mill. We're supporting the local forest products industry, and indirectly we receive wood chips, and I'll talk about that here in a little bit. As part of that sustainable forest management, we plant about 500,000 trees annually from a sustainable perspective. So speaking of sustainability, we've been embracing environmental stewardship. I mean, it's just part of what we do. We've been doing the green thing long before it was fashionable. On the wood basket, I won't spend too much time, but we're planting those 500,000 trees. We harvest our forests, and we provide that to the local forest products industry, local sawmills, that they turn those round trees into rectangular or square boards. You can only do that, so much of that, and you end up with waste wood chips from that process. We receive those as a residual material from our local forest products companies as commodity products to them. We're manufacturing our paper from waste or residual materials. We're not using virgin wood fiber for that purpose. The other side that's of more importance to our discussion today is on the recycled paper side of things. We installed our recycling facility in 1991 in response to California adopting standards and requiring 60% recycled content to all paper used in the state of California. I'll speak a little more to that tomorrow on our market drivers. But being a West Coast mill, in order to be able to enjoy that market share, we installed that facility in 1991. Mike thinks it was his fault, but I think there was another driver, Mike, but you were probably a part of the picture. So we're producing a paper product. We're shipping that off, and I said, newsprint's accounting for less and less of what we do. It's less than 50% of our overall production right now. You've heard of names like USA Today, San Francisco Chronicle, Seattle Times. They're all declining publications. So we're shifting more and more into all kinds of different specialties. I don't even know what all of our paper's end use is. Those placemats at McDonald's and all your fast food restaurants, wrapping paper, book stock for textbooks, dime store novels, on and on. So a lot of advertising, et cetera. So we have our own shipping firm. We ship our paper off to our publishers. Our friends from the inks and pigment industry are providing products to our publishers who are printing that material, and then we actually bring that paper back after it's been used. So we're collecting our paper from as far as 1,500 miles away from this facility. That's why a Washington state-specific solution isn't going to help a company like ours, because we're getting as far as Canada, all over the United States. So we bring that paper back to us, and that process continues. So that's just a little bit of background on our company. This side of the equation on the circular sustainability is what's currently in threat because of this issue that we're talking about today. We're having to meet these very stringent standards. So there's going to be a little bit of redundancy here. You've had some really good presentations this morning. They say you have to hear something 3 times in order to get it to sink in. So if it's not getting into your head by now, you might want to do a little self-evaluation. So Toxic Substance Control Act banned PCBs in 1979. Pigments, you've heard the 50 ppm number, maximum 25 ppm number on average. EPA recognized back in the day when they banned PCBs under the legacy concept that there were still chemical manufacturing processes that produced pigment or PCBs inadvertently, and specifically even recognized pigments. This is all out of federal regulations, and specifically you can see that pigments that contain 50 ppm or greater. So that remained within TSCA until 1982. After that, it became reserved, and I believe that everything just falls under that general category of the 50 and 25 ppm source. We're throwing these numbers around like they're actually tangible numbers. 7 parts per quadrillion. It's so hard to get your mind wrapped around that, whether you're a scientist or not. That's 10 to the minus 15. Draw yourself a decimal point in your head, put 14 zeros down in a number. That's what we're trying to achieve here. What I'm trying to convey to you is the difficulty that we're dealing with, the challenge that we're dealing with here in Washington State in attempting to try to meet these standards. Dave threw some numbers around. I'm going to throw them at you a little differently. There's the federal TSCA allowance at 50 parts per million maximum, which affects us as far as what's allowable in these inks and pigments by law. And then we're trying to meet a standard that is over 7 billion times lower than that number. Our friends with the downstream, the Spokane Troubled Water Quality have troubled water quality standards of 1.37 parts per quadrillion. I always have to get an analogy to wrap these things around my head. A part per quadrillion is if I take a dime, I drop it off somewhere here in the state of Washington, go find it. I got to find 7 of them in order to meet these standards, or it's equivalent to a dollar bill dropped in the lower 48. I don't know if anybody that's been around the United States, it's a pretty big place. So that's what we're faced with. And keep in mind, we can't just meet 7. 7 is the number. We're going to have to be below 7 in order to be able to meet that standard. So essentially the number is 0. We have finally moved to 0. That's essentially what we have to meet. And so you can understand the significant challenge associated with trying to meet that. We can't measure it. We certainly can't meet it. So one thing I want to convey to you is we have the most advanced treatment system of any pulp and paper mill in North America, and after we put the tertiary treatment UF membranes in place, we're going to have the most advanced treatment plant of any pulp and paper mill in the world. We're removing about 90% of the PCBs that come into us right now. We don't know what we're going to do on the tertiary treatment yet. That's going in November of this year, or by the end of the year we'll have it operational. So by next year we'll have some better numbers. But we're 21 million times higher than the standard with the most advanced treatment system in the United States as it currently exists. So, the county's getting fantastic removal. If we get another 90% of 21 million, we're still not going to quite be there. So anyway, that is the challenge that we are faced with. These are the PCBs that you typically see in pigments. This is Hugh and Hornbuckle. I know, Lisa, you've worked with these folks in the past as well, too, and they basically showed a kind of a congener profile of the various types of pigments that are out there, Hansi yellow, monoazo yellow, and our inks and pigments folks that I'm looking forward to hearing from later can speak more to all of these things. But these are typically the pigments, the PCBs, congeners that are detected in various pigments. This is IEP. So this is typically the congener profile we see, and you've heard a lot about PCB11 today. It is certainly the most overwhelming source, congener source to our facility. And if you match up most of these pigment or congeners, you'll see that they match with other pigments as well, too. We have very little control over what comes to us. Remember, we're collecting paper from as far as 1,500 miles away. You don't know how much color is coming from what location and where. It just varies consistently over time. You saw this graph by Dave earlier in regards to PCB11 being the most overwhelming PCB congener and its exceedance of the water quality standards alone by over 2-fold. This is a workshop today. We've got a lot of smart people in this room, and I want to kind of get the conversation started, or at least get the creative juices flowing with you in regards to solutions. We need to start thinking along the lines of, what do we do about this impossible problem as it is perceived? One thing that I would like to point out, and Dave pointed out, we're seeing it in the water column, but we're not seeing it in the fish to any great degree. So what we're doing here is we're trying to protect human health, water quality criteria. There's going to be some tough conversations that have to be made. We're on the tip of the spear ourselves, so we understand how tough this is, and there's going to be a lot of conversation, hopefully, around some very difficult decisions, but we need to have those conversations. So if PCB11 isn't harmful to human health, not necessarily harmful to human health, but not accumulating in fish and potentially not accumulating in humans, is it problematic? Can there be some kind of consideration on these lower-level congeners in regards to how we might talk about them from a regulatory permitting policy perspective? So, again, there's going to be a lot of uncomfortable conversations, and I'm going to come to that because I don't want to spend a lot of time on this background. I call these BMPs. They're not really BMPs. Frankly, I lay awake at night thinking about, okay, what can we do about this issue? And frankly, we're quite limited because we don't really have control over the source that's coming to us. So frankly, these are the solutions, the only solutions that I can see for our particular company. The first of those is what we're doing today. We're investigating TSCA. We're investigating iPCBs. The chair of the TSCA work group. We're looking at all kinds of novel approaches to how to deal with this. EPA, and Kat, I don't mean to target you, but they're resistant to actually wanting to make any significant changes to TSCA. And so we have to try to find other innovative methods for being able to do that. I think there'll be a discussion later on in this workshop that, for instance, we were able to find a solution to yellow road paints. Going to substitution that is a non-chlorinated version, and Washington State adopted that as a standard. So we were able to find a solution to the yellow road paints as an example of that. So as part of this iPCB and TSCA work group, that's what we're trying to do. And frankly, that's culmination of this workshop is getting all of the people who are stakeholders in this room to try to investigate these sources. End of pipe removal. We're always looking. We've tested 27 different technologies, primarily for the dissolved oxygen TMDL that was mentioned earlier by Lisa, that we're all having to put advanced treatment technologies in place for. We had to go through 27 technologies to finally arrive at a solution. And in each step of the way, so as not to have to reinvent the wheel or put on more additional, more expensive technology, we always looked at the PCB equation as part of that as well, too. So we believe that with UF membranes and all the other additions we put onto our plant, that we have the most advanced treatment system for removal of nutrients and for the removal of PCBs, at least as it currently exists. Then, obviously, there's no technologies to be able to achieve the zero. And then the third really hard part of this discussion that we really want to resist is the elimination of recycling at our facility. It is the source. And I'm going to show you a slide here after this one that will demonstrate the benefits, if you will, of that. But, the one thing I'd like to say about that, we haven't solved the problem. We haven't solved the problem. What's going to happen to that paper if we stop recycling or if we stop recycling paper in the U.S. because of this issue? PCBs are still going to exist. They're going to go into a landfill. They're going to go into a waste-to-energy plant, perhaps be distributed through atmospheric deposition, whatever have you. We haven't solved the problem. One thing I can say to you is that we're removing 90% of those PCBs right now currently at our facility. We're putting them through a combustion system that destroys them. The best way to destroy, or at least one of the best ways to destroy PCBs, is thermal destruction. So we're actually taking those biosolids. I think it was Heather back there, if I'm not mistaken, was asking about biosolids. We actually take those biosolids. We're producing energy from that. That was part of our natural gas reduction efforts, and we're destroying those PCBs in a very efficient manner. And so we are actually part of the solution, I believe, and we should be using a natural resource used in our own backyard. If we don't use recycled paper, we're going to have to supplant that with virgin wood fiber. And so we just think this is a better environmental solution. But that remains to be seen if that's believed by everyone on a whole. So we're actually going the opposite direction. Because of the California law, we were from 1991 till about 2009, 60% of all raw material supply was recycled paper. Ever since that point in time, we've been decreasing our dependency on recycled paper to determine if we could continue to manufacture those 50 different grades of paper, and at least it's out there as a possible solution for us if indeed we have to pull the plug on recycling. It's not something we want to do because it does give us flexibility in fiber supply and all of the environmental benefits that I had mentioned earlier. So just as an example, I wanted to show you this slide. This is a mill that's actually north of us, Ponderay Newsprint, about 60 miles north of us here, very similar to IEP in configuration. Same products or similar products, more weighted towards the newsprint side, but they actually did cease and desist using recycling at their facility. And what you're looking at here is what happened to their PCB profile with the elimination of recycling. So the yellow line is the percent recycle furnish, and so over time since 2009, they've decreased their dependency, and finally in 2014 have completely eliminated the use of recycling. And the blue is the total PCB profile using EPA method 1668 on a quarterly basis. Essentially, you can see what happened. They went near zero. Now, of course, there is no such thing as zero. The ubiquity of PCBs such as they are, they're in the intake water we're bringing into our facilities. There's going to be another chemical product, et cetera, et cetera. But essentially, you can see what happened here is very profound, the impacts of that. So perhaps maybe that combined with our advanced treatment technology might be the solution, if we indeed want to do that. So, as I mentioned earlier, I want to focus more on the solution side, assuming I have enough time to roll. You just shut me off whenever you need to. But I want you all to start thinking. These are the things that wake me up at 3 o'clock in the morning trying to solve this problem. So they may be a little dreamy or nightmarish, might be the better word for it. Again, this is going to make everyone uncomfortable in the room, including myself, because these are not easy discussions to have. And we're going to get pushed back from regulators, from the pigment industry, from ourselves as far as technological development. But we got to kind of put that stuff aside and figure out, because when you're 7 billion times apart or 38 billion times apart in in response to the Spokane Tribal Indians water quality standard, one thing isn't going to do it. You're not going to eliminate pigments. You could pull every discharger out of this water body. It's not going to meet the standard. There's all these other ubiquitous sources that are coming in that have to be resolved. So it's going to take a culmination of a bunch of different solutions to ever get us there. And each one of those are going to be a part of that discussion. So I think about these things from technical, regulatory, policy, legal perspective. So I'll just throw a couple technical ones up. I don't want to bias you, but these are the things that I think we need to talk about, and I want you to think also as we go through this workshop of other ideas. We're counting on you to bring new ideas to the table. So on the technical side, the one that's going to make the pigment manufacturers perhaps a little uncomfortable is, can we use alternative products like we did with the paints for the yellow road paint? Do they exist? Are they even out there? Can we develop new alternatives that are non-chlorinated, that perhaps would be lower PCB containing? I don't know the answer to that. You guys know that answer, maybe, but we certainly want to have that discussion with you. Use or develop products with reduced levels of PCBs. Is there options that we have available, say for publishing and printing, that would have lower levels of PCBs in them? This is what makes me uncomfortable. It's very expensive for us to treat and try to remove what's coming to us as a source. Millions upon millions of dollars. It's estimated we're going to spend close to $1 billion as a community just on this nutrient issue alone. So what's the PCB cost going to be, and to what value? What benefit are we actually going to get out of that? But we're going to continue working on that as part of our BMPs. So I'm just going to leave it at that and have you think about other technical solutions. Are there other things from the pigment ink industry that we can do? Are there other technical considerations? The other one is regulatory and policy. This is the one that's going to make our regulators in the room uncomfortable. But really, if you think about it, we do not produce, we don't manufacture PCBs. We think we're doing something environmentally responsible by recycling, but because of law, because of federal regulation, we're getting PCBs coming into us. Then because of law, federal regulation, state regulation, we have to meet and remove down to a level of 7 billion times lower or higher. So, perform a risk assessment. Is PCB 11 really bad? I know we've talked about its breakdown and things like that. We've seen articles where, I think, Lisa, I don't remember, it came out recently where we saw that breakdown of the PCBs and they said that it wasn't harmful or toxic. Are they? That needs to be answered. And I understand EPA is actually conducting a risk assessment, although it's not full-blown, but is that a possible solution? And I've heard this. I don't know if this is true, and I hope that our pigment folks will address this, is, other countries do not regulate mono and dichlorinated PCBs. I don't know if that's true or not, but is that an option? If that's truly where the focus of a lot of these inadvertently generated PCBs are occurring on the dialoride yellows, et cetera, is this something that could help as part of the overall solution? Again, not one is going to do it. Don't regulate the lower content of PCBs is basically what that relates to. We know that 12 of them are really bad that are dioxin-like. I'm not saying that we ignore the other PCBs, but we ought to really be putting our focus towards the ones that are really bad and doing what's necessary to get them removed out of the system, destroyed. Deal with that now. We'll deal with the other ones later if we deem them to be harmful to human health and the environment. But I think we ought to be putting our focus on those 12 dioxin-like, at least at this point in time. Establish a lower threshold for TSCA. Again, going to make a lot of people uncomfortable in the room. Can we go to lower levels? Can we manufacture? Do we have the technology? Do we have the advancements in the manufacture of the inks and pigments to be able to say, yeah, you know what, we could do that lower than 1 ppm or 0.1 ppm or whatever the number may be. It's not going to solve it because we're still millions of times higher, but it's a step in the right direction. So that is something that I think needs to be discussed. Rulemaking to bring Clean Water Act and TSCA regulations into conformity, which, this is almost a physical impossibility or regulatory impossibility. In fact, we're doing the opposite. We're not moving the TSCA side of the needle, but we're moving the water quality standards further apart from the TSCA, which makes no sense to me whatsoever. But in essence, that's something that should be considered. Can we provide an NPDES permit offset or exclusion for inadvertently generated PCBs? It's like an intake credit. It's something I have no control over that's coming to us if we truly believe that environmentally what we're doing by recycling that material is more beneficial to the environment because we're removing 90 plus or whatever the ultimate PCB removal is going to be. Is that more environmentally beneficial than putting us out of the recycling business? So, yep, I am almost there. And then this one's kind of a marketing perspective, and I think the next two actually are, is encourage end users. And I think HP's here, and they're going to have a discussion a little bit later on about how they adopted a policy lowering their standard for their particular products that they manufacture and or produce or manufacture or actually receive. So from a marketing perspective, can we incentivize, and basically that's the next one, is incentivize kind of a competitive marketing advantage. Is it a marketing advantage for them to use lower or non-containing PCB products? And again, I'll just leave it at that and say other regulatory policy solutions. You think about it, you folks that are really smart in this room that understand the regulatory policies and procedures and limitations, which I think we'll talk about later. It's easy to say no, we can't do that. I hear that all the time. It's really frustrating, and so just putting all of the onus of the burden on those at the end of the pipe is summarily unfair, and I think we need to do it more collectively because we're not going to solve the problem by ourselves. I think that's it, Lisa.
So thank you, Doug. There are probably questions. I'd like actually to let Steve go ahead and present, and then we'll take questions for both of you because we're running over. I do want to let folks know we're at a pretty PowerPoint-heavy day today, but tomorrow it's primarily going to be some panels and breakout groups to talk about the solutions and thoughts that Doug just laid out on his last two slides. So I encourage everybody to digest those. Maybe we'll try to get them printed out and stuck on the wall for tomorrow morning. Our next speaker then is Steve Jones from Hamilton Manufacturing. He's worked in the erosion control industry for 38 years, and he really brings to this workshop a unique perspective from the manufacturing industry. They're the folks that produce the hydroseed that was sampled in our watershed. So we appreciate you coming and telling your story.
Good morning, everyone. Thanks for having us. This is Matt Smith. He's one of my colleagues here. We're here to talk to you about if recycling does go away and what the impact would be to our company and other companies in this industry. So I'm going to run this video for you, kind of give you a brief rundown of who we are, and then we'll talk to you about some of the obstacles that we're facing. Go for it. Sorry, everybody, just a sec. Now it's going to be super loud, probably. Now the laptop isn't making any noise. It worked for you yesterday, I promise. There we go.
1962, located near the Snake River in southern Idaho. Hamilton Manufacturing is a family-owned business since 1962, located near the Snake River in southern Idaho in the USA. We are proud that we are one of the few companies that make products that are USDA certified, organic, non-toxic, and biodegradable. We specialize in using recycled materials to create superior products in the areas of insulation, erosion control, and beyond. HMI was founded on the principle of environmental citizenship. For us, that means thinking about the entire life cycle of our products, from where the materials of our products come from, to the processes and energy we use to manufacture our products, to how our products interact in the world after they are installed and used.
Recycled materials is a positive way for us to move into making a good quality product. We take ways and means to sort in order to clean out the contaminants and make the product as efficient and clean environmentally as possible. Whether it be, for application domestically or internationally, we take the utmost concern that all of our products that we sell through this facility are non-toxic and very user-friendly in the environment. We make products for domestic application. We make product for international application, whether it be attics, walls, floor space. It has so many benefits regarding, insect control, fire, retardancy, and the R factors of cellulose compared to the other products that are out there. It meets or exceeds their R factors.
Buildings of our insulation products use over 25% less energy than those built with fiberglass insulation. Our Thermalock insulation absorbs over 80% of sound. Our unique process and additive create a distinct fire suppression advantage versus other cellulose insulations, as well as fiberglass and foam products. Our inside insulation creates a non-toxic barrier that keeps pests and other insects outside of the home. Unlike other insulation products, our inside insulation maintains its pest control properties for the life of the structure.
Nature's Own is a line of erosion control and dust mitigation products that are 100% organic, biodegradable, and non-toxic. Our proprietary process creates a strong and durable fiber which enables our products to stand the test of time and the elements. The product has been made to mix easily and flow well, leading to faster application and less problems on a job site. Nature's Own products can be used in a variety of projects, including golf construction, highway erosion control, pipeline soil stabilization, housing construction. We have a broad portfolio to meet every need.
We don't believe there has to be a compromise, and we have proven that for over 50 years.
Okay, so now you guys know how to make mulch and insulation, So the reason why we're here is, been working with Doug here and as a part of the task force, and our products was one of the products tested as far as hydroseed mulch was concerned. And it did show up having PCBs in it, like everything does. So the reason why we're here is just to kind of put this in perspective that if recycling gets eliminated, basically our company does too. And that stuff will end up in the landfill. So we are taking recycled newsprint, we're making insulation, we're making erosion control mulches for us. We ship to 35 countries worldwide. So it's not, it's a big impact. And there are other cellulose manufacturers here in the United States as well that if this thing, turns into a regulation program for us to not be able to use recycled newsprint for making our products anymore, then where does that end up? we wanted to come to you just to kind of just put it out there so you have a better understanding of what that impact would be. So you got some numbers here, so we can. Karen.
There might be some interference.
Okay.
Stay away.
Yeah.
I think just to give everybody a little bit more information about how hydroseeding works, we grind up, we bring in recycled paper in our plant, and then we have a mechanical process that grinds everything up, and we turn it into a product, which is put into a hydroseeder, mixed with water, mixed with fertilizer and seed, and then it's hydraulically sprayed onto the ground. So that product is made as an erosion control product. So it's made to sort of protect the seed and allow the seed time to be able to germinate and grow. And then it eventually biodegrades and turns back into the topsoil with cellulose fibers, so it's organic. I was just sort of listening today about some in some of the other presentations, and I kind of wanted to break down a few numbers for you guys to give you an idea about how we cross over into PCB world here. So Lisa was talking about in her presentation that 209 is green dye. That's correct, right? Pigment.
Pigment.
Okay. So basically, when this is industrial standards, so hydroseeding mulch uses green pigment in the production of mulch, and that's basically a regulatory thing. So if you apply the material, then you know where the material has been applied. If you don't have that in there, then it looks a lot like topsoil. So it's really hard for regulators to actually know how much of that, that material has been applied over the soil. And you're talking about if you don't apply that, then you have contractors potentially cutting corners. I don't like to think that that happens, but it does happen, imagine in every industry. So the consequence is that you would get higher erosion rates. So you have a lot more organic material, topsoil entering into soil sheds, watersheds, so, and potentially into rivers, and that has an implication of, let's say, eutrophication and algae blooms and whatnot. So mainly 209, that's we use recycled newspaper, but it's not the only thing we use. We use probably I think right now 50 to 60% cardboard. Some of that doesn't really have any dye on it. So we have reduced the amount of newspaper that we use overall because industrial-wide newspaper is being reduced. But cardboard is actually still being used for packaging and stuff, so we were able to draw off that. But to give you an idea, the Pacific Northwest, we draw alone probably 13 million pounds of recycled paper.
From Washington.
From the Pacific Northwest. So Washington included. So if you didn't so cellulose manufacturers similar to us are a major user of recycled materials, mainly cellulose, in the United States. And if you create, I think that you have to be kind of careful about how you look at hydromulch and how it's used, and the PCBs in general, and how that relates to watersheds, and if PCBs from hydromulch that are applied on land are actually entering into the watershed and water rates, because you're not counting, let's say, photo degradation, which I found an article here that talks about photo degradation of PCBs, and they're saying the half-life of some particular PCBs are 3 to 8 hours. So when you apply hydromulch, it's the last thing you do. So it's exposed to a lot of UV light, and you might have some of that. And 209 in specific is not something it looks like that is being found a lot in the waterway. So that's something to take into account too. So maybe a lot of that, maybe there's not a lot really leaching occurring.
One thing that I'd like to add is that the mulch industry as a whole is under really strict guidelines as far as being able to get their products approved to be on the QPL's qualified products list through the various states. And we have to do the EPA testing, fish toxicity, solvents, heavy metals, photo degradation types of tests as well. We have to, one of the biggest things that we go through is seed germination enhancement. So you don't get on these QPLs just by grinding up a bunch of paper and doing that and getting on there. We do have some inputs in there that we do to make sure that we adhere to these guidelines. Like I said, we ship all over all over the world. One of the biggest users of our products down is the Amazon jungle. So if we stop doing this, this is the...
You're talking about reforestation, environmental wetland rehabilitation. And the option, you could potentially take recycled newsprint out of the equation, but not at our plant. Our plant we'd have to close the doors. But the other option is virgin wood, and that is used in the hydromulching industry. Virgin wood is ground up and sprayed, but then what do you do about the already influx of recycled materials that we have a problem with in the United States, especially with China not taking recyclables off the West Coast? If that goes in the landfill, then you risk methane production, CH3. So, anyways, just a little bit of perspective. If there's any questions.
Questions?
I have hundreds of questions, but on the hydro seed, for Doug as well. On the hydro seed, did you do the profiling of the PCB, or where is the PCB coming from? I mean, it's a very high result. Robert and I keep going backwards and forwards, and we're just confused where such a high data point's coming from.
Yeah, I think that it was measured by the state, right? So Spokane or the state. Who is Doug? Doug.
Yeah, so the city of Spokane actually had a sample that he tested as far as looking at the products that they utilized, and Jeff could probably speak to it, the guy sitting right beside you, as a matter of fact. So this was kind of one of the opportunities we saw as the TSCA work group, was to evaluate where it was coming from, because there's all kinds of different products that go into making what they do. So we got 4 different hydro seed manufacturers with different binders, different raw materials, and evaluated them. We did not, and we did use EPA method 1668 in a very controlled manner. We did not get the high hits like the city did for that 2.5 ppm, I think it was, that you guys got.
Yeah.
What? Okay.
Yeah.
Of course. But we did find it in other products like binders in a couple of them. So it was a blind study, but we allowed them to share the information so they could produce a lower PCB containing product overall by saying, hey, what's this binder you guys are using that we're not? And so I don't know if that actually happened or not. But
in our industry, the tackifiers are across the board. Some of them are all polymers and so on and so forth. We use non-polymer products, so for that reason, there's some. In the state of Minnesota, I believe that they removed antimony was the biggest thing. So antimony was completely rid of it. So that's what we adhere to.
So and kind of one caution that fell out of that is we've got to be really careful what we're doing here with this very sophisticated method. Perhaps I'm going to call it unreliable necessarily, but contamination issues of potential. Was there one bad sample that was taken? I mean, think about the variability I mentioned about us taking in. We have no idea where the recycled materials are coming from, what amount of color we're getting, whatever have you. Was it real? Was it not real? So we got to be careful about throwing somebody under the bus with one sample. Is basically what my cry out was to, as far as dealing with the purchasing standards and throwing a company like themselves under the bus for one sample. So we got to err on the side of caution.
And that's what I was trying to understand whether Hamilton's gone further to try to profile where the PCB's going. Is it the recycling? Is it the green? Is it another?
It sounds like green pigment could be potentially an issue, and that's not something that you wouldn't be able to take out of the hydromulch. I mean, you can take that out, and you still have an erosion control product you would, you'd still have an erosion control product if you took the green pigment out. It would just be a little bit harder to regulate. I mean, you'd have to, rely on contractors doing their thing, and then rely on regulators to do their due diligence to make sure that you're applying the right amount of hydromulch for erosion control, which is a very important aspect of the material to begin with.
Yeah. I switched to Doug then, because I can speak that. I can speak for it.
Yeah. Doug, burning question I keep meaning to ask you. Have you analyzed your whole process from the door opening to the effluent and whether PCBs are actually generated?
Yeah.
You're doing de-inking, I'm assuming you're bleaching.
Yeah, I actually meant to mention that during the presentation, but obviously ran out of time. We had to do a PCB source ID study as part of our last permit cycle, so we had to analyze all of our processes to determine, where potential sources were coming from. And it was overwhelmingly evident. We were getting hundreds of thousands of parts per quadrillion coming out of our recycle plant. And so, like that's how we made the determination that we were removing over 90% of the PCBs by the time it got to our final effluent. So we profiled all of our systems to make that determination.
Processing where you're getting a generation of cyclone?
No. Nothing evident.
Take one last question. The discussion's just getting really exciting, so I apologize. Oh, two last questions. And then we're going to grab some boxed lunches. We do have our presentation at lunch, but there'll be time to ask additional questions individually.
Great. So, so for Steve, and I don't know your colleague's name, you certainly don't have to use green. You could use blue or some other pigment. So I do think you could just change colors, and you can respond to that. And then, Doug, I can tell that you are an optimist, and you think that this is solved, and I agree with you, even though you did say 30 billion 10 times. I particularly work on phthalates, and phthalates is something that 10 years ago they said it's everywhere, we can do nothing about it. The reality is this, we just did a test of a bunch of products in conjunction with Ecology and others, of over 200 products. 38 of them were paints. We thought that the paints were all going to come up with phthalates. Not one of the paint samples had phthalates in it. And when I talked to some of the coatings people, I'm interested that there were a bunch of coatings and paint people in the room, they said, well, yeah, we took it out. So this is the thing. It can happen. It can go away. And in Europe, it's become mainstream now. Phthalates are a plasticizer that cause human reproductive toxins, for those who don't know. In Europe, they've done a lot of progress. Here, it's become mainstream. Lowe's and Home Depot said we do not want phthalates in our flooring anymore. This is a solvable problem. We want you to stay in the recycling business, and we want the pigment to not be your enemy anymore.
Appreciate your optimism.
And let's go back to the first question. Well, let's go back. Well, wait, that's right. Let's go back to the first question, which is why not a different color?
Lisa, you mentioned, I think in the blue is actually a 209 as well, right?
Yeah. Greens and blues.
So it sounds like, it's not that we couldn't use another color. That's fine. If there was a color out there that was PCB free, yeah, we could do that. It's an easy injection in our industry to do that. So if somebody comes up with an idea, then
we're all ears.
Let us know.
Doug, my question for you was, you mentioned you have membrane technology. Does the membrane technology how low does it go with PCBs? That was actually my question.
Yeah, we don't know the answer to that yet because we don't have it installed. We did some pilot testing. Membranes will move 100% of solid particulate matter. So any PCBs that are tied up to that solid particulate matter will be removed by the membrane. Soluble stuff that will pass through will not. So very difficult question to answer, and as part of that variance discussion that somebody, I think it was Cheryl, mentioned earlier, we have to make that determination. What's the highest attainable condition we can get to? But we need to be able to establish a data set in order to be able to do that. So hopefully 50 to 90% more, depending.
Hi, thanks for being here today, guys. I think this is an important part of the conversation. I know that I've talked with Steve several times about the challenges on getting on WashDOT's QPL for hydro mulch because we have changed specs over time. If you
I'm excited to hear that actually you seem open now to using a different pigment color, because we discussed going dye-free. We understand that regulators have historically liked to see, and the public like to see that green, because they know it's not dirt, and it also helps with the application challenges, making sure you're getting the uniform coverage. But it may not be necessary for application. I think maybe regulators may, now that they know the pigment could be a problem, might lighten up on that. Certainly a different pigment would be awesome. We talked about, beeps, like even if it's just red for a few minutes while the application is taking place, perhaps that's adequate. That seemed to be kind of not an option at the time, so I'm excited to hear that that could be a potential solution. And also we talked about other solutions, and I'm looking, because I don't want the recycling business to go away either, but are there things we can do that will make it better? Another challenge we identified was the in-the-field mixing and the variability, and we have seen, WashDOT has seen contractors add extra dye to make the product look like it's really well installed and super thick. And so this is something that we're concerned over, and, there was also a comment about going dye-free might create bad application and therefore erosion issues, and that's a concern for your product, because then it becomes a finger pointing, is it the product that failed or was it the application? We talked about how that was really a training issue in the field to get that good coverage, and was there an opportunity in partnership to get training, get consistency, make sure people aren't mixing stuff inappropriate in the field, et cetera. And so, we'd love to continue conversations about those solutions.
I think that would be great. Yeah. Maybe we could schedule an appointment and talk a little bit more about what all the options are. And I think one of the main things is you're really you're changing an industrial standard. It's not that you couldn't do that.
You could be the first to start.
You would be the first, yeah. and it would go across the board, and I think the contractors would be a little bit shocked, and the regulators would definitely have to learn how to know that it's installed properly. What's that?
She said it would take at least 5 years.
5 years, okay, well, yeah, maybe with our help we could do it a little bit faster.
I can address one thing, and I know we need to get going. Yeah. So Minnesota is in the process of eliminating dye right now, okay? It's probably not going to happen for at least another 2 or 3 years where it's going to happen. But that puts a lot of strain on the manufacturers, because now we have to produce something especially for that state. So we need to get this changed as a whole, okay? We don't sell a lot on the East Coast. Those East Coast companies will have to deal with that. About early 2000s, we played around with different dyes: yellow, green, blue, purple, you name it, black. Black seemed to be the most popular color at the time, because for UV, we could grow stuff better with it, absorb. But the problem is that green is a curb appeal thing, okay? You see green, you think grass, okay? It's been that standard since I've been in the industry, and I've been doing this for 38 years. So to get that changed, it's going to be very difficult. Maybe Minnesota will set the bar for that. They're just removing dye. So it's just going to be natural wood colors. So, and I don't know how that's going to.
I think sorry, one last point. So just to make a correlation between hydromulch and PCBs within waterways is a pretty dangerous thing to do, because there isn't actually a study or correlation at this point. So what we're saying is we can reduce the stuff because there are PCBs in it, but will it have any sort of impact on the reduction in waterways? I think it would be negligible. You might be able to, if you're measuring it quadrillions, maybe you would be able to make a correlation. Maybe you wouldn't, but we apply this on the land. Nobody hydroseeds in a river or a lake. So just to make that point. Thanks. Thank you very much for having us here too.
Yeah, thank you guys for coming, and maybe just a round of applause for all of our morning speakers.
Okay, Kate. Thanks a lot.
So, You guys have been really patient, and we're running really behind as usual. But it is 12:20. There should be box lunches. I'm assuming they must be out in the hall. Oh, no, they're right behind there. Boy, they were quiet. So there's box lunches. There are some gluten-free and vegetarian options. So those of you who need them, make sure you grab one. And then we have 2 lunchtime speakers. So after you take care of checking your cell phone and get your sandwich, come back to the tables, and I think in about 10 minutes we will start our presentation for lunch. Thank you.
Okay, webinar folks, I'm going to put you on hold and we'll unmute and we'll bring you back out during the presentation.
health effects. No safe level exposure identified, and any exposure is significant. Those are quotes out of that document. And later on, they identified as 1 part per million being the definition of PCB-free, because at that time, that was what the analytical methods could get to. We didn't have the sophisticated analytical apparatus we have today where we could identify congeners. In those days, all we could do was look at error chlors and identify error chlors. We also recognize that we can't control all the PCBs in the environment, right? We're talking about that today. We're talking about where are these in the river? Are they in the fish or in the sediment? Are they here or there? Once the PCB is released to the environment, it's very difficult to control and it's very expensive to clean up. But we did recognize at the time, or EPA recognized, that we can control manufacture. And a key point of the TSCA regulation is that major and extensive economic disruption was an important factor in evaluating whether or not a product or a material would be banned. So when the proposed rule came out then, it banned the manufacture, processing, distribution, and commercial end use. And really we're talking about error chlors at that point. It was noted that we needed more information about pigments and dyes and inadvertent PCBs, but it did establish that 50 part per million. You can see here that the thought was that other regulatory standards would apply for other media, and specifically water. So we're starting to see a point at which water and TSCA, Clean Water Act and TSCA, are starting to diverge. It noted that serious environmental damage may result from deposit in or near water, even with low concentrations of PCBs. So if we think about that, what really the focus of this is to stop the manufacture and creation of the problem, because once it gets into the water and the environment, it's very difficult to clean up. When the final rule came out, that 50 part per million level was there. It wasn't set because of health or environmental harm. It was set because of the disposal capacity for PCB waste at that time. So Wayback Machine, we didn't have a lot of hazardous waste facilities back then. Wayback Machine, they're talking about electrical equipment primarily. They're not talking about PCB and all the other media and all the other ways that it is found in our society. At that point then, also pigments were regulated, and it was estimated that 5,700 pounds of PCBs were produced a year from pigment manufacture. The last bullet here, which is kind of why we're here today, is that EPA expected to control environmental releases to water through the NPDES system. So now we're seeing once again where this regulatory divide has happened. TSCA is controlling manufacture, and it's controlling the release to water through the permit system. Well, of course, like every regulation, when it gets passed, there was immediately a lawsuit. The Environmental Defense Fund sued EPA, saying that the wrong criteria were used to determine unreasonable risk. Environmental Defense Fund was focusing on environmental risk. TSCA, their risk assessment process focused on economic risk. So EPA's reasoning, and they prevailed in this, was that their regulation excluded municipal sludges that had low levels of PCBs due to ambient conditions. We were talking about biosolids earlier. So they are not regulated under TSCA. They're regulated under a different set of regulations. They believe that we should control PCBs through the production of the material. So that's a key theme here. We can control PCBs through the production. That's much more effective than controlling them at the end of the pipe or in the environmental media, because we can't regulate diffuse and extremely numerous sources of PCBs. Again, other statutes available, i.e. Clean Water Act, was identified as the reason that that they set for the TSCA regulation. So the court also sent it back for economic analysis, and there's a special document on inadvertent PCBs. At that point, then, they identified the limit of quantitation of PCB in water at 100 parts per billion. That was as low as they could go at that time. with the analytical tools available. And it evaluated the cost of managing incidentally generated PCBs in 1982. So almost the end of the story here, 1983, the proposed rule was issued where that 50 part per million number comes in again. Some people have asked about PCBs in food. Well, it's not regulated under TSCA. The FDA regulates that. They use their own set of standards and criteria to do that. And in 1983, the Clean Water Act had, I would call them technology-based effluent standards. So they're not the same effluent standards that facilities are faced with today. Today, in the Spokane River, we're talking about water quality-based standards. The 1984 final rule then passed. So, 30 years later, April 2010, EPA opened a notice of proposed rulemaking. They started to ask the question, do we need to look at TSCA again? And they specifically asked the question about this 50 part per million level for excluded products. There are other things in that rulemaking, and it went through a series of discussions, and I think there were some minor rules that were issued after that. But this main rulemaking was never completed. It was never, these questions were never addressed. They remain open. It's now 40 years later. The question here, I think, is, not whether or not we should change regulations, but what is the impact of having PCBs in products today? And I think the main impact and what you're hearing, some of the permitted dischargers in the river, what you're hearing them say is that this is costing a lot of money. We are receiving products that have something in it that we don't want, and we have to pay to clean it up. And not only do we have to pay, our community has to pay. So in Spokane area, to date, somewhere around $500,000 has gone into investing in clean water. I don't even know what the investment is in cleanup of legacy sites. I know we've done quite a few. I don't have the numbers behind that. But you can add that on to that cost of managing PCBs in our area. And it seems like kind of an upside-down economy. When I turn on my water, turn on my tap, by the time it hits the sink and the drain, it has gained in value 4 times, right? It costs me 4 times more to run my water down the drain than it does to pour it out the tap. And for many people, that doesn't make sense. It's a waste product. Why is a waste product costing so much, right? And really, the way to deal with this is to deal with it before it gets into our waste stream, right? So that's what this discussion is about these 2 days. It's very heartening to see a wide variety of people here with a wide variety of interests and value systems and economies. It's really, it feels good. And I think, Doug, you were involved, I think, Lisa, 7 years ago when we had a presentation with the American Chemical Society, and it was hard to have the pigment industry being involved with that. And so it feels very good to see the level of progress that we've come to date, to have what I would call good discussions and positive discussions and solution-oriented discussions. So yes, regulation could be one solution. It's often the last thing because we really want to get there on our own. We want to get there without being regulated. And Spokane River used to look like that. Wayback Machine, once again, that's 1900s. And if you look at the bigger picture of that, you'll see there's outfalls all over up there. It was a highly industrialized city in 1974. That whole area was remodeled for the World's Fair, the first environmental World's Fair. And just recently, the city's remodeled Riverfront Park once again. And so, we have a lot of pride in our city, and we have a lot of pride in a clean environment. And this is the area, Spokane's the place that gets it done. Pass it on to Mike, who's going to give you the current situation. Thank you.
That's great, Adrian. Thank you. And I'm just going to have a brief session here because I want to talk about the update that actually happened, the Frank-Lautenberg Chemical Safety for the 21st Century Act, June 22nd, 2016, because it had been recognized that things were 40 years out of date. TSCA had not lived up to its expectations, at least from an environmental and human health status. And so what that act did, and I just pulled a few words directly out of there. In 1 year, they had to establish a risk-based screening system, and that was human health risk is what they were focused on. And then, and I think they've started doing this, they had to start risk evaluations on 10 chemicals, and these were the 10 priority chemicals that TSCA felt had not been, or people felt had not been addressed by TSCA. A woman, and I'm just going to read something she said, Patricia Coma, she's a research investigator in environmental health sciences at the University of Michigan School of Public Health, said the science is and has been clear. Some people are more vulnerable to toxic chemical exposures than others, in particular children. And as a result, they need extra protection. The U.S. EPA's risk evaluation methods have not kept up with current science, do not account for widely accepted risk evaluation practice, and as a result, leave our communities and vulnerable groups like children at risk. And so the whole point was to first start with the 10 chemicals, and then in 3.5 years, and this is right in the law, and I don't believe this has been done, but I could be corrected on this, there was going to be at least 20 high-priority substances, and I don't know if those 20 have been identified, but we're basically at that 3.5-year point. So the Frank-Lautenberg Act definitely took on this health and environmental risk assessment, saying you have to do this as a result of no changes during the 70s, 80s, 90s, and early part of this century. So it says right in there, the EPA must now make affirmative health risk determinations and consider susceptible and highly exposed populations, and that's what we want them to do. So how does that happen, though? The EPA, as we heard, didn't do anything after 2010 when they had a notice of proposed rule. They haven't acted very quickly after 2016. Well, there's a legal process, and I want to thank it was a memo by John Cummings. He's at the Gonzaga Environmental Law Clinic, works under Rick Eichstadt, who wrote some things down. And basically, you can petition the EPA in a formal matter, and the EPA must consider that petition and balance it against the evidence that the 50 parts per million is not sufficiently protecting human and environmental health. And so this could possibly be a route to examining it, looking at all the numbers. Maybe that's where we look at PCB 11 to see if it's in the same category as the other PCBs, but take a serious health-based risk assessment of this. So I think that's my last slide, and I didn't want to talk too long and go over the 1 o'clock, but I did want to say that I think there are solutions here. I was just talking to lunch about a potential solution to the hydroseed. There are solutions to this. Do we drive it down to 1 or 0.01, or is that possible? Does that get us to where we are with the water quality limits? I think those are very good questions that Doug is asking, and I hope that we spend a lot of this remaining day and a half trying to answer those questions. So thank you.
Well, thank you, Adrian and Mike. a little bit more background in Tosca. I think I learn a little bit more every time someone brings it up. One of these days I'll just read the whole GFR. So to tell you what we have in store this afternoon, we've got a number of presentations that are going to occur. For those of you who are planning to step out at a certain time, I want you to be aware that at the break at 3 o'clock, we are also going to have a sign-up. Some breakout groups tomorrow, and we may break out by topic area if there are some people interested in one topic versus another. So at 3 o'clock, I'll give you specifics, but we'll have 3 sheets of white paper up here with 3 topics for breakouts and some of the questions we're going to ask. And we'd just like to have you sign up for your first and second choice topic so that the breakout groups can be designed and coordinated with the breakout group facilitators this evening. So if you wouldn't mind doing that, that would be great. I will be using those numbers to order lunch tomorrow, so please make sure if you want to eat, you got to sign. Okay, and then the other thing is this afternoon we have a pretty ambitious set of presentations, so I'm going to ask our speakers to try to stick to their time limits. And Emily here, right here at the front, has a 1 and a 5-minute limit sign that she's been holding up. I don't think many people have been watching.
Not paying attention, huh?
Well, when you're speaking, you're kind of, in your own head. But now you know that she has the time.
So I can know to ignore her.
I know. Did you notice how I told everybody about it right before your talk?
I understand.
Okay. So anyway, without further ado, wait, because I have to read your bio. So I would like to introduce Gary Jones, who's come to us from the East Coast. Thank you for making the trip. He's the Director of Environmental Health and Safety Affairs at Specialty Graphic and Imaging Association. So we've been referring to that as SGIA, and if you hear that, that's scary. He monitors and analyzes environmental health and safety regulatory activities at all domestic and some international government levels, and represents the industry and provides membership assistance on environmental health and safety compliance and sustainability programs. He's also supporting SGIA's efforts for the Sustainable Green Printing Partnership.
Yes.
So thanks and welcome.
Oh, well, thank you. Good afternoon, everyone. All right, yes. Always tough to be the first speaker after lunch. When I give a lot of presentations, you never want to be the last speaker of the day or the first speaker after lunch, because first speaker after lunch, man, you're up against what everybody just ate, and everyone wants to take a nap, and I want to talk about printing. So I may put you all asleep by the end of my presentation, but I have to stay on time. So I was invited. I guess the series of presentations we're having this afternoon, they all kind of fit together. So I'm going to kick it off and discuss printing, and I think George will be following me. He'll discuss ink. And then I think we have a dual presentation on pigment. So we kind of get broad and narrow down because obviously, as what we've been hearing, pigments are contributing to the PCB issue. And one of the issues, of course, that Doug's grappling with is, he's recycling things that get printed. So I'm going to talk about printing. And really, I wasn't sure what your understanding of print was and where we were. So I'm going to start kind of broad and maybe get into a little bit more of the details of print technologies and wrap it up with a discussion on sustainability from printing and packaging, which is obviously a topic itself we could spend an entire day on, but we'll just try to summarize and hit some of the big issues. So what is printing? At its basic sense, it's application of text and images for mass communication. It serves a wide variety of purposes, and actually, as I like to think about print affects you every day. There's nothing that you don't do that print doesn't. You don't interact and involve with print in some way, shape, or form. It could be simply as reading the directions on a label. It could be using your microwave. The keypad on your microwave is actually printed. That's a conductive circuit. If you have an automobile, you get in your car and you drive, your dashboard and your stick shift is screen printed and formed. So printing isn't just books and magazines, newspapers, and packaging, but when you think about it, even wall coverings, floor coverings, signs, road signs. Print affects you, and you don't even realize it. You just consume it. You know, we don't have name badges. Things get printed. It's a communication mechanism. It's inexpensive to distribute, easy to spread awareness. We can limit it by geographical areas. In fact, that's a hot topic in terms of marketing, where you can do a lot more target marketing for audiences, and it serves as a way for people to sell products. It serves as a way for us to communicate. It serves as a way to educate people. And even though we live in a digital world, the studies have shown that printed books, literacy rates are much greater having printed books in front of you instead of digital. And I'm surprised to see that schools are moving towards digital, but that's a whole different argument, because print, by far, people retain information a lot better. So anyhow, that's kind of the world of print. It's much larger. It's huge. And lastly, from a sustainability perspective, we like to say it doesn't need a power source. You don't have to print. You don't have to plug in your book in order to read it, right? You can just open it up, and as long as you have light, you can read it. So, why print? Of course, obviously, there's several main drivers to print. Brand support and awareness, primary message and product center, allows for business growth. Print is integral to a lot of businesses. Print is critical in terms of growth, understanding how do people get word out about new products and new activities, and so print is integrated into the business community, and print serves as many important roles when it comes to looking at why someone would want to print materials. And so that's kind of our basic understanding of print. I also thought it would be important for us to delve a bit into color, right? Now, Doug understood I'm from Pittsburgh, so I just said that word K-E-L-L-E-R, not C-O-L-O-R. That's how we pronounce it in Pittsburgh, so you may pick up on a few things from my area. But color serves a very important role in marketing. And I think as we talk about, hey, well, why don't we just change this color for that color, right? We could just simply do that. Well, not necessarily. Color is in the world that, from a printer's perspective, they live in a world of color. And color is driven primarily because of our customers, right? The printer is a manufacturer, and if you think about it, they're manufacturing a custom product, because every job that they produce is really a custom product, and it has to be manufactured to the specifications in which the customer wants. Well, color is a driving force in a lot of what people want with their print. Why? Well, because, first of all, color has different psychological effects. And I thought this was fascinating. Actually, I put the source for the article. If you really want to delve into it, it just is just the tip of the iceberg. But colors elucidate certain reactions. Red is exciting, it's action-oriented, passionate, energetic, and encourages appetite. That's why you see with a lot of fast food places, you see a lot of red in their logos. You see a lot of red in their marketing. You see a lot of red in their advertising, because it encourages appetite. Purple I thought was interesting because it's associated with nobility, power, luxury. So color elucidates a lot of different responses, emotional responses, and guess what, guys? We utilize those to get you to buy things, right? We collectively, anybody that's selling a product, wants to utilize and enhance and use those colors for sending messages both directly and indirectly. So, interesting enough, 93% of buyers focus on the visual appearance of a product. 84.7 claim color is a primary draw for a product. So if you think about it, you're producing a product and you want to stand out in the marketplace, because rarely does anybody have a monopoly on any particular product. You have competitors, and you have to demonstrate that your product's better. 84.7 claim color is a primary draw. So where do you think you're going to spend a lot of time focusing on what my product's going to look like, right? I have to distinguish that product in the marketplace. So color is going to be a very important distinguishing mark. 80% believe color is responsible for brand recognition. So if you're a brand and you're trying to make a market and you're trying to produce a product, recognition for color is important. If you say, okay, well, we think of, and I was thinking a great example would be Starbucks, which is buried in the green. But Starbucks is a pretty well-known coffee purveyor, right? So Starbucks' logo is what? It's a green mermaid. So think about this. Do you think Starbucks just randomly picked green and randomly picked a mermaid for their logo? But when you go to any Starbucks, whether it's here or whether it's across the world, you buy a cup of Starbucks coffee, you're getting a cup of coffee that has a green mermaid logo on it. And that green is a very specific green. Well, those cups aren't getting printed in one place, right? They're getting printed across the world. So there you have issues of color, reproducibility, and all the quality that goes into that. But understand, Starbucks' image is the green mermaid. And you can pick any one of these companies across the board, and you can say each one of these, their brand is recognized by color. In a lot of instances, if you just throw out a color, you could probably think of a bunch of brands that come to mind. Why? Because you're associating that brand with a color. You're associating the product with that brand and with that color. You're associating, Coca-Cola Red, for example, right? So when you look at it and you look at the stuff sitting in front of you right now, it's an important aspect. So the point is, it's not an easy thing to say, oh, we're just going to change your color because we're going to change your color. Color is critically important in terms of where businesses spend a lot of time, effort, and focusing on that so that you, as a consumer, can make that connection with their brand and their products. Okay, the role of ink and print. Well, it may be obvious, but ink is used to impart text and images on substrates. Substrates range from us. We print on paper, we print on plastics, we print on metals, we print on ceramics, we print on polymers. We print on just about everything. In fact, in some cases, not really commercial printing, but they actually print objects now with 3D printing, right? So that's not necessarily what our members do, but you think about printing. Now, the key thing is that ink provides a decorative and a functional layer to your product. There's a wide variety of applications that come from ink and the benefits that ink provide. I think what's most important to understand when it comes to printing is that in the world of printers, we talk about CMYK. There's another acronym for you. And the reason why we talk about CMYK are those are the four basic process colors. If you have an image in front of you, a photograph, a brochure, and that image, it looks like as I said, it looks like a photograph, magazine cover. It looks like a picture of a car. Well, understand that printing, we cannot print a continuous tone image. A photograph is a continuous tone image. In order to print that image on that substrate, that image has to be broken down into four primary colors, black, cyan, magenta, and yellow. And what happens is then those, we basically trick your eye into thinking it's a continuous tone image because in the world of printing, we print dots. We print dots of ink. So when they print an image, a four-color image, there's dots of ink that they lay down at discrete angles to each other by those four process colors. And with those four process colors, you can reproduce many colors in the spectrum by doing four-color process work. So you hear the word four-color process work. Then, in addition, we have what are called spot colors. Those are commonly referred to as Pantone matching systems. And right now, there's over 2,100 separate PMS colors. The PMS book that you'll see is about this thick. So the best analogy I can say is if you're looking for paint, you go to Home Depot, you look at all the paint chips that are out there, think of that as one big PMS, right? So, for example, the McDonald's yellow is a very specific PMS. The red that's in Coca-Cola is a very specific PMS. It isn't just a processing. So it's a very specific color that is made from inks that have various pigments that go into making up the color, and George is going to touch upon that. So printed pieces can be can be a one-color piece. You can have 1 to 4 colors. You can include one or more PMS. Here's a great example, which I think makes really brought it home to me. As I was in a facility and they were printing Green Giant vegetable can labels. It was an 8-color press. So what does that mean? There was 8 separate units. There was 4 colors for the 4 primary process colors, and there were 4 separate PMS shades being printed on a label for green beans, for Green Giant. So when you think about it, wow, that's a lot of ink. But then you think about a Green Giant green bean label. It's on a grocery shelf, and then they want to distinguish themselves from the other competitors because they want you to buy their particular brand of vegetables. So they put 8 different colors into that label that goes on a can that you open up, empty the contents, and toss in the recycling bin. So it's a lot of work that goes into something that ultimately gets recycled. But the thing is, you bought that product, right? So 8 different colors go into that particular can. Again, ink is ordered. Now, this is important. From the printer's perspective, as I said, we work in a world of color, right? So ink is ordered by color. So we don't delve into pigment specifics. Printers, you could talk to a printer and ask them about what pigment is in that particular color of ink, and they go, I don't know, it's a yellow, this, or that. So that from a printer's perspective, they don't understand pigments. That's not their job. That's not their role because their customer is specifying color. In turn, what happens is the printer goes back to the ink manufacturer and says, my customer wants X, Y, and Z. I need an ink that matches what my customer wants because I'm going to print what my customer wants. That's my job. I'm producing that product. So ink is usually formulated to a specific color. It's also ordered based on performance specifications. It could be drying time. It could be coating compatibility. For example, a lot of times we'll put an overprint coat on a printed product to protect the surface of that. So again, you have to have compatibility because you don't want your coating peeling off your ink. Scuff resistance, light fastness, there's a whole variety of issues in terms of performance characteristics. And most importantly, ink is formulated to meet a very specific application technology, which we're going to get into. And probably the most important part of understanding that is that they're not interchangeable. And you'll see what I mean when I get into the application technologies, right? So those are not necessarily interchangeable. So what you can do perhaps with one ink system, you can't do universally across the board with other ink systems because of the limitations of how that stuff gets put on the substrate. So when we look at our options for printing, we have conventional printing and digital. Digital technologies are literally becoming, in some areas of our industry, the dominant process. In other industries, conventional still remains dominant. But we're in a situation in the printing industry where we're in a big transition right now. And we are transitioning away from analog technologies into digital technologies because the digital technologies are getting better and they're becoming more cost effective. And so we're seeing more of our members moving into digital or adding digital applications instead of conventional. So with that being said, on the column under conventional, we have categories of breakout: relief process, letterpress, and flexography. Basically, that means the image area is raised relative to the non-image area. Intaglio, which is basically how a lot of our money is made, kind of as a gravure process where the image is engraved into a cylinder. It's recessed. Serigraphic, which is screen printing, and most people, if they took a high school printing class, may be experienced or have seen screen printing. It's basically a screen where you're pushing the ink through the screen. And planographic, which is probably the most common process from a commercial printing perspective, is offset lithography. And then on the digital side, we have inkjet, we have xerography, dry toner. That's the one most people think, which is basically, a Xerox machine that's been around for quite some time. But that technology is growing because it's gotten a lot better. They have a lot more performance capabilities and a lot more expanded durabilities. There's liquid electrophotography, which is an indigo, which is kind of a digital offset press. There's dye sublimation, and then the new technology coming on the market is nanography, which is basically a water-based version of the indigo press. Advantages and disadvantages. Conventional, large quantities can be printed cost-effectively. Your unit cost goes down as the quantity goes up, right? So what drives some of these choices, obviously, is the economics of printing. I want to print 100,000 copies of something. I need to go to a technology that's going to produce that in the most cost-effective way. A large variety of paper types and other substrates, special custom inks can be used. We can get great color matching with conventional technology, highest possible print quality with greater detail and color fidelity. Again, important to our customer. Advantages for digital, setup costs are much lower for short runs. You print only the amount that you need. You can have minimum quantities as low as 1. Like, for example, if you order a book from Amazon, this is interesting. People think there's these large warehouses of all these books sitting around, which used to be the old model. The new model is that there's actually companies that will print one version of that book for you. So if you want to order a book, now if it's like a Harry Potter, obviously there's going to be warehouses of those if it's a large, best-selling. But if it's a not best-selling book, but you want to order it, there's actually a company where you place that order. The order gets sent to the company prints it, boxes it, ships it, it goes out to you the next day. And so that's what digital technology allows you to do. You don't have to have warehouses of books, but I have to have warehouses of databases with all the data so I can download that, put that on my press and get it off. So a variable data capability. In other words, I can say you particularly like blue sweaters, right? And then you buy from Land's End. Well, Land's End might send you a catalog that says, hey, we have blue sweaters on sale. And it's your name, right? So you can customize that print using a digital technology. And then improved technology has made quality acceptable for more uses, and that's where we're seeing the growth. So how do we select print technology? Again, certain products can be produced with specific technologies. Print quality is very important. such as color matching. Run length is also a factor. Cost is a huge factor. And then customization with spot colors and special effects. So in terms of what's happening in the industry, I thought this graph was pretty interesting, is that in terms of just 2013, which was just seems like a few years ago, the installation of digital presses was around 26%. In conventional was 74, and now we've seen a growth of color digital doing 52 versus 48 on conventional. So we're seeing a shift in terms of the way things are getting printed. So I was asked to look at print technology for packaging and newspapers. So with kind of that background, when we look at packaging and newspapers that are printed, newspapers are fairly easy because it's usually offset lithographic printing. There's some flexographic printing, but primarily it's offset lithographic printing. Packaging is a different story. Packaging is actually a huge growth area. And you guys probably don't realize that because you may not be in a packaging market, but in our world, that's a huge growth area. Packaging is exploding because more people are buying things. Think about it. Most people buy something, at least off Amazon, maybe once periodic session. If it's my wife, she's buying it more frequently. I buy it less frequently. We have neighbors that get packages delivered every day from Amazon. So think about packaging, right? What has to get put in something, and whatever you're buying has to be put in something. So packaging is a huge area of growth. So conventionally, we have flexo, gravure, and offset. By far of those, I would say offset's the most common. But if you have, somebody had mentioned earlier about cereal boxes, General Mills cereal boxes, you know how many millions of cereal boxes that get printed, through the course of a year? That's going to be through a gravure process because it's more expensive to set up, but the unit cost goes down as the run length goes longer. And then we're seeing, on the digital side, we're seeing inkjet, xerography, and liquid electrophotography making inroads constantly into the packaging market. So it is interesting where the dynamics are going. So I've been mentioning some processes. I thought it would be good to share with you how those work, and there will be a quiz at the end, so pay attention. So the relief process we're talking about is flexography. The way that you would think about flexography, and I have the things that are printed there, think of it as a raised image area with a rubber plate. So it's a very rubber polymer type plate. It's very soft, and it's going to be printing the image directly onto the substrate. So there are ways that this image gets applied to the substrate. So that's basically the way flexo works. Also, what you want to think about with flexo ink is that the inks are very fluid. What we mean by that is they basically pour like water. So it's going to be very fluid ink that's applied through this process through a raised surface area, right? And then there's other parts of the system, but that's the key aspects of flexo. Rotogravure, as I mentioned, that's basically an engraved process. That means there's a cylinder that gets engraved with the image. So now my image area is recessed relative to the non-image area. I have to use a very liquid or fluid ink system that gets applied to the surface of that cylinder. The substrate passes over that. The image is directly transferred to the substrate. Usually it's paper, but it could also be, like for example, wallpaper. And wrapping paper. We're coming into the holiday season. Wrapping paper is printed by gravure because think about the volume of wrapping paper that's printed through the course of the amount of wrapping paper, it's done via gravure. A lot of wallpapers, which is starting to make a comeback, but they don't call it wallpaper. They call it wall coverings or something more fancier than wallpaper. But to me, it's wallpaper. So anyhow, basically with gravure, we have also with flexo and with gravure, we have water-based ink systems and we have solvent-based ink systems, depending upon the substrate that you're printing. If you have a plastic, like a flexible film, we all have potato chips or your cookie bag, for example, is called a flexible package. Generally, in that case, those are going to be a solvent-based ink system because water doesn't stick very well to plastic, and I need to get that ink to stick to that plastic so I can dry it, right? So typically, those are going to be a solvent-based ink system and not necessarily a water-based ink system, although there are exceptions. Planographic, as we mentioned, offset lithography, basically, this works on the premise that oil and water don't mix. So you have an image that's on the plate that's treated, the image area is treated to be oil receptive, the non-image area is treated to be water receptive. And this is an interesting process because offset lithography deviates from other processes because the image is being indirectly placed on the substrate. So the plate itself accepts the inked image, it transfers it to a rubber-covered cylinder called a blanket, which then transfers that transfers that image from the blanket to the substrate. The ink for offset lithography is thick. It's like peanut butter. So you can take a can of litho ink, literally take the top off, turn it upside down, and rarely would you actually see it come out of the can. So when the press operators put ink on an offset press, they actually have to scoop it like peanut butter and place it into the press. So there's a distinction and a difference in terms of the ink. And those are important in terms of how they apply. Now, this is interesting. The guy who invented this process is now like a gajillionaire. But he said, well, why don't we come up with a I don't know his thought process, but my thought process, if I were to interject it, his thought was, why don't we come up with a hybrid between offset lithography and xerography? And basically invented the indigo system. The indigo system works like a Xerox machine where you have a cylinder that gets charged with the image. There's no plate, right? So it's all done electronically, and then the ink is attracted to that image as you have with a Xerox or dry toner, and then that's transferred to the substrate. So in an indigo system, you have a blanket, so it's an offset image, but the ink is very similar to an offset ink. It starts out very thick and very pasty, and it gets diluted when it gets applied. And this technology, by the way, has taken off. It's incredible. There's a lot of products produced via indigo because your setup costs, I don't have to make a plate. I now have a digital image that comes from my computer. I can get it to image on my press, and then I can print it. And I can change my image on every turn of the cylinder. See, that's the advantage of a digital technology versus analog. Analog, I got to make a plate. If I want to change my image, I got to change my plate. That means I got to stop the press. I have a lot of setup time set up with that. With a digital technology, I don't have to change plates. I can just change the image electronically, and then I get a different product that comes out. Xerography, which we're all pretty familiar with, which is a dry toner, again, system where you basically charge a cylinder with the image. The dry toner is attracted to it. It gets applied to the substrate, and it gets fused to the substrate. Inkjet is where there's a lot of growth going on, and the best way I can describe inkjet is to think about your desktop printer, but think about it on steroids. And when I say think about it on steroids, some of the largest inkjet presses I've seen are about the length of this entire room. Now, not the width, but they're about the length of this entire room. So think about an inkjet printer on your desktop is about the length of this room because that's how they're producing a lot of books right now through inkjet. And an inkjet is just literally exploding in terms of applications. So we're seeing with folding paper box, labels, commercial printing, banners. In my segment of the industry, you'd see a lot of, you don't see it here today in the convention center, but a lot of times you go to conventions, you'll see a lot of banners. Or you'll see vehicle wraps. That's another thing. When you're riding down the highway and you see a truck that has a company logo on it, that's a vehicle wrap typically. Those are screen printed and applied to the vehicle. So I said printing affects you don't even think about it. So fascinating industry. So let's talk about sustainability with print and packaging. Well, traditionally, or I would say historically, the focus that we've been, I have to ignore you, all right? So I'm not paying attention. But I guess still 5 minutes, so I'm actually in good shape because I have 2 slides left. So traditionally, the focus on sustainability with printing was primarily substrate driven. And still to this day, I would say it's still substrate driven. What we mean by that is that a lot of folks, primarily our customers, think of print and they say, well, I need a product that's recyclable. You know, from a paper-based perspective, and of course that's what we want is recycled paper. They think of it as, okay, it's a single attribute focus, recyclability, right? That's what they view in terms of looking at the product. You may see some folks who focus on, from a paper perspective, the source of the fiber. You know, is it an FSC or SFI certified fiber? And so to them, they think, well, man, that's sustainability because I have a fiber source and it's recyclable, right? As we know, there's a lot more that goes into that, but traditionally that's what it is. We occasionally get some focus on inks. In the term you hear soy ink, that's the one that gets a lot of play, right? And soy ink isn't, we could spend time on that, but it's an interesting concept. But it has parts of the ink, and this is primarily a litho ink, where the petroleum oil has been replaced with a soy or other vegetable-based oil. And George can probably obviously add to this. You know, heavy metals were an issue in terms of a focus historically. And of course, we got rid of lead chromate yellow, and now we have diarylid yellow. And look where we are, a room full of people worried about diarylid yellow. So what's the choice? Go back to lead chrome. Anyhow, and then recyclability, as I said, coatings, also recyclability, adhesives. Can my product be recycled? And then what we've seen is an emerging, focus on other aspects and the process. So part of what we like to talk about is it's not just the product, it's also how the product's manufactured. And that's where we focus on what's called the Sustainable Green Printing Partnership. I'll do a quick commercial. Basically, it's a certification program for printing operations that want to meet criteria of sustainability, and it covers everything from A to Z. It looks at transportation, manufacturing, warehousing, grounds and maintenance. It looks at all the materials they're using. It's not just paper, and it's not just ink, all right? And it sets standards that companies have to meet with respect to sustainability, requires them to do a continuous improvement project. They pick it. We don't pick it. They pick it. They can focus on VOC emission reduction, energy efficiency, solid waste reduction, et cetera. And if they meet the criteria, they get certified as a sustainable green printing partner, which means that they're deemed to be a sustainable manufacturing operation based on the criteria. What we've seen also, emerging issues, the impact of the China Blue Sky program, which I think Doug touched upon. That's caused major ramifications throughout our industry because obviously we're manufacturing these products for our customers. And what do? Well, part of what we've seen, and you have probably experienced it here as well as everywhere else, is this move away from plastics, right? There's this big issue and big concern regarding plastics and what do we do with it. A lot of focus on single-use plastics, and I struggle with what is a single-use plastic, right? Straws have become the tip of the spear, so to speak. But what's a single-use plastic? When you look at plastics, man, there's a lot of single uses of plastic. Your potato chip bag, your cookie bag. I mean, I'm not going to reuse that. That's a single-use plastic. So, what is a single-use plastic? I don't think it's clearly defined. What we have seen, though, is we've seen movement towards, new polymers and new recycling processes. And if you follow that issue, there's a lot of activity going on in that area. Extended producer responsibility. That's an issue that's come up and continues to be discussed, and we're engaged in that process because again, I understand the basis of extended producer responsibility, but the challenge, I think, quite frankly, is infrastructure. To take that material to recycle it, because if you look at the European Union, which has had extended producer responsibility for quite some time, they have really clean bales of stuff they can't send anywhere. All right? So as you think about extended producer responsibility, it's an infrastructure. It's a demand issue. It's not a necessary collection. And I'm almost done. So, and then mandatory recycled material content, we've seen some movement in that area. And then chemical composition. PFAS in food packaging is actually Washington State has an issue of looking at PFAS in food packaging. BPA in food packaging is also a big issue. And then, of course, California Proposition 65. We've now seen some action against packaging for Prop 65 because there's some chemicals in some of the flexible packaging that weren't warned against. And so there's been some action brought on packaging. So we're seeing more chemical related. Of course, we could add the PCB issue here too as well. So we're starting to see more chemical driven types of discussions on end products. And so, where it goes, it's very interesting. It's hard to predict where I think this is going to end up in terms of the industry, but what I can say definitely is that our industry is actively engaged in this process. We're cognizant of it, and we're working with our supply chain. We have to work with our upstream and downstream suppliers. And so George and I spend a lot of time talking with each other about ink issues, but we also have substrate issues as well. So I think that brings me to the end, because if not, I'm going to get it really bad. But so there's my contact info, and I guess I can take some questions if people have questions.
Yeah, we have about a couple minutes for questions. And also I want to, one sec, Doug, I just want to apologize. We're supposed to have coffee 24/7 here. There's no coffee now. I know a lot of you are doing that like post-lunch, it's coming. So just hold on, Doug.
So, Gary, you didn't get to the very end where you mentioned PCBs. So obviously there's somewhat of an awareness of this issue. Can you speak to what that awareness is?
From a printer's perspective, zero.
Okay, that's what I thought.
It's not, there really isn't, because it's not an issue that crosses the radar screen. Quite frankly, it's because, if it's not driven by a customer, it's not an issue. In other words, the printers don't live in a world of pigments. The printers live in color. And the printer is basically printing is actually manufacturing. But we're really a custom manufacturer, and we're going to respond to the market signals that come from the customer base. If the customer base says, I wanted this, that, or that, then the printer is going to produce that or do the best job that it can to produce and satisfy the customer. The printer doesn't just create boxes and hope somebody buys them. Like other industries, they don't make products and hope people come and buy them. They're responding to their customer's order for a particular product. I mean, maybe the closest you get are publishers, right?
So we have a couple other questions, and I do want to. One thing that you brought up is, I think you said, we don't really have any packaging folks in the room, but we actually do, right? Songren is here. You can raise your hand. So Songren Packaging, is that the formal name of the company, is a local packaging company, and we really are trying to get supply chain all the way down to a 10. So just thought I'd point that out.
Excellent.
I thought the point about the human element of developing brand loyalty was really interesting, and the packaging and the printing is really an indicator of the product that people want. And I'm wondering if any brands that, now it can be important for different corporations or brands to have sort of an environmental perspective, and people vote with their dollar a lot. I wonder if there's been any effort that you're aware of, because now social media, every brand, many of them have a social media page. I'm curious if there's been any effort by any brands or corporations to sort of feel out the public as to whether more sustainable, whatever it is, printing inks or packaging would be something that wouldn't hurt their brand's loyalty.
Yeah. I don't have a clue on that one. I mean, that's a hard question, because look at every individual brand that's out there and the decisions that go into making what they decide to do with respect to a product line or a campaign or a package or printed matter. I'm not sure I can answer that question.
Okay, I'm going to take two more questions, then we're going to have to move on.
Yeah.
You mentioned a lot of different processes for printing, and I know very little about ink, but I know that pigment is only one small part of the ink, right? And we think that the PCBs are maybe associated with the pigment part. So do any of these processes help you reduce the need for the pigment? You talked about different types of ink. Some are more fluid than others.
No, I mean, you have to have pigment in all your ink systems if you're going to part color. George will be talking about that, but you have to have pigments in all those. The application method of application will dictate the formulation of the ink and the characteristics. In other words, that's why I was trying to stress is that an offset, like you can't take an offset litho ink and put it on a flexo press. It's not going to print. You can't take an inkjet ink and put that on a flexo press. Even though they're similar in nature, they're a liquid ink system. They're designed for different applications. That application method is very specific in that the ink has to be specific to that application method, if that makes sense. And then the choice of application method is going to be driven by cost, run length, quality, and all the other attributes that go into it in terms of deciding because somebody's asking a question, well, why is one package printed this process versus that one? And those are the factors that go into it in terms of determining what's the process that I use.
I have a quick question about your work with the Sustainable Green Printing Partnership, and I'm looking at the agenda this afternoon and into tomorrow, and we're going to start to discuss potential solutions or innovations that we can explore in this realm. And I'm curious if you can speak to an example or two, either from the Sustainable Green Printing Partnership work or some of the other sustainability measures that you had mentioned earlier in your presentation, and highlight some success
successes there or processes that you thought worked really well? Who needed to be at the table? How did you engage with industry and other interested parties? How did you engage along the supply chain to implement some of these sustainability measures?
Yeah, the SGP program requires the printing operation to engage in their supply chain and their customers as part of a conversation. And so in order to be certified, the printer has to go to their customer and talk about alternatives and options available to them. And then likewise, they have to go out to the supply chain and seek out those alternatives to make them available to their customer. Now, the SGP program doesn't force that decision because obviously the printer is in a situation where they can't say to their customer, oh, by the way, it can only print, I know you want that red, but you know what, we want to give you this red over here. That's not going to happen, right? So the printer is not going to dictate to their customer the product that's going to get produced. They can make suggestions and open a conversation. And to be certified, they have to have those conversations. What they have to do internally, for example, the continuous improvement project, there's facilities that said, I'm going to go zero waste. So right now we have 3 facilities that achieve zero waste. And you think about a manufacturing operation that throws nothing away, that's a phenomenal accomplishment that they get to. Energy reduction is a big one, VOC emission reduction. So where the things that printers can easily control, they're reducing VOCs by looking at the solvents they're using, looking at management practices, things like that. So there's ways that they can drive sustainability on their manufacturing end of it. So it's a manufacturing certification. It's not necessarily a product certification, if that makes sense. There's product certifications out there. This is a manufacturing certification that has a product element associated with it.
Okay, thank you. Thanks, Gary. We're gonna need to go to the next speaker. I apologize. So feel free to grab Gary.
Yeah, I'll be around.
So, George, you're up. Yeah. So we just had a presentation on kind of an overview of the printing industry. Now we're going to go the next step down. We're going to go into printing inks. And George Fuchs of the National Association of Printing Ink Manufacturers is going to give that presentation. Then we're going to take an even deeper dive next after that and have a presentation on the pigments that are part of those inks. George is the Director of Regulatory Affairs and Technology for the National Association of Printing Ink Manufacturers, and he's worked in the printing ink industry for over 25 years. Welcome.
Yeah, thank you very much, and thank you for the opportunity to speak to you a little bit about printing ink manufacturing. It was an interesting question, Lisa, about pigment usage in ink systems, and not one that's easy to answer. One of the things you've got to understand about the ink industry and other parts of the chemical industry as well is that ink formulations, and I have a bunch of them to kind of show here, is intellectual property. So, and it's not that this material is, this information is not disclosed, but it's generally done under a non-disclosure agreement. So it's a difficult question to answer. Do some ink systems use lower concentration of pigments? In some cases, maybe yes. I've heard that some of the digital ink formulations have a lower concentration of pigments than some of the conventional ink formulations, and that may or may not be true. I mean, that's kind of a rumor that I've heard, and I'm not exactly certain that may be the case. But in any event, I'm going to talk a little bit. It's difficult, a little overlap between my presentation and Gary's. It's tough to talk about printing without talking about ink, but I'm going to talk a little bit about exactly what printing ink is and how it's formulated. Just a little bit about NAPM, National Association of Printing Ink Manufacturers. It's probably, if not the oldest, it's right up there at the top of all the American trade associations. And our membership in the association represents probably somewhere between 85 and 90% of the domestic production capacity in the U.S. And I got a little truncated there, but our membership represents both ink manufacturers and suppliers to the ink industry, so the resins, vehicles, pigments, those types of things are members of our association as well. And we've had a number of research task forces over the years that I won't go into here, but they're all listed on our website. We do have a research institute, NPIRI, National Printing Ink Research Institute, which has kind of run all these task forces that through the 60s, 70s, 80s, and 90s looked at addressing print-related problems, color matching, and picking, and other types of things that were part of the printing ink industry. One thing to understand about printing ink manufacturing is that we are part of the chemical manufacturing sector, okay? So we are regulated the same way as any chemical manufacturer is, and that's under OSHA and RECRA, some of the acronyms we've heard previously today, Consumer Product Safety Act, Clean Air Act, Clean Water Act, Food, Drug, and Cosmetics Act. I should have put TSCA up there as well, but we're kind of peripherally covered there. I will say something, because it came up before, about FDA and PCBs, and the statement was correct. FDA does not really regulate PCBs per se. FDA, when you think about it with respect to printing ink or packaging, regulates two things: food additives, both direct and indirect. Okay, but one kind of a point of reference in terms of the way EPA thinks about chemicals on food packaging. There's a rule within the FDA regulations called threshold regulation. Okay, and essentially what that says, from an ink manufacturer's perspective, or from a printer who's printing a package, is that if you have migration from the outside of your package into the food above 0.5 parts per billion, that's the limit that they've set, then you are regulated as a food additive or an indirect food additive, depending on how it got there. But it's not a straight concentration, the 0.5 ppb. Essentially, it's a dietary concentration. So if the typical user of your product is exposed in their diet at 0.5 parts per billion or greater, you would be regulated under FDA. If it's, or less, or greater rather. If it's less than that, then you're kind of outside of the scope of the things that FDA regulates. Just kind of a point of reference with respect to how that government agency looks at things. This is basically what the supply chain looks like. We buy our resins, vehicles, pigments, solvents, additives from a raw material supplier. And one thing I'll mention about raw material suppliers of all these base chemicals is that a lot of these materials are not manufactured here in the U.S. Okay, a lot of it in the last 25, 30 years has moved offshore. So there's not a great degree of control in some instances over what we have in terms of the raw materials that we're getting from China or Asia or other places around the globe. But anyway, that's kind of what the supply chain looks like. Raw material supplier to ink manufacturer to the printer converter. Typically, converters is kind of a term of art. It means converting substrate into a package. Call them converters. Then it goes to the brand or CPC or CPG, Consumer Products Company, and then ultimately to the consumer. So that's kind of the world that we live in. Another point about ink manufacturing from a chemical manufacturing perspective, we are a mixing and blending operation. In other words, we're mixing A and B together, and you still have A and B at the end of the day, as opposed to running a chemical reaction where you're mixing A and B together and coming up with a completely new chemical. So that's kind of the way that we are regulated under NAICS codes as well as OSHA and other places. So there's no chemical reactions taking place. In some cases, the use of our product, like a UV ink, there may be a chemical reaction there when it's exposed, but when it's being manufactured, there's no chemical reaction going on there. Just taking a quick look at the size of the industry. In terms of chemical manufacturing, we're pretty tiny. It's a $4 billion pound industry, about a little less than that in terms of dollar values. Europe's a little bigger, of course. They're somewhere in the 5 to 6 billion pound range. Not quite sure what the dollar value is. And globally, it's probably about a 14 billion pound industry. So as chemical manufacturing goes, that's pretty infinitesimal. It's a pretty small group. And almost all ink that's used here in the U.S. is made here in the U.S. Now, the raw materials may come from somewhere else, but the ink that's manufactured, the ink that is used here, by and large, is made here in the U.S. And that's primarily because it's a relatively inexpensive product, and it doesn't make a lot of sense to manufacture it elsewhere and ship it here into the U.S. So most of the ink that's used here in the U.S. is made here in the U.S. I did put the kind of the HCS U.S. codes. Those are our tariff codes, and I show here what the actual import and export values are of printing ink. And this presentation will be available. There's a lot of detail in here, but I'll try to get through relatively quickly in terms of the industry. There are roughly 200 firms, printing ink manufacturing firms in the U.S. A lot of these, there are 5 or 6 very large ink manufacturers. Sun, Flint, Ionix, Sigberg are probably the larger ones, and there's an awful lot of very small companies that might be in the $5 million to $10 million range that are making specialty inks, metallics, fluorescents, electronic ink, those types of things. So it's a little bit of a misleading statistic. There are 200 companies, but the majority of the ink is produced by a much smaller number than that. And I may disagree a little bit with Gary in terms of of how the market breaks down in terms of value of shipment. This is ink rather than printing, okay? But in terms of value of shipments, we call digital printing non-impact printing. You can see letterpress is a pretty small fraction. Flexo is a fairly significant portion. Gary talked about gravure, and then of course there's offset. Well, we broadly break down printing in, and by the way, printing is about a $200 billion industry here in the U.S., much larger. And so all the printing firms and the employees overall is about a $200 billion industry here in the U.S. So compared to ink manufacturing, it's much, much larger than we are. But you can see the different print processes there and the dollar value of shipments. In terms of the market composition, you can see the two largest segments are flexo and litho. And so that's kind of where we break the market down between packaging and commercial. Okay, so commercial printing is typically magazines, newspapers, annual reports, those types of things. And then packaging is just what you would imagine it is. It's any type of packaging. It can be food packaging or product packaging or those types of things. But there's a lot of crossover. A lot of packaging is done flexo, but an awful lot of it is done offset as well. And the same is true with respect to commercial printing, newspapers, magazines, annual reports. Okay.
By volume or by value?
This is by volume. By volume. Now, the other point I'll make about this, and this might not be all that intuitive, and we've bumped into this a lot of times in the past, in terms of deriving exactly how large a market here is in the U.S., you might think that information is pretty readily available. It's really not. So trying to get this kind of information on a specific market is not as easy as you may think. The U.S. Bureau of Census used to put out numbers on the size of the market here in the U.S., especially with respect to printing ink. But with an industry the size of ours, they started running into data quality issues that we just didn't have enough volume for them to meet their data quality requirements. So trying to get specific numbers, for example, exactly how much flexo ink is made or how much offset ink is made, is kind of a difficult number to come by. And even when I talk to people in the large ink companies, and their salespeople, it's not that easy to get those numbers. We've done a lot of surveys over the years, and I think I have a pretty good idea about how it breaks out, but it's not as easily derived as you may think. Let me just say, one thing about digital printing or non-impact printing, I have it here is about 8% of the overall market. I think that's relatively close. What we're seeing with probably the biggest single change we're seeing with digital printing is kind of hybrid presses. So you may have an offset press with a digital print head at the end. One of the things that conventional printing does a lot better than digital printing is speed and cost. Okay, and so the ability to move paper, either sheets or web, through an offset press is really fast. And moving that type through a wide format digital press doesn't happen near as fast as it does with an offset press. So one of the things we see is people putting a digital print head at the end of the press, right? So you could customize each sheet coming off or the web coming off, but not have the kinds of paper handling problem that digital has an issue with. We've talked a little bit about inks versus dyes. Dyes, of course, are fully solubilized. Inks are dispersions. We call them dispersions. Some people may think of it as kind of an emulsion, but it's really a dispersion. And the technology that's involved in ink manufacturing are that is probably the single greatest intellectual property, and I'll show you a little bit of the unit operations for manufacturing going forward, is getting a very uniform dispersion of the pigment particles in your ink. You can see the one on the right, I guess on your left is an ideal dispersion, and the one on the right is pretty poor. So you would not have a great color match with a dispersion like that. Gary talked about color. Okay? Color is a very, very critical part of the ink manufacturing business, and almost all color is what we call trichromatic color. Okay, so it's produced through three primary colors, and black is going to be the index, but that's generally how it's done. CMYK, that's how it's produced, and in each one of these specific colors has a very specific formula to produce that particular shade, green shade red, or whatever it is. It's a very specific formula that was all based, this is kind of cutting to the chaser, that has always been based on available pigments at the time. So the diarylids and the phthalocyanines have all been very specifically formulated, and all these colors have a very specific formula to match that particular shade. Okay, so a little more about that later. And as you can see, that's kind of a representation of the trichromatic color. That's just a few of the PMS shades of yellow that are available, that are all kind of predicated on various pigments that were available at the time these color swatches were produced. And over there on the right, for any of you who fooled around with Photoshop, you can kind of see exactly how specific those colors are. And essentially I'm not a color scientist, and there's an awful lot of people who've got PhDs in how to do this, but this is basically how it's measured, right? They have a way of numerically indicating, specifying what a particular color is. So when they get a request from a brand to match a particular color, they'll use this type of color specification to numerically indicate what it is. And there you can see an example of, for example, the yellow rose and the red rose is a very specific numeric designation as to how to produce that. And again, this is an example where that would fall on that kind of LAB value in there. It's color management, color science is a very, very technical topic, and in each one of these formulations that produce these particular colors are based on the pigments that are available to produce those colors. So to pull out diarylids and phthalocyanines would essentially mean redoing this entire color book on there. It's a pretty big task, actually, to do that. I'm not saying it can't be done. I'm saying it's a pretty big task, and it's not just the ink manufacturer who would be involved in that task. It's a group effort. And the other thing thing and I kind of neglected to mention, I was kind of talking about foreign-based raw materials. You know, in 2008, the commercial side of the business, newspapers, magazines, annual reports, fell off the edge of the table, about 35%, okay, as we measured it here in the U.S. A lot of people looked at that and said, well, you know what, it's the impact of cyber advertising, and a lot of the brands said, well, you know, we're just going to put all our dollars into advertising on the web. Well, I'm certain that had a very large impact. The other thing I'm fairly certain of was that an awful lot of printing went offshore. And so whether that's being done in China or other Asia or other places around the world, I'm fairly certain there's an awful lot of that being printed offshore and brought back over here. So just another thing to keep in mind when you talk about, well, how do we affect a change here in the way, you know, brands think about color and printers use it and ink manufacturers use it. Color is measured very, very specifically, generally with a spectrophotometer, and I have a couple of examples up here of how it's measured. And trust me, the brands use this all the time. They know exactly what that color is supposed to look like, and they measure it with a spectrophotometer, and it better be within one LAD value of where they want to be. So it is a real science in terms of how color is produced and measured. I put up here, and the pigment guys will talk about this more, but it's not, there's a lot of issues that go into pigment selection for a particular ink. Gary talked a little bit about printing compatibility, you know, whether it was a flexo ink or flexo printing or offset printing. But the ink guys look at it from that perspective as well, what kind of substrate it's going on to, but also the chemical compatibility in the ink system. So whether or not it's a solvent-based ink or a water-based ink or a paste ink, which is essentially an oil-based ink, there's an awful lot of characteristics that are considered when you select a pigment, not just the color, but you know, the ink system, its alkali resistance, temperature resistance, water resistance, weatherability, whether it's going to be outside or inside, its durability, its slip. There's an awful lot of characteristics that go into that pigment selection. And I mentioned before that the commercial side of the business is down, but the packaging side is up, and typical substrates are, we're interested essentially here in paper and paperboard, not so much film and metal, but those, of course, are part of the equation as well. I threw this one in here about 10 or 12 years ago, maybe a little bit longer. EPA, in their Controlled Technology Assessment Group, or Controlled Technologies Guides, looked at flexo printing a while back, and they did a very comprehensive, sophisticated analysis looking at the health hazards and environmental hazards of various printing technologies. And so they looked at water-based flexo printing, solvent-based flexo printing, as well as energy-curable ink systems. And they compared each one of these in terms of its impact on the environment, its performance, as well as human health hazards. So if you haven't seen this, and they did a fairly sophisticated toxicological analysis of each one of these ink systems and included in the book, so it might be something to look at. Gary touched a little bit on some of the environmental health and safety improvements that have been made in inks over the years. Elimination of heavy metal pigments was a big deal and really happened about the time of OSHA and the Resource Conservation and Recovery Act came about. And so today there are essentially no heavy metal-based pigments used in America for printing production. In fact, you know, the diarrhelids really, and the pigment guys may talk about this a little bit, the diarrhelids pretty much were invented to replace the use of some of the heavy metal pigments. So, you know, I hate to say there's no free lunch, but there's always effects, right? When you try to eliminate one problem, sometimes you create another one. But in any event, the water-based inks were developed to reduce VOC emissions under the Clean Air Act, which were regulated. Energy-curable inks, essentially the same reason, very, very, very low VOC emissions. biorenewable content. It's not just soy, but there's a whole raft of vegetable-based products that are used in printing ink, and a lot of them are used in printing inks today. And a lot of the brands look through their supply chain for increased usage of biorenewable materials in their products. Heavy metals, I talked a little bit. I won't spend too much time on this, but they've pretty much been eliminated from all the pigments that are produced, or all the pigments that are used here in the U.S. This basically shows kind of the substrates that are used. We're concerned about the ones here on your left, which are paper board, primarily used in packaging and other types of printing. Here, I've kind of graphically illustrated the drying mechanism for an offset-based ink. Sometimes they dry by evaporation or penetration, and then kind of oxidation and polymerization when they're printed. This chart kind of lays out in a tabular form all of the different types of printing inks and how they're used and what the drying mechanism is, just kind of for reference purpose, what the typical substrates are that you would use these for. I put in a number of example ink formulations. This is an offset ink formulation, which is essentially an oil-based ink, what was referred to previously as a paste ink. I show some of the additives there and basically what the breakdown of the composition is, and you can see what the pigment concentration is in that. Now, these are generic formulations that are available in a reference text on ink. As I said before, this is intellectual property of the ink companies, so it's generally not available. You can't go on their website and see exactly what the components of their ink formulation is. But that's a typical oil-based ink would be used in lithographic printing. So water-based flexo ink, as the name implies, it uses a high content of water, and there limits air emissions, at least VOC emissions. Energy curable inks. The drying mechanism for litho inks would be absorption into the substrate. For flexo ink, it's essentially evaporation. Energy curable inks are dried through the use of either an electron beam or a UV light, and that requires the use of a photoinitiator in there, which can be a dermal sensitizer. So again, there was a shift away from solvent-based inks to energy curable inks in this purpose, but we added a component that might have been a higher health hazard than the other ones that were previously there. Well, one chart I wanted to get to, and I just kind of put the reference text that I used for this. This book is still available. You can buy it on Amazon. It's probably the tome for ink manufacturing that if you're interested in it. But I thought you might be interested to see how much ink is actually on printed substrate. And so the way we look at it, assuming 100% coverage, dried ink would be about 1.3 milligrams per square inch. So that's as applied, and it'd be somewhat less than that after it's dried. So the basic formulation components, pigments, resins, solvents, additives, or what's in the ink system. Let me just quickly show some of the unit operations, though in a typical ink manufacturing location, weighing, mixing, milling. Milling and filtering is a way to disperse the pigment, a solid particle in the ink system, whether it's a paste ink or liquid ink. These are typical vertical toast mixers that are used, or 3-roll mills, which are used to kind of deaerate the ink and also break the pigment down for a nice dispersion. In there, another kind of inline mill process, which is commonly used today. Impacts and challenges. The color standards. Everybody likes to talk about Pantone, but they're not the only one. They're Graco and Fogra and ISO. And there are numerous color standards that are all based, they're very specific about exactly how color is produced, formulated, and measured. And so, generally speaking, a lot of this would have to be, a lot of these standards, absent phthalocyanine pigments and diaryl pigments, many of these color standards would have to be completely revised. And that's kind of a group effort between, the brands, the printers, the ink manufacturers to kind of agree that we're going to revise how we're actually measuring color. So that's kind of all I have to say about it. I'll be around here this afternoon and tomorrow. I'll be happy to talk about any of these issues and how we might approach this problem to solve the issue. But thanks for listening.
So we have time for just a couple questions. Doug, you already had your hand up.
Yeah, the same question from each one of you folks up there. Is this PCB concern, is it on your industry's radar?
Yeah, so one of the challenges that very small industries like the ink manufacturing industry, and I guess as you saw from the numbers I put up there, is we don't have a lot of leverage in terms of kind of turning the ship. Okay, so when I talked to my ink manufacturer members before I came out here and said, well, what are you hearing about PCBs? And almost 2 to 1 said, well, we meet the applicable regulatory standards. In most cases, they're talking about TSCA in that case. So is there anything new that's happening with that, Doug? I didn't hear it from the ink manufacturers from that perspective.
Okay, follow-up to that, too, is I find it interesting that you have historically gone through shifts in your industry, heavy metals, VOCs, it's like what's next? But you have been successful in being able to come up with formulations that have moved away from some of those things. Were those federally driven?
Mostly, I would say that's probably true. The TCLP standards under RCRA probably occasioned the elimination of heavy metals, because when the printer was using an ink, he didn't want to have to dispose of that ink as a hazardous waste under RCRA, which he would have if it had, say, lead, cadmium, chrome, or something like that. But also under OSHA, where you had permissible exposure limits for employees in the workplace. So yeah, I would say a lot of that was federally based standards that drove that. Yeah.
Okay, sorry, I still got it. Yeah. So there's a lot of focus on the pigments as being, the smoking gun here, but you just talked about a whole bunch of different additives that can be in inks. Has there been any view or look at some of those other additives, chlorinated base, perhaps, that might be?
It's interesting. I asked that question, and about chlorine-based materials used in print. Almost none of them. All of the additives and other components, very, very few chlorine-based solvents or vehicles used. Very, very few.
So that perfectly leads into my question. I saw the word siloxanes on one of your slides.
Right.
Because the little I know about siloxanes is that there's 2 types. There's phenyl and there's methyl. Do they use the phenyl siloxanes in any of the inks?
That I don't know, Lisa. I could ask that question. As Oscar Wilde once said, I'm not young enough to know everything, but I will.
Lisa asked me if I knew the answer to that question. I said, no. And so, yeah, all the front row people are asking questions, so I just put the challenge out for the back. Fascinating tour of the ink industry. I found it intriguing then that in the U.S. Market, a relatively small number of players, and the sourcing of those raw materials seem to be the issue. So there might be an analogy, and in fact, a Q-Calorie research consortium that, perhaps a collaborative, research project could be pulled together. But we have experience with brake friction material or brake pads, where we set a goal for reduction of copper within those brake pads. So the manufacturers, OEMs, got together and helped set a reformulation standard around that. And that, in fact, reset sort of a global standard around all those brake pads being produced globally. Now, I don't know if there's a possibility there, but because you are using offshore sourcing, combining sort of a regulatory driver with an industry initiative like that can produce those kinds of results.
Right. Well, thank you for that. The printing business is a global business, and I say that not because we're global, really. Most of our inks are made here, but our customer's customer is global. And so they're paying attention to, I tried to get right before I came out here kind of effluent limitations globally, and the query that the people ran for me just kind of showed me what the threshold limit reportable quantities were, which is not what I wanted. But it'd be an interesting data point to have to see whether there are comparable effluent limitations in Japan and China and other places. So, but sadly, I didn't get that data.
So maybe from a business perspective, with the printing market changing and what you're printing, what you're producing in the printing market, what's the business side of the equation? Are you a profitable market in producing inks? And then, if so, what's your ability to absorb increased costs?
That's a very good question. And trade associations, by law, don't really get into the money side of it. We can't really do that. But what I can tell you from the information we have collected, we're a very low margin business, okay? And I don't think anybody's going to disagree with that. We'd love to be able to get the kind of money that they're getting for inkjet inks in your little cartridges. Pound for pound is probably more expensive than silver, but that certainly is not the case for ink manufacturers. It is a cutthroat business, and it is very, very low margin business. So the ability to absorb costs is pretty minimal on that. Yeah, and what we've seen over time is the printers have been playing one ink manufacturer off against the other, and it's very difficult to get the price increase through on these types of issues. So, yeah.
So you kind of mentioned that trend over time in terms of things becoming more sustainable. So in terms of a brand, if they wanted to have a sustainable ink and have it be PCB free, aren't there sort of boutique shops who might create these PCB inks and then market those? I mean, we've seen that happen with, for example, low VOC. So I'm wondering what you think the feasibility of that is in terms of them, or even just brands developing a PCB free line that may not have that exact correct color, but it would be, but they can market that otherwise.
Right. Well, I'm not saying it couldn't happen. In fact, there are a number of niche producers of inks that I mentioned before. I think it would be a real challenge to produce the exact kind of color, meeting color specifications for the brand. So as I kind of mentioned before, this would have to kind of be a group effort between all the players in the supply chain, because the ink industry, like the printers, are essentially listening to what their customers saying, and the CPG or CPC or the brand is listening to what the public's saying. And so it kind of filters on through. So the answer to your question is yes, but it's a big change and would take all the players involved to kind of agree to make it happen. So.
Thank you.
Okay, thank you so much.
Thanks so much.
All right. Great questions. I hope that you keep these questions and conversations that we're having right now in mind for a little later this afternoon when we have a moderated discussion. So we've got two presenters for our next presentation. So we went from printing to printing inks, and now we have a presentation on the pigment industry, where all of the key questions that haven't been answered, we're hoping are going to be answered. What's really possible, both Dr. Robert Mott and Dr. Mark Vincent, representing PPMA, will be presenting. Both of your bios while we're waiting for the PowerPoint. Robert, you go first?
We're going to tag team.
Okay. So while they're working on the technical difficulties, I will introduce both. Robert Mott has been working in the color business for more than 35 years. He has a BS in chemistry from Michigan Technological University and a PhD in chemistry from the University of Idaho. He's worked in various aspects of the industry, including dye and pigment development, manufacturing, analytical R&D, as well as global regulatory aspects. He currently chairs the Chemical Risk Management Committee with, not sure how you say this acronym, SOCMA, and the Organics Committee within the Color Pigments Manufacturing Association. Now, Mark Vincent I'm going to go ahead and introduce you as well right now, has a bachelor's and a PhD in organic color chemistry from the University of Wales, and has been working in the pigment industry for almost 25 years, again, holding various positions in research and development, regulatory sales, division management, and more recently as the CEO of Dominion Color Corporation in Canada. And a number of people in here have worked with you during that time. He's known for his technical knowledge in pigments, in particular yellow, orange, and red. So we are looking forward to hearing about that. And today he's representing CPMA and its member company. Okay, yeah, and sometimes
I will stand this.
We're trying to make technology work for us here. While he's putting up the slide, is this on? While he's putting up the slide? Go ahead.
Yeah, maybe flip it over.
Oh, okay. Do it the other way. I know the question's coming up about, how many pigments are there? Why do we have new pigments and things like that? If you look it up, there's roughly 155 million chemical substances, inorganic and organic, that have been assigned a CAS number. Of those roughly 155 million chemical substances, there's roughly 1,000 of them that are in the color index identified as dyes or pigments. So you have about 1,000 colored chemical substances that are useful in commerce, that were ever useful in commerce. Now, some of those happen to be based upon things like benzidine, toluidine, the methyl analog of dichlorobenzidine. They were used in dye stuffs primarily, and they're no longer being used. They're no longer being manufactured. The reason is dyes, we've said this before, but dyes are soluble. Because they're soluble, they enter cells. Because they enter cells, they get metabolized. Therefore, they quit making those products because there was no market for it, and it was dangerous for the workers. So they quit making those, those diaryl dyes that were based upon phenetidine. Looks like we're having a hard time with this.
Yeah, I can only get it up on the one.
All right. Anyway, so that gives you an idea. Of the 1,000, there's roughly about 300 chemical substances that have been in commerce over the last 25 years that are organic pigments. That's of any market, value in range at all. We've done this in connection with some activities that we'll be mentioning later on here. As a practical matter, there was no color industry in North America until World War I. With the advent of World War I, it became at a certain point inconvenient for the German chemical companies to be delivering dyes and pigments to the United States by submarine at the point that we became at war with the Germans. The Color Pigments Manufacturers Association was founded as the Dry Color Pigments Manufacturing Association in 1925. We promote our products, as seen, meeting all regulatory standards. We engage with policymakers, NGOs, groups like this, regulatory people all over the world, actually, in determining, how is it that we can better educate people in what it is that our products do and how they work. We provide a membership form. One of the things that sometimes is forgotten is that not all the color that enters North America comes in. Not all of the product that comes into North America comes in as a dry powder. A lot of it comes in already printed, already in the form of an ink or a paint or a plastics. All of the product that comes in as a pigment meets the same regulatory requirements. There's no such thing as the fact.
Yeah, the phone is right there next to them. On the webinar, they can hear him. Two people in the audience here? Say yeah.
All right.
Why don't you give him that mic?
Okay. So everybody that manufactures pigments and brings them into the United States or manufactures them in the United States, we all have to meet the same regulatory standards. Right? There's certain clarifying assumptions that everybody has. At a certain point, you trust your suppliers. If you don't trust your suppliers, then you're required. Then you would have to test it yourself. What are pigments? I mentioned before, pigments and dyes are different. Dyes are soluble. Pigments are insoluble. Pigments are defined as colored black, white, fluorescent, particulate matter, inorganic solids, organic solids that are essentially insoluble in their application media. When a chemical company sells a pigment to an ink company, the crystal that's in the ink when it's delivered to the printer is the same crystal that was in the drum of pigment. Doesn't change. There are some inconvenient cases that happen. Phthalocyanine pigments. Phthalocyanine was invented as a perfect pigment in 1935. That perfect pigment's had over 10,000 patents published against it since then to improve it. One of the inconvenient things that it does, it changes crystal form. The alpha shade and the beta shade are different shades. The ink guys get really, really upset when they do a color match and then the color changes during the application property. Pigments selectively scatter or absorb light, depending upon the pigment. They're dispersed in the vehicles. They don't dissolve, they're dispersed. Pigments retain the crystalline structure throughout the application process. Dyes do not. Let's see. Next slide is. All right.
So, as I said, I get very passionate when people talk about dyes and pigments interchangeably. This is to try and show you the difference between a dye and a pigment. It's not the best picture, but on the right here you have two powders, and they're powders. On this side over here, you can see we've just thrown in some water. The yellow is just floating to the top. That's a pigment. The orange is dissolved, and it shows that that's the difference between a dye and a pigment. Very straightforward. So a dye is soluble, and a pigment is insoluble. So the performance of a pigment is actually governed by the crystal rather than actually the molecule, whereas the performance of the dye, the majority, is governed by the actual chemical molecule. Big difference. I spend my life in the lab playing with crystals and trying to make them better. I don't really care about the molecules so much. That's the difference. So when you were talking about green dyes earlier, I was crying. That's a pigment. It's not a green, and it's very important because you're talking to the wrong people. Because if you're talking about a dye, we may as well go home because it's a completely different industry. Well, he may know he's a dye expert as well. As mentioned there at the beginning, I'm a yellow, red, orange type pigment person. Robert's a bit more knowledgeable across the board in blues and greens as well. I spend my life on the yellow, red, and orange spectrum. This is how we manufacture diarylite pigments. So what we do at the top, we have an amine that goes into the diazo tank, and we diazotize. It's on controlled temperatures, typically less than 0 degrees C. Everything's done in water. It's all aqueous based. So we basically do the reaction of diazotization or tetraazotization for specific at 0 degrees C. We buy a coupling component. It's basically grayish material. We react them together in what we call a straight tank. Where I come from, it's called a coupling tank. You control the temperatures again with ice, steam, acids and alkalis. You control the strike. It's at this stage where the colour's made. And it's at this stage where we spend most of our life in the R&D lab playing around. It's not about the actual chemistry. This has been known when were diarylites developed?
Around 1912.
1912. It's been known since 1912. It's all about the formulation. It's formulation expertise. And every company has their own special formulas to make the pigment as wonderful as possible, and we'll touch on that later on. Ours in Canada are better. It then goes through a filtration press, very straightforward pressing, granulate, and then you have drying. Different people, different manufacturers have different techniques of drying, depending on volumes, etc., and what you've installed as your dryers. Goes through a grinding unit. Most of the time goes through a grinding unit. You generate a powder, and it's packed out into paper bags or sacks or drums, etc., etc. Very straightforward process, been around for a long, long time. You would ask where's PCB 11 possibly generated? Right up the beginning in the days, they think. Because at that point, the molecule you perform, or a tetrazo, can give off nitrogen, and that potentially will form PCB 11. And that's the most likely step of its form. That's why your control on that reaction is very, very critical to keep it below 0 degrees C. If you go above 0, you'll get more nitrogen formed, therefore more PCB 11.
Then the question came up as to what colors do we use, what pigments do we use for the various printing applications. One of the things that you're going to notice as you go through these next two slides is that some of these things show up time and again. Top one on the list, blue 15:X. It means it's a copper phthalocyanine. It may or may not have some degree of chlorination involved in it. It may or may not have various additives. The additives can range from something like aluminum benzoate. I always like the one product that has aluminum benzoate in it because it was made by the company that I used to work for the year I was born. And they were still selling it essentially unchanged when I retired. So I kind of like that one. 57:1. Again, it's going to show up being the number 2 one on the list because that is the magenta. You know, they mentioned before CYMK. Okay, the blue was the C. This one's the M. Some applications, then you have various other colors. We'll skip down to the diarylate yellow, the yellow 13 over here on the right, and then carbon black. Carbon black is again going to show up on all the lists because it's, as a practical matter, it's the only black that people will use. Having said that, there are dozens and dozens of different carbon blacks in the marketplace. Some of them are blacker than others. People say, oh, how can it possibly be blacker than others? Well, George showed you a picture of color space before. Well, if it absorbs all of the light, it's black. But if a little bit of the red isn't absorbed, you know, then it's kind of green shade. A little bit of the yellow is not absorbed. It goes over to the other side. You know, black is one of the worst places to be because you're trying to absorb all of the light being right in the middle. But anything that causes it to wander around a little bit, including changing from fluorescent lights to going outside, and the color looks different. If we look here at the digital printing, we see that there's some other pigments that are used. Some of these are very high performance pigments. They aren't necessarily going to show up being widely used in some of the other printing applications. That's because digital printing has more stringent requirements in many cases than some of the other applications. If you go to an art exhibit, they used to call them prints, now they call them, was it Gilchi or Geechee or, they have a fancy name, but basically what it means is it's a print. They use wide format, inkjet printing to do that. If you go, if you have a occasion of importance, you might be getting your invitations engraved for a wedding or for an anniversary or something. You're going to, again, they'll probably use wide format printing. So we use some yellow 150, some yellow 74. The advantage of those is they don't have chlorine. Go over to offset printing. We use yellow 13, yellow 14, yellow 12, depending upon the application. I mentioned that there were about 300 organic colors. There's about 210 different yellows put into the color index. Most of those are organic colors, so let's say 3/4 of them are organic. About a dozen of those organics happen to be diarylids. Of that dozen diarylids, there's actually about 4 or 5 of them that are actually important for use. You have yellow 12, 13, 14, 176, 126, and 83. I knew I was going to miss somebody. Oops. This is basically a very similar list to the previous one. What we have is we've introduced 52:1 is the specialty red. We have the yellow 14 still showing up, the yellow 12 still showing up, and then basically we have the same list for the flexographic.
Okay, so this gives you an idea of the technical aspects what a pigment has to have when we're formulating a pigment for a printing ink. So we talk about chroma. Best thing to describe is brightness. How bright is the color? In layman's terms, that's what it means. So brighter, high chroma, duller, low chroma. Shade functionality. So pigments, I mean, Robert mentioned there, yellow 12, 13, 14. You're thinking, what the hell's the difference? It's basically this. Variance is in shade. And color is all about shade. So you can go from a green shade, which would be like a yellow 14, a mid shade would be like yellow 13, and a red shade, this one here is I think the yellow 83. And there's broad shade functionality. Over here, these are actually iron oxides, which I won't get onto. That'll give you an idea of chroma. That looks very dull looking, low chroma. Iron oxides are very ugly looking colors, but that's their performance. Useful elsewhere. Durability. Is the color going to last? Do you care if the color lasts? Certain things like magazines, they don't care. Other things like posters, you would care. If you think about your car, you'd really care. So this is the example of poor durability where we've exposed the panel to UV light and it's effectively turned white. That's actually yellow 14. This is a more durable pigment. I can't remember which one I chose, but it just shows you the color has stayed. So very important. Opacity, transparency, very, very critical for printing inks. And sometimes they want an opaque ink, depending on what you're trying to cover. Sometimes you want a transparent ink, because like on a metallic can, the Coke can, they want the metallic to shine through. It looks sexy when you're walking down the aisleway, so you can see the metallic shining through. So you want something that's more transparent, so you can see the substrate. Metamerism really is a bad picture. Basically, it's a difference. If you have something in your hand in this room and it looks red, and you go outside and it looks like a different red, it's different color under different light sources. And we will try to formulate away the metamerism depending on what the end use is. Some end uses, they don't care. Dispersibility, this is something that's extremely bad. We get kicked out of the ink plant. If we sold them this, I tried. This is something that's good dispersibility. Basically, whether the pigment particles are going to disperse in the medium. This is where they take the fancy equipment, they grind the pigment down in the vehicle, where you get a nice color development, or where you get no color development. We're talking about crystals. Heat stability says what it is. Will the pigment survive the heat? In ink, it's less critical. Solvent resistance. If your ink is based on solvents, which most packaging inks are, particularly like for the can, the pigment's got to be solvent resistant. Gloss retention, less critical for inks, but basically it's the same thing. If you expose the ink or paint to light or UV, you lose the gloss. That would not be good in certain applications. Color strength, super, super critical, and this is one of the big reasons why diarylids are used. Very, very high kinked-in strength. So if you try to hit the color that somebody is desiring, if you're using a strong pigment, you need less pigment. Using a weak pigment, you need more pigment. So if you have to load up more pigment in the ink, is the ink going to flow? Remember George and Gary earlier said the ink has to flow in certain applications. So if you load up the ink with a weak pigment, you've got to get more in there to get the color. And that's the difference between high tinting strengths. Diarylids are phenomenally high strength. Then we have fitness for performance, fitness for purpose. That's really a performance performance thing, regulatory, does it pass all the regulatory requirements? And there's many to require. Cost in the ink industry, cost is a huge driver. That's one of the big reasons why the pigment sourcing's gone to Asia over the many years. When I moved to Canada, for example, we used to produce about 1,000 tons of diarylates. Today, we probably produce 100 tons. The rest didn't stay in Canada. So it did go. But that's the issue of the ink industry. And availability. You may say, well, let's use this pigment. If there's only 10 tons produced a year and you can't source the raw materials, the ink industry is a big volume driver. So availability of the pigment and availability of raw materials is also a big driver. So these are the big and critical things that we focus on when we're either developing a pigment or pushing or promoting a pigment to a specific customer.
Questions that come up?
Questions that we have then as to how do we sell the products? Depends upon what the customer application is. Are they printing on paper? Are they printing on a can? Are they printing signage that's going to be outdoors? Are they printing something that's going to be thrown away by tomorrow afternoon, like the Sunday comics? What's the value? How much are people willing to pay for the product, that's being manufactured and the color that's in it? People asked, are there any drivers that we might be more aware of, in our consumer system, life? If you go to Walmart, for instance, Walmart isn't one of the companies that most people would immediately come to mind as being conservation conscious. But what you will notice if you go to Walmart is a lot of their packaging has changed over the years. There's less extra stuff. The package fits tighter around the article that they're selling. That's so you can put more of those packages in the box so that you have fewer boxes coming to the store. The second thing you should notice about Walmart stores, if you look around, you'll notice that there's these big overpacks. What do they do with the overpacks? The overpacks is what the stuff shows up at the store on. A lot of the overpacks say, do not throw away, will be recycled. So what they're doing is they're literally knocking them down, sending them back, retaping them, and reusing them. So you're not supposed to throw away the box. Manufacturing cost. How much does something cost? If you're buying a Bugatti, cost of some things is less important than if you're buying a Hyundai or a Yugo, the ones that disappeared, or the German, the Trabant from East Germany, okay? Cost wasn't an issue there. Whatever was the cheapest thing to make it colored was perfectly fine. Supply chain and delivery. Like I said, 1915, 1916, 1917, that's when the pigment industry and dye industry started in the United States because it was difficult to get things here from Germany because Germany was at war with England and France. So the supply chain became very important, not the cost. Over the decades that have happened since, raw materials got sourced from other places, so you were chasing the source of your raw materials. Sometimes your competitor is the only source of the raw material that you need to make a specific color. But that's okay, because you probably supply something he needs. It's one of the interesting things about the color business. All of our competitors are also our customers and also our suppliers. So we rely on each other, even though we are competitors. Customer preferences, they're very global. People have different opinions as to what it is. When you travel, it used to be that they were talking before, Gary and was talking about the branding. It used to not be as uniform as it is today. Back in the early 90s, when I used to start traveling overseas on vacations, one of the things that I noticed was that in the supermarkets in Europe, and even different countries in Europe, different colors were predominant. And the red that you would see on some of the packaging wasn't the same as the red that they would have in that same brand in the United States. In the last 10 years, though, they started to tighten that up. They want that color to be exactly the same in the United States as it is in Greece, as it is in China, as it is all over the world. The regulations, here's a list of all the regulations. We could read them all, but the fact of the matter is everybody has to comply with federal regulations, state regulations, international regulations. If you have any specific questions about some of them, you could ask us. Here's some of the things that we've done from a regulatory assessment point of view over the last 2 decades. Canada was doing the lead with that. Did you want to do this one?
Oh, you think so.
Okay. Canada was taking the lead with that. They had something a few years ago, prioritization and categorization of the DSL. Had somebody call me up one time, very important customer, very serious-minded, individual, wanted me to assure them that none of the products that we sold them were on the DSL. I said, I think that you misunderstood something here. What they wanted to do is they wanted to determine if there's anything on the DSL that presents a risk or a hazard to human health and the environment in Canada. They all have to be on the DSL, otherwise they couldn't be sold there. The one I like is the 2010 U.S. EPA, which happens to be very closely paired with the 2014 Canada assessment of diuretics. The ministries in Canada and the U.S. EPA evaluated these pigments and came to the same conclusion independently. They are satisfactory for the use, that they're intended. They do not present a hazard to human health and the environment. We have the REACH dossiers that came in. We have some OECD SIDS dossiers that took place, earlier for both some of the diarylids and also for the monoazotes. Oh, the 1995 one was an interesting one. Copper phthalocyanine pigments were listed as a hazardous waste. So we petitioned the EPA, and we had started with green 36 and green 7. The more halogens there are on it, the less soluble it is, the less bioavailable it is. They said, okay, we agree. Then we came back with some things that had fewer chlorines, 4 and 8. They said, okay, we agree. Then we came back with them with some, mono and dichloro ones. They said, we see a pattern here. Said, thank you for recognizing it. So what they did is they subsequently delisted then all of the phthalocyanines substituted only with hydrogen, chlorine, and bromine. So they're no longer hazardous waste. Here's some of the perspectives. The industry hasn't done anything to address PCBs. Contrary to what some people think, we have. The pigment industry became aware of PCBs starting in around 1976, about the time the U.S. EPA started talking about PCBs. And part of the reason we became aware of this is because they were in fact doing surveys to try to figure out what the scope of the problem was. They knew about the aerochlors, and the reason everybody picks on Monsanto, by the way, is they made about half the world's production ever of aerochlors, and primarily in the United States. We discovered we had PCBs in our pigments. We didn't realize that. The reason we didn't realize that is because the levels were parts per thousand or less, or parts per million, down. But that's not enough that you would see it in your yields. So there were, incidental components and things. We did things to reduce those. One of the inconvenient ones for us was the Washington State survey, saying that the amount of PCB11 ranges from 20 grams to 31 kilos. Unfortunately, that's because, in a less than precise way, an article was written by a member of our industry a number of years ago, who's educated some 40 years previously, when everybody used Roman numerals. And he wrote down M, meaning 1,000. Well, in modern parlance, it's more common to see an M, and it means million. So slight order, 3 orders of magnitude difference. And that's where that 3 orders of magnitude difference roughly comes in from the Washington State plan. The PBQ is difficult in water. That was already discussed before. If you do follow 1668, have a high resolution GC mass spec. you can identify all 209 congeners as well as the ones that have C13, labeling in them. But it's not something that everybody has. I'm sure that there must be some questions.
Yep.
I think we're done.
Yeah.
I was going to start with the last slide saying, are there any questions? But,
We have 10 minutes for questions. Heather, I'm coming to you there. You guys might want to both stand by the speakerphone.
And share this, I guess.
Yeah, I guess.
I'm sure I'm just asking the questions everyone else wants to ask too. So, several questions, but starting with, so in the diagram where you showed where the PCB 11s are probably generated, you said that it has to do with the temperature and the amount of nitrogen generated depending on the temperature. So 2 questions. 1, if you were to ensure that it was below 0 degrees Celsius, do you get PCBs? 2, are there other chemical reactions that could occur that would not, or do some generate PCB 11s and do some not in that part of your diagram when you're making these particular pigments?
Sure. So the starting material for all diarylides is called dichlorobenzidine. And so you go through a tetraethanization step. So all the diarylide yellows we've talked about all start the same raw material, PCB. The issue you have is, how many chemists in the room? And thank you. Oh, you answered it. Thank you. The issue you have, the production of nitrogen is entropy driven, and you can never cancel out entropy 100%. So you could, the reaction's controlled below 0 degrees C. There's always going to be some degree of PCB11 produced.
There were some other things that were discovered back in the old days, when many of us were younger. And some of the things that we discovered also that led to the generation of the PCBs was little things like the presence of certain metals in, the diazotization tank or in the strike tank. They would cause the decomposition of the tetraazo before it had a chance to couple, to make pigment. The other thing that you could do is by using certain buffers. They happen to be more prone to causing the decomposition. By learning those things, what we managed to do was we accomplished going, like I said, in some cases from thousands of parts per million to, below single-digit parts per million. Why would we want to be low single-digit? One of the things that's overlooked with the TSCA regulation is that it's the annual production and use that has to be 25. So if I ship George a drum of pigment to make ink out of, I only ship a drum of that pigment product, not pigment type. It has to be below 25. Because if I only ship him 1 drum and it happens to be 49 and a half, he's got a TSCA violation. That's why we guarantee our processes and certify our processes, through our management practices to be well below the 25 average so that we never have the situation that we cause the ink or the other people downstream to have a compliance problem.
Any other questions? Really?
Lisa wants a question. She's in the front row. She has to have a question.
You guys are probably familiar with that study from Japan where they measured PCBs and pigments, and some of those were quite high, hundreds of parts per million. So I'm wondering, are there some manufacturers that are just sloppy about some of the processes that you're talking about? And then my second question is, if there's no way to completely avoid the creation of some PCBs, are there ways to somehow remove them from the pigment before it gets shipped out? Or is that not economical?
Removal would be a difficult, if not impossible task. And therefore that wouldn't be a practical way to go since we do manufacture the products in water. The problem that the Japanese had was they signed Stockholm, all right? And they said that you will eliminate PCBs. We won't manufacture and sell them, use them. Then somebody one day asked them a question around 2012. They said, surely you don't mean incidental PCBs that are generated in excluded processes or products that are coming into or manufactured in Japan? And the government said, well, of course we do. But they, in fact, had no guideline in place with regards to testing or compliance. And there were there was a series then of basically quarterly papers that came out. In some cases, it was like a drum of pigment from a specific supplier. It wasn't that all pigment 83 was like that one. It was like that drum of 20 kilos or that drum of 200 kilos, that was the entirety of it. And so part of it was an awareness thing.
There was another part to your question.
Let me answer that first.
Oh, okay.
Very smart.
All right, so here's a Tosca question. And it's an interesting dilemma because Tosca regulates intended use of the chemical. However, we find that these molecules get out into the environment and there's sort of this unintended consequence. Thoughts on how do you really kind of address that? Because we often, as regulators, end up with the end of the pipe to clean up. And so when you narrow that intended use area, it doesn't factor in the full sort of life cycle of these materials. Any thoughts or ideas on that?
You may be smarter on that one.
Well, in that particular case, right now, TSCA doesn't per se address that. And the reason that they don't is because the byproducts and impurities that result in the manufacturing of a chemical substance are not per se covered by TSCA. So when they just did the TSCA reset, I mentioned before that there's something like 155 million organic and inorganic chemicals. In commerce in the United States, per the TSCA reset, there's closer to like 65,000. It's less than that. 43. Is it 43,000? It's right. It was 43,000. Yep. And so it's a much smaller number than we would have thought. But that doesn't include, as at this point, what are we going to do about impurities and byproducts and things like that? It's one of those things we get to do in the future.
Dr. Mott, you said earlier on in the presentation that there are 300 pigments in commerce as organic pigments distributed in commerce. Of those 300, how many are chlorinated processes to produce those 300? Half, 10%, what?
Well, it depends on depends on how you look at the chlorination. Was chlorination used in the manufacturing process? Sometimes you use chlorination in the manufacturing process so that you can use it for the introduction of another functional group. And therefore, what you're most likely to be seeing isn't necessarily the PCBs, is seeing things like PCB 209 and hexachlorobenzene, which result actually from the manufacturing process for the chlorine that goes into making the chlorinated things. But for the pigments, it probably amounts to maybe 2 dozen, maybe a little bit more than that. It's hard to say because you have to look at the things that have been phased out over time, And like I said, the vast majority of them are the diarylates. There's some monoazos as well, but the monoazos usually have another functional group in there. Therefore, they don't lead to making biphenyls, chlorinated biphenyls. By definition, chlorinated biphenyls can only be a biphenyl molecule that is substituted only with hydrogen and chlorine. If there's anything else there, it is by definition not a PCB.
Okay. And my second question, I'm not sure I'm going to be able to get an answer to, but it has to do with the 2010 US EPA benzene study or determination on dyes and the action plan, the determination being safe for human health and the environment. Maybe it's a question
7 parts per quadrillion, because 7 parts per quadrillion is not a standard for, substances. 7 parts per quadrillion is a relatively 2016 established number, which, as we're all aware, the government is still arguing with themselves whether that one is better than the 170. But my recollection is that, for instance, I was surprised to hear that Coeur d'Alene Lake, I think it's a lake, only had double-digit PCBs in it. Because my recollection was that at the Idaho border, the level was ranging between 220 and 350 parts per quadrillion at the border, much to the chagrin of the people in Idaho and Turkey.
There was the FPMD, the semi-permeable membrane device work that was done in the early 2000s, and that had maybe around 100 at the state line. But all of the graph sampling was 60 and 68. The task force did generally much, it's in double digits.
All right.
Okay, I have a couple questions back here too before we adjourn for the break.
Before the next question, this gentleman over here, you had talked about are there any actions to develop a new pigment? You asked it in the morning. Simple answer is very, very, very unlikely. Simply because the cost to launch a new pigment now, it has to be global, and you have to do all the test work up front before you're guaranteed any level of market, and it costs millions and millions and millions to launch a new product now. And I doubt I'll ever see one. I don't know if Steve or Robert or Phil.
The last commercial new pigment family was the dipropyl. It was actually discovered as an academic accident, and a clever SEBA chemist was sitting there looking at this academic puzzle book. Literally, it was an academic puzzle book, saying, please draw a structure for this chemical that we accidentally made. See if you can figure it out from the data that we're providing. And he says, gee, an insoluble orange substance. That sounds like what we do in our pigments division. And so that led to the commercialization of a product. That was 1985 or so. So roughly every 20 or 30 years, you might have a new family. If you wanted to make a new substance, I don't know if Steve ever worked in research or not, but Mark and I did. We could go into the laboratory today. We could probably make 6 new colors that have never been made before this afternoon. The question is, do they have light fastness? Do they have solvent fastness? Do they have any real color value, in an application system that somebody cares about? And the answer to all those questions was yes. So let's say I want to put it on an automobile. There's something called the Florida Sunshine Test. How long does it take to do a 4-year Florida Sunshine Test? Try to sell an automotive pigment where you do not have, especially if it's a new class of substances, where you do not have a Florida Sunshine Test and you want to put it on an automobile. You may remember the Pontiac Fiero, some of you. It was a bright red car, except for the horizontal surfaces, which turned black because it didn't photo fade, it photo darkened. And as a result, that style kind of faded away.
One last question.
That was pretty much my question, but also, so I think one of the earlier presentations said that if you have a specific color, then it was made using specific pigments, right? But if I wanted to make a certain yellow, and I just asked someone to make this yellow, is there only one way to make that yellow, or are there a lot of different pigments they can combine? How exactly do they go about doing that?
So if you said I wanted to make that specific yellow, I would be saying, okay, what weather fastness do you need? What heat stability do you need? What solvent resistance do you need? What's the final application? So there's a whole long list of technical requests. Yeah. Then ultimately you'll come down to, okay, I've got 3 pigments to choose from, plus or minus. And so you can take that 300 that Robert's talked about and come down to less than a handful that ultimately you end up choosing from. Then I'll come back and say, okay, you want better transparency, you wanted this yellow, sorry, you have to have slightly this yellow. And then we have a compromise conversation. And it always comes down, color selection is compromise first. You're always compromising on performance or your regulatory requirements or your cost requirement or your shade requirement. It's a long list of conversations.
If you want a good example of strength and transparency, if you look at these bright red cans, you'll notice that there's a spot at one point where it got overprinted. Okay? It doesn't look like it's overprinted because it's a solid red color. But you'll notice that it's much deeper red. That's because the ink is twice as thick at that point.
Okay, well, thank you very much. I think people have more questions, and it's probably going to be, hopefully you'll be accessible one-on-one. Before we take the break, I have a request, and we're going to go ahead and we can put these up now, I think. We've got 3 big pieces of white paper here, and they describe 3 different topic areas that some of our breakout groups are going to address tomorrow. And so we're trying to get an indication of which topic area and which breakout you might want to be in. And I thought that might happen. And I have some tape. So what I have under here is some Post-its so that you use a pen instead of marker on the convention center walls. And there's a first choice and a second choice. So if you can look at these, decide, well, this is my first choice. I really want to be in the market drivers panel. But if for some reason there's not enough room, my second choice would be the other one. Just put your name under first choice on one of them and second choice on the other, sometime between now and 3:20 when we get started again, and that would be great. And then we'll let you know what group you're in tomorrow morning. We'll re-adjourn at 3:20.
I had one other thing that I wanted to mention. When I said that Mark and I can make, half a dozen things this afternoon, even if they pass all those requirements, you then have to spend roughly $2 million to get it on the chemical inventories and all the places that you need to be able to sell that pigment to before you can ever use it. Yes. And that actually isn't a pigment specific thing. That's a chemical substance thing.
So that's not a TSCA issue because they realize TSCA.
No, it's not a TSCA. It's not TSCA. It's TSCA, Canada, Japan, Korea, Philippines, Australia, and Europe. And you might have limitations and restrictions.
So this will go to the right or left, and then there is a laser pointer on it.
Thank you. The laser is
This red right here. Yep.
Okay. Now this is here?
Yeah. Yep. This is the people on the WebEx.
All right.
They should be able to hear you wherever you go.
Okay.
Hooked up this too just before we microphone.
Okay. Now that in here. I wanted to keep a note here. So.
We'll just do that right before we start. Yep, it's off now. Yep.
Okay, perfect.
The guy next to you.
That's why we're here. So I'm going to be very honest. Thinking I will hang on.
I know, that's okay.
I'm going to use somewhere, I don't expect you to remember this. So we are using these in color now.
Right now, they haven't given us don't include this.
Did you want me to when I do my comments?
Sure. And I'm not
There's something I'm careful to work with that today, because I can now measure part advertising size is below.
You have other things you're worrying about, so if this gets dropped, I'm leaving and I won't be able to get to it.
It's on my to-do list for Thursday morning. Going well. There's the couch. Oh, who do I give it? Me, I think, right now. Okay. Unless I give it to Bob. You know what, I want to actually just
In terms of,
using those, you know what, I extra, but I would love to have some point
along the line.
Yes. How much do we take in as check?
I don't know.
That's all, right? Okay. Yeah, there's a check. There's a cash. This is $150 in cash.
You don't.
Just pick this way, roll.
Yeah.
Yes, $100.
So the fact that Wayne, I can write it by that. I did write it on. So maybe, you know what, on one of those registration forms,
particles have on the things that are, some people think that they're all reason that you can put that against some solvent or against some water and extract it out. I mean, if it was in the crystal, that would mean you literally have to dismantle the crystal to get that.
Right.
And we know that that's not the case because the DC methods, something called the DC PCB method, developed back in the 1980s. And what you do is you dissolve them in sulfuric acid. And various people over the years have tried to argue that, well, you can come up with an easier process if you didn't dissolve it. And you do exactly the same answer, except that there's a reliability.
I had a thought.
How carefully are they doing it? The fact of the matter is that the PCB on the same not in crystal structure.
They don't. Like other molecules, like
just like cool paint. Weathered, all right?
Yeah.
Then that's, that's in part where, why we're seeing it. It's very troubling to us. I mean, really, one of the things that's very troubling to us is just the idea that there's only a few substances and family groups picked on continuously since hospice started. Okay, now a couple of them are, I argue, well, asbestos, BPA and phthalates. I mean, we went through this rather torturous argument with phthalates that, well, it was just these phthalates as opposed to, well, maybe these phthalates and these phthalates, and then maybe these other two are quite close to those others. But folks, at some point you're just going to have to give up and just add these phthalates.
Yeah.
You go to Europe, there's a list of acrylates that are safe for use in contact applications. The list keeps on getting shorter. You would think that when it's bigger, because people do research to find safer ones. Oh no, the problem is, as you test them, well, we have another one, it's also a skin irritant, it's also an eye irritant, So what it is it's a non-testable part. As you test them, then keep on falling off the list. At some point, they're going to have to just acknowledge probably, maybe acrylate.
I was sort of made aware that EPA was feeling sensitive about that, so don't push on EPA a little bit. But I am going to mention, sort of here there is a path for regulation. And there's always a role of enforcement, and really generally, and there needs to be better alignment between, like the OECD work with Congress and trying to look at why is there a misalignment between cost coverage and water access? What are other countries doing in this area? So I don't know if I could mention that you often, answer questions about what you can and can't do. Like, it's still confusing. Like, I guess I'm not a regulation expert, so the only thing I know is, like,
Right, and I wouldn't be able to, I can't speak to how the Water Act interaction, but I can talk a little bit about the product testing that you've started and where that's going to go.
Okay, that's a good idea.
There were some questions around ecology, and I know that the national, well, we're not, EPA is not, the National Toxicology Program is part of NIH, actually.
Yeah, I want to do a talk. So you want to write that down?
Of your career and
Yep. If you're doing something, you're paid reasonably well for 35 years to do something, you think forget about it.
No, it's good that you can work on it. I know that there's also the international pigment association. I tracked the Japan ministry issue for a couple of years, and they came to some determination.
One of the things too that's interesting about the Japanese is they don't necessarily put an absolute standard down. They like, one of the things they like is best available technology, and they even apply that to the same chemical substance coming from different suppliers. So the standard might not be the same for different suppliers.
More flexible.
There's a certain level of flexibility. But the other thing about the best available technology is the market difference between a manufacturing process. Let's say it's a patented manufacturing process that makes something that had markedly less of a hazardous substance than somebody else's. They have a mandate that you must use best available technology. You must pay your competitor for access to that method. He can't cheat you, all right? It has to be fair value to him and to you. But you must do it.
Hey, Justin.
Hey, how's it going, Ken?
Good.
I had a bit of an academic question for you.
Okay.
About surface structure and bird feathers. How does the color of that?
Refraction.
Okay, it's all through refraction.
It's almost all due to refraction, because many of the birds, when they lose their feather, they don't look like what they did when they were sitting on the bird, flying through the air. And it's because it's by refraction. Same thing, a lot of butterflies and moths are like that as well. They're not all absorption colors.
Okay. So it's not a color.
They're not all. No.
I read a number of years ago, this is all R&D kind of stuff, that Toyota was looking at these kinds of sources like, I guess, octopus. How do you produce the volume?
Well, we always look at everything, we try to look. There was an interesting glue that was invented in Oregon State. The guy was mixing together various, transition metal oxides and heating them up to very high temperature, trying to make a semiconductor or something. And he got, they opened up the vessel and bright blue. It turns out that it's a very expensive product, that it might in fact have some specialty applications. If you only have a small volume, it doesn't cost you $2 million to commercialize. In many places you might have small volume. Some places don't. Some places just have blue. In China, for instance, you have to do a registration to bring the sample in to be tested in China. Because there's certain tests that have to be done in China using Chinese organisms.
Yeah, I've read about, their equivalent of REACH or whatever, China REACH.
That's also something that people don't know.
For China, the equivalent of REACH?
It's called REACH, like EU REACH. And then there's...
The laws in China for public health and environmental are virtually identical to North America and Europe. The difference is enforcement. Worker safety. It's like, for instance, for the Olympics, they shut down factories, okay, to make it so the air was cleaner for the sporting events. Many of those factories never reopened. And it was known that they weren't going to be reopened because the replacement factories were already constructed and ready to go as soon as the Olympics were over with. So they shut down the old thing so that now they have engineering controls in them, they have worker protection in them, they have ergonomic things so that you're not relying on people carrying 200-pound bags.
Yeah, an efficient is not egalitarian.
They can just flip the switch.
Well, dictators and sole proprietorships can phase in change much faster than other systems. Like, for instance, in South Carolina, Milliken Corporation, privately held textile company, make a lot of rugs, things like that. The head of the company decided in the early 80s that he wanted a quality program. real simple. He held his quarterly board meeting. He told all of his plant managers when they're leaving, come by the secretary and tell her how many copies of this book you want delivered to your plant site.
Yeah, here it is.
And then what you're going to do, you're going to schedule that we're going to close your plant down for 2 days. And we're going to take all of your workers.
Time to get started. I don't know. I think so. Yeah, I think so. Kat might say something. I found it. It's right here.
I'm going to get people.
All right, but I want to be able to.
Same quality lecture at the same time. You know, we're going to do it on the weekend. You know,
Not still in housing.
those options.
Can people take a seat, please? We're going to get started.
Switch over to the printers. Printers will do the jobs. Figure it out.
We're trying.
Dictatorships are a lot easier to.
Yeah, give her a chance. Why not?
Yeah, we'll be around. Thanks.
So if anybody has any questions about signing up for the breakout groups, feel free, before you leave this evening, to check in with myself or with Kara over here, or Anna Montgomery, who will be facilitating the panel that we're going to have this afternoon.
If you don't go too far,
Yes, I think so.
before you try to do that,
Sure.
So our next speaker is Dr. Lauren Hine, Northwest Green Chemistry, and we've heard now from the printing industry, the printing ink industry, and the pigment industry, and now she's going to talk a little bit about opportunities and challenges and possible next steps and the need for innovation to address some of our issues. And because she gave me her bio so late, it's on my phone.
Do you want me to read it?
I got it. So Lauren is a senior science advisor for Northwest Green Chemistry. She has over 20 years' experience in the field of green chemistry and is the director of Safer Materials and Data Integrity for a new database of safer chemical alternatives for a company called ChemForward, formerly known as MaterialWise. And also, I'll just say Lauren's been pretty active with the Regional Toxic Task Force. She's done some green chemistry papers along with some of her peers at Northwest Green Chemistry, including Dr. Amelia Nessler and Dr. Anna Montgomery. Those papers, you can link to them on the website for this workshop, as well as on the task force website. So without further ado, I'll hand things over to you.
Want the other...
I do. I've got a mic right here. Oh, so let me turn it on.
There you go.
Great. I'm saving this for Kat. Okay. All right. Can you all hear me okay? All right. I'm just getting over a cold, so hopefully can speak okay. First of all, I'd like to thank my colleague, Dr. Amelia Nessler, who is on the line and not traveling right now, for putting together much of this presentation. And I'm really thrilled that with the participation we have, there are a number of experts from all aspects of the value chain here. And so in the spirit of controlled redundancy, which is a term I really like and heard here, I'm going to touch fairly briefly on some topics because I feel like we've had the opportunity to hear from the experts, and I'm someone who's on the outside looking in. I'm not an industry expert. So the goal of what we're doing here is to, the end goal is to reduce PCB levels in the Spokane River. At the same time, we want to increase recycled content in paper, and we want to maintain the vibrant colors of our printing inks. As someone said, the color makes them happy, and there's a lot of value to color. And so we need to be creative and thorough and strategic and research-based and collaborative. So I'm going to talk just very briefly about primarily yellows, diarylates, and blues and greens, and then some opportunities for advancing no and low inadvertent or iPCB pigments. And my goal is to really set us up for discussion. So I'm actually going to be shorter than I intended to be, so we have a little more time for the people who have spoken previously, so we can have a panel and start a much more interactive discussion than we've been able to have. We've really downloaded everybody with a lot of information. So, first of all, and please correct me, Mark Vincent, there's anything that does not look quite right here. But diarylid yellows, this is the primary structure of the diarylids. And example diarylid yellows are the pigment yellow 14, 83, 12, 13, 17. They all share a common structure and common synthesis route. And what happens, as mentioned, the chlorobenzene are used, and Mark mentioned the dichlorobenzene, and you can see such a similarity in structure between the dichlorobenzene and the PCB11. They're very closely related, and that's why they're synthesized. That's why there's a likely generation here. And so there's a two-step process, diazotization, and then this coupling step. And Herbst and all estimate that there are about 60,000 metric tons of diarylid yellows manufactured, and if I use about 25 parts per million, that would be about 1.5 metric tons of inadvertent PCBs. So, we talked a little bit already, we touched on this. What are the options for process controls? We talked about minimizing the time of the reaction, minimizing the temperature. Heather Trimed brought that up. Controlling pH, and some additives like scavengers. These are some things that you can control, but we also learned that you can't prevent the formation of the PCBs altogether. So the benefits of process controls is it can reduce iPCBs. You don't need to reformulate anything. You're still using the same pigment, and you'd have the same performance. The drawbacks is that it does not eliminate them entirely, and this may already be optimized by the top manufacturers. We don't know. We're not the insiders. We don't know if they're already doing best practices or if practices could get even better. Alternatively, we could substitute, use non-diarylid yellows to replace the diarylids in specific applications. We've learned these applications are very specific. You can't just universally say, oh yeah, replace pigment yellow 1 for diarylid yellow and call it good. It's going to depend on the solvents, the applications, all of that. But there are alternatives, monoazo pigments, pigments 1, 65, 74, the acid harylid pigments, and 155. Benefits? Some of them actually improve performance with UV resistance. You avoid the generation of inadvertent PCBs in the synthesis. The drawbacks may be lower performance or color strength, could be increased cost, less availability of raw materials today, and you will need to reformulate. We heard from Dr. Fuchs about the challenge of reformulation. That can be a necessary but challenging process. So with respect to the phthalocyanine blues and greens, this is a nice example of a porphyrin ring. They're really quite beautiful. These are trickier because the examples of the pigment blues and pigment greens, there aren't that many of them. And that's a real challenge. And there aren't that many alternatives. So these are, again, use the chlorobenzene solvents, and you generate the pigment, but you also generate the more highly chlorinated PCBs in the formation of these phthalocyanines. But these may be more prone to process improvements. So part of the problem with the formation is the use of the chlorobenzene solvents. So if you can get away from the chlorinated solvents, maybe you can make these without the PCBs. And in fact, other solvents have been used in the past, kerosene, naphthalene. Now, they're not necessarily they're not toxic by any means, but clearly they can be made without the chlorinated solvents. They have been made without the chlorinated solvents. And there is a technology called the dry bake, which I don't know a whole lot about, but it also is an alternative process. Again, the benefits, it eliminates PCBs. It's been used in the past, and you avoid the hazards of chlorobenzenes, which are, I'm sure, equally toxic to these other, probably more flammable materials. Drawbacks that the solvents themselves are also hazardous, and the dry bake pigment can be less pure and harsher on equipment. So that's a real high-level overview, redundant, of the technical side. And unless there are any specific questions, I'm going to keep going and move toward, set us up for discussion. Any questions? And I will probably defer those questions to the experts in the room. All right, so what can we do about this? Doug had sort of broken it into regulatory solutions and technical solutions, and I've been thinking of it more along the lines of regulatory, procurement, and supply chain / technical solutions. But I think there's a whole lot of things we might be able to do. And as somebody said earlier, there's no one silver bullet that's going to solve all of this. So regulatory, we have to think about what's reasonable, how are we going to monitor and enforce, what are the unintended consequences. Procurement, we can drive the demand, but is this actionable, practical? We're going to learn a lot more about this tomorrow from Sunday and others. What are the unintended consequences of procurement policies? The hydro seed had experience with that. And then supply chain. What's the role of industry associations in here? Can you help with lowering allowable limits as a voluntary part of membership in a supply chain? Can you guide best practices? Can you even guide pigment selection? So I'm going to touch on these in a little bit more detail, and I'm actually going to call on Kat Compton, who very generously offered to speak about some of what EPA is doing now in sort of preparation for regulatory action, potential regulatory action. So I'm going to hand you the mic and let you address. And really, I just wanted to say before you start that with the regulations, we are going to need to identify what are the appropriate limits, how will this be enforced. We learned earlier about the Stockholm Convention and other really strong enforcement limit, and the MEDI study in Japan where we learned that many pigments had PCBs that exceeded the limit, and again, the need for alignment between TSCA, Clean Water Act, and recycling. So I'm going to let Kat.
Yeah, so I'm happy to talk a little bit about what actions are going on in the federal space. I work for the Pollution Prevention Program, so I'm not in the regulatory side of the house. And I can try to answer some questions if there are any in the room around the regulatory, some regulatory questions. But what I'd like to talk about is what EPA and other agencies are doing right now around PCBs. And then I'll touch a little bit on just the Pollution Prevention Program in general and maybe some tools that we have at our disposal that the P2 program can offer. So the first thing that I'd like to mention is that, and Dave Dilks, I think, presented this earlier today too, is that some of the product testing that EPA, ORD, the Office of Research and Development has been doing, looking at PCB concentrations in products. That work is continuing, and with the effort to test more products and then also look at doing some emissions testing, so taking products and looking at how and whether PCBs actually migrate out of those products and into the air, and then maybe potentially doing some settled dust testing as well, whether PCBs can migrate into that settled dust from the product. And so that work is ongoing. I don't have an update other than what has already been presented to the task force, but I'm sure that Michelle Moen and others who attend those meetings will keep the task force up to date on that progress. I also want to mention some work that the National Toxicology Program, which is a part of NIH, is doing in sort of collaboration with EPA. EPA mentioned this to the NTP and has been working with them to encourage them to do a toxicology assessment of PCB11, and that work is ongoing. I don't have an update on their findings, but those will be released, and I'm sure that we can make sure that they get to the task force when they are released. And then Cheryl mentioned the IRIS program, the EPA's Integrated Risk Information System, and there's an analysis of PCBs that the IRIS system has done, that program. And they are initiating sort of an update or a reanalysis. And this is likely to be quite a long process, 5 to 7 years. But the IRIS program does do a pretty good job of at least posting on the website where they are in the process. So there might not be any conclusions or sort of final products for quite a while, but at least you'll be able to see where they are in the process of that analysis. So those are 3 things that are going on related to PCBs, related to inadvertent PCBs in the environment, in our bodies, and products that I think that this group and the task force are really interested in. We're happy to keep everybody up to date on those. From the pollution prevention side, I think that there are a lot of really interesting tools at our disposal, and specifically one program that the EPA P2 program has is called the Green Chemistry Challenge program, and I'm always, my ears perked up when we started talking about, are there possibilities of generation of new pigments or low and no PCB pigment innovations? Because I think that there are some tools at our disposal that might help incentivize or invigorate that work. And so if you're interested in talking about that, I'd really love to connect with you either later today or tomorrow. I'm happy to answer questions, but I also don't want to derail your presentation.
No, that was great. You've got some, why don't we take, there is one. Already a question? Okay. Yeah.
Actually, it's more of a comment, and it relates to the slides that were shown about the 16 products that were tested. And this sort of carries over to the work that was also done by Washington State on when they tested products. I think that it's grossly unfair to say that you tested 16 products and show like 24 containers of Play-Doh. You probably tested one of the Play-Dohs. You didn't test all 16 of them or 24 of them. Same thing with the chalks. You probably tested the yellow chalk. You probably didn't test the red one, the white one, et cetera, et cetera. And I think that that's grossly unfair, to the public as well as industry.
Why is that unfair? Why is it unfair?
Because it's a misrepresentation of the facts. If you didn't test the products, don't show them. If you didn't test the red, the blue, the white ones, don't show the containers of the red, the blue, and the white. If you only tested the yellow one, show the yellow one. You tested 16 products, there should be only 16 pictures up there, not, a picture containing 24 different, colors of Play-Doh.
So we have another, Roger had a question. Oh, okay. Doug.
Largely deal with null sets because you don't test. That's the reality. You largely deal with null sets because you don't test. I guarantee you, if I tested any of your houses, any of your yards, any of your stuff, you're going to have just as much as anybody else, and maybe more. So it's a null set because you've never tested.
Doug, did you have a question too?
So kind of a big what-if question, Kat, is that we're doing this toxicology assessment through the NTR, whatever it was. We already know that PCB11 is not as persistent, not as bioaccumulative. What if it comes back that there is low or no toxicity to PCB11 through this assessment? What do you think is going to happen next? And, I know it's not a full-blown risk assessment, but, if it gives us an indication that maybe perhaps these lower-level PCBs are not toxic, what do we do? What's next? I mean, does it open up a larger conversation around perhaps not regulating monos and dyes?
I do know that, so, there have been some questions about PCBs regulated under TSCA, and there is a process to update regulations. And in order for that to happen, the agency has to make a finding that the existing concentration is not protective of the population and that a new level would be protective. So information that gets us to answering those kinds of questions are needed in order to move on that front.
Yes. And then I'm going to finish my presentation and we'll have a panel. But this is good. I feel like you've been so patient and a lot proudly.
Kat, I know you said you're not on the regulatory side of things, but does the EPA have a stance on the Stockholm Convention or on the update to the POPs regulations? So a lot of us who work in industry deal with global regulations, so we follow those anyway. So does the EPA kind of take away key learnings from these things? And maybe that's something you can't comment on, but I was just always curious.
Wait a minute. I should be giving you the mic. Are you?
Yeah, for those who couldn't hear me, so I actually don't know the answer to that question. And but the Office of Pollution Prevention and Toxics, which sits within the Office of Chemical Safety and Pollution Prevention at our headquarters office, is the office that houses the TSCA program. And so those sorts of questions would be better directed to the director of that office.
All right. Thank you, Kat, for your impromptu help here.
Yeah, Steve Kamish, BASF. And I don't know if this answers your question or not, but there are no drivers in Europe to reduce the 25 ppm limit for pigments or any other inadvertent produced PCBs. And I think that that's an area that's of no concern in Europe at this time.
Thank you. All right. Basically, I'm just going to run through some sort of high-level ideas about areas where we might be able to intervene and innovate. One of which is procurement. We're going to learn tomorrow a lot more about government procurement and the state of Washington's new law and how it's being implemented and some of the challenges of that. But there's also private business. We're going to hear from HP, who's going to talk about their material specification. They set a limit for PCBs that is below what is mandated by TSCA. We're going to talk about what would be the value of unified procurement policies. How might we reach consensus on a number? Does that number need to change for different products? Or can you agree on some number to kind of start to ratchet things down? And related to that, that limit, is it reasonable? Is it actionable? Is it measurable? We learned about the challenge of measuring to 7 parts per quadrillion and the test methods that assume that if you reach 50 that you're okay, parts per quadrillion, that's as low as you can go based on the law. So what limit and what limit would be necessary to reach the water quality limits in the Spokane River? And how would you verify that? Who's going to verify it? Which test methods are going to be used? And then related to that is certification. Might there be a place? I think Heather Trim, you had brought that up. The idea of certified products that are certified free of PCBs or certified to have ultra-low levels of PCB. How might that support procurement or verification that's worked in other sectors where you see BPA-free bottles and things like that? But how can we simplify the process of procurement, help people who are making these decisions? How can we engage leading brands to help drive this? And this may drive additional specifications, and these are all going to be challenging conversations. Supply chain engagement. This is, we learned about how a lot of the pigment manufacturing does not occur in this country, and inks as well. And what can be done, say, at the industry association level to advance lower inadvertent PCBs across the globe and across the value chain. And availability. We touched a little bit on if everybody was to switch away from diarylate yellow today, what would they go to? Is there enough material available? How long would that take? And how long would it take to reformulate to achieve a similar or a good enough performance level? It's doable, but what's involved? What's the cost in doing that in time, in performance, and everything else? And so here's kind of a sort of a summary of some different approaches that we might be able to take and things that we need to be able to consider to implement to get to a place where we are protecting the fish, we are protecting the people, we are protecting the planet. And but what we do know is that we need to do this in a collaborative way. Who needs to be at the table? We've got a fabulous representation of people here. We thank everybody who travels to be here and are in Spokane. And I guess with that, I'll start. We can bring the panel, people who spoke in this session can come up and have a seat, and we can answer some questions and have a little bit of a panel discussion. So, the speakers from the last session. And yep, yeah, and I delegated to both. Yeah, I think we need both of you.
Yeah, we need, and George.
You wish George.
And Gary.
Yeah. All right, come on. Where's Gary?
Gary's coming.
He's coming. Okay.
I think you need one more chair.
One more chair.
Gary ran away.
Beautiful chairs here.
Mark wants to volunteer not to be here.
Mark wants to volunteer not to.
I delegate.
I don't know.
Okay.
All right. Good.
Sorry.
All right.
No, we need you guys.
All right.
Before anybody asks a question, I just have one that I wanted to throw out, and it sort of relates to something that Doug, I think, mentioned in his presentation a little while ago. That is that why is it that mono and dichlorobiphenyls are considered to be an issue in the United States to begin with? In doing some reading over the last week, actually, I discovered that at one point, about April 1st of 1986, I think it was, that the first PCB regulation actually was published. And at that time, there were 210 congeners. Why are there only 209 congeners now? It's because at that time they included in the definition of polychlorinated the one congener that contains no chlorine. Now, if we go to Europe, by the way, or to Canada, they have a better understanding of the English language, apparently, and they define poly to mean 3 or more. And that is, in fact, what the regulations in Europe and in Canada say with regards to polychlorinated biphenyls, and they've always been that way.
Nothing to do with persistence or bioaccumulation or anything like that.
Well, even if you go back, even if you go back to the, fundamental regulations within the U.S. EPA, you can argue as to what the basis was for picking 500 versus 50 versus 25 or any other number that they might have chosen. But the reason that they chose the discounts for the dichloro and the monochloro is because it was recognized in 76 even that they did not demonstrate the toxicity that the dioxin-like PCBs and dioxin did. And there was a valid reason why they should be considered somewhat separately.
When did you say they don't demonstrate the same persistence in bioaccumulation?
I didn't say persistence.
Toxicity is different.
The toxicity.
Currently studying the toxicity of the.
Yes, and the reason they're doing that is because the only tox studies that have ever been done were on the aeroclars and on the 12 non-diox, or the 12 dioxin-like PCBs. The other, 200, 197 haven't been tested.
So you can't say they're not toxic if they haven't been tested.
Can't say they're toxic either,
Right.
but you have.
No, I say as a class they're considered.
So before we get started with a formal panel questions, I just wanted to introduce Autumn.
We're just talking amongst ourselves.
I know. I know, thank you.
Thanks very much.
Yeah, but I also, well, actually, you're having an informal conversation, but you are on the webinar. So Autumn Montgomery is Executive Director of Northwest Green Chemistry, and she's going to be formally facilitating this panel now that you've given her the microphone. Thank you.
Thank you very much. I will give it back, I promise. One thing that we wanted to make sure that we do here is to help everyone here synthesize sort of part of what's gone on through these past few presentations and look at what does change look like from these multiple perspectives. It's one thing to hear about it, from each point on that, but it's another to really begin to put this together. Of course, look at potential solutions, and there's still disagreement on the facts, which is expected, and that's part of why we're here. But we're also here to look at how do we go beyond that with the information we do have. So I want to make sure that there's an opportunity to ask more questions, but I think we'll kind of start with a question or two, and then please do let us know if you have something that you would like to follow up with on that or ask a specific panelist a question. But keeping in mind that the point is to sort of let's gel all this together, not take apart each thing separately. So I think we have definitely, it sounds like iPCB levels in existing pigments can be reduced in the process of the diazo tank. Could you please speak specifically to that process and kind of the ranges with that so that we can begin to understand, is that a potential solution?
Yeah. Every manufacturer is different, and Steve's in here somewhere, so I'd be interested if he's really got the data in his head. My experience is with diarylite pigments, PCB levels is around 1 to 5 ppm. That's a typical range. I'd say we control it by controlling the temperatures. Do I feel like by further control, could we get it down even further? Maybe, possibly at 1 to 2, but I can never ever imagine it in diarylite pigments being less than 1. Again, there's a natural driven process, entropy, if you look up entropy in the chemistry books, and nature drives some of it, some of the synthesis to PCB level. What your experience is?
Well, just to reference what I said before, one of the things that we did have when we first became aware of the idea that there were potentially PCBs in our products, we started looking at them, trying to figure out, well, gee, we didn't realize that. There's no reason for analyzing for something that you didn't know was there. We identified that they were there, and like I said, in some cases they were there at well over 1,000 parts per million. Now, one of the interesting consequences of that was that we improved our manufacturing processes to get them down to essentially something below 10. Like I said before, the reason you want to be below 10 is because you want to make sure that you never ship a customer a single drum of something in a calendar year, causing them to have a TSCA violation. So you need to be certain that you're way away from the 25 average in order to be able to accomplish that task. One of the problems we discovered then is we got customer complaints when we reduced the PCBs. And so what it basically did is it then led us to a whole other area of research. Why do we get customer complaints? It turned out that basically what we were doing is we were painting the surface of the crystals with PCBs. We didn't know we were, but we were. And therefore, in some ink applications or some plastics applications, the product dispersed better. When you took them away, the product no longer was coated. Therefore, when you took the water away, pigment crystals slapped together like a thunderclap, making them hard to
because we had taken out the inadvertent degenerated PCB. That doesn't mean anybody ever thought about putting it back in, by the way. Besides the fact that the agency had a regulation, I mean, there's no way that you would do that.
I think that's a good segue into, would anyone here like to share an example of a recent pigment, ink, or printing innovation and sort of the driver behind it? Doesn't need to necessarily be related to this issue.
Well, yeah, I kind of mentioned some of the changes that took place over the years, and probably the biggest single one was the introduction of water-based systems, primarily flexo printing inks, where the driver was to limit air emissions, and so VOCs, organic compounds, and so the idea was to drive those out and replace them with water, which they did through the use of an amine compound, which would make it soluble when there was water in it, much like water-based paint works. It's the same principle. You use an amine to solubilize it, and then the amine evaporates off, and then it's no longer water soluble. So that along with the energy curable ink systems, so the use of either a photo initiator or an electron beam, was the same incentive, was to limit air emissions from print, not only from the print process, but from the manufacturing process as well. So whenever you can drive out the use of a volatile compound, it makes it safer to manufacture, safer to use, and fewer air emissions. So it was probably the biggest, single one that I can think of. I mean, obviously the elimination of heavy metal-based pigments was another driver.
Yeah, and another aspect of, going to what George was just talking about the waterborne, systems, it may seem counterintuitive, but if you wish to make waterborne paint or waterborne ink, first thing you need to do is dry your pigment, because the pigment as manufactured is 75 to 85% water in the press cake, and the consistency of that press cake in some cases is almost like paving brick, depending on how hard you squeeze the press. But it still has too much water for you to be able to actually use it for a useful purpose. So what you have to do is you have to dry the product, and then that led to the innovations that people had to do to develop how do you now disperse it without the use of aromatic solvents or other solvents, so that you can now have something that would then work in an aqueous paint or aqueous ink.
What I'd like to add is from the printing perspective, the ink on substrate aspect, probably the greatest thing that's occurring right now is the change in technology and the migration from conventional analog to digital applications. It's being driven primarily because of economics. Obviously, economics drives a lot of things. But from the benefit from an environmental perspective is that you have less waste at startup. You have significant less use of solvents to clean, because some of these technologies don't require an inkjet head, for example. Instead of using, printers would buy gallons of cleaning solvent that would evaporate, right? Now they're buying quarts, and they're using wipes to clean the heads off. So that, to me, is a huge innovation from an environmental perspective and also from an industry perspective, and I think we'll see that continue to migrate. Challenges are the technology themselves, but there are stepwise changes as well as revolutionary changes that are occurring in the digital application. So it's fascinating to me to see where it settles. But you have real limits at this point. You're not going to print Cheerio cereal boxes off the digital press because it's just the economics aren't there. The cost is high, as George alluded to. The inkjet inks if you think the inkjet inks in your home printer are expensive, when you buy an ink set at $50 a pop, literally printers who have these large format inkjet, these drums are $10,000 each. A 30-gallon drum of ink is $10,000 for each drum. So where they're making their money, it's just like Gillette. They give you the handle and charge an arm and leg for the razor. So, you buy a home desktop printer, you can get one for, $39.99, but go buy ink for it, right? So Where they're making the money is on the ink. So the ink, those digital inks are incredibly expensive. So the cost aspect of it, run length and cost, there's a huge factor. And we have companies that will get orders in from customers, and they'll do the math. They'll say, if we do it analog this way, do it digital, here's your cost, here's your benefits, and then the customer chooses the way to go in terms of getting the product produced. But I would say clearly that the introduction of digital technologies, applications, and where that's moving is really significant for the industry.
Can I ask a follow-up? Why is the digital ink so expensive? What's the process? What's causing? I always thought it was a marketing thing. Buy the HP printer for. I'm sorry.
Well, I would say, that's a good question. I would say perhaps these gentlemen can talk about the specific ingredients and what goes into it. I think there's a lot of proprietary innovation in those systems. A lot of them are tied to the application method. So in other words, you just can't go down to Joe's inkjet print store and get ink to work on your system. You have to buy an HP inkjet ink with an HP system. You have to buy an OSA ink. And there's a lot of development because the secret sauce is the heads, right? And how the heads fire and how they deliver the droplets of ink to the substrate, and that's where the inks are tied to that application method. And so there is a tremendous amount of R&D that goes into it. So I don't know if the material cost is there. I think it's how they're going to recoup their cost for the development innovation. It's my opinion, is what drives it is the application. Now, I think there's differences in perhaps pigments that are used in some of these systems. There's differences in the solvents and binders and all that. So those could also be a higher cost factor.
I did notice when, I think it was you, George, who put up the slide of digital versus some of the other technologies, that something like 3 out of the 4 were not diarrhea that were used in the digital technology. So I was wondering if there will be a shift in the type of pigments used as well as digital grows. And then this is, I know you can't answer this because you're not a voodoo, whatever, but you can't predict how big will digital get, what percentage will eventually that take of the market, because this problem could go away if digital were to sort of take over, Let
me add to that. I don't know if I mentioned this in my presentation or not, but the limitations of digital are such that you can't get, in many instances, direct color match. So you can get close, and I think that's because of the pigments. So you can get close with digital, but you cannot necessarily always get exact color match. The analog, that's where a huge advantage you have for the analog systems, is you can get direct color match. And I think the palette pigments available are much greater you have than in the digital. I think you're very limited in the digital application, so that's a hurdle that has to be overcome.
Right now, technology limitation, and
if you remember back to that slide, the first 2 pigments that were listed in each of the 4 ink types that I had up there were pigment blue 15:X and 15 and red 57:1. Okay, that means same chemical used in all 4 applications. What happens though is that in some of those traditional analog applications, what we've done is we've developed products that we're selling tens of thousands of kilos of. All right, those pigments don't work in the digital applications. They literally don't work. Same chemical, by the way, when you finally get around to finding something that works. But the 57:1 that you're selling tens of thousands of kilos of, you can't give it away for a digital application. Same thing with the blue. So you didn't invent a new molecule. What you had to do is you had to come up with a way so that that molecule was, if you will, sufficiently wet or mixed with something so that when it gets put into the application system, that it disperses so that you have crystals that aren't clogging up the inkjets. The big problem, if you think that you have dispersion problems, with a regular printing application, all you see is spots and streaks. On a digital application, if you have a dispersion problem, you have no color.
So it sounds like some of the drivers for change have
we have some packaging and printing people, if they're still there in the audience.
Anyone want to speak to that?
Maybe on the raw material side, where you said raw material shift was to more foreign countries as your supplier. Is it similar to like the rare earth materials that are very limited in production or availability? Is raw materials limited in, where you can find those raw materials in those outside countries?
The prime driver to the Asian countries for the manufacture of the pigments was purely cost. The raw materials over the years, as a result, have drifted that way too. And so China in particular has become the raw material manufacturer of the world. Even when you're sourcing your raw materials from India, the raw material manufacturers sourcing their raw materials from China. But really the prime driver was cost. And the ink industry is hyper competitive. And George would say it's not the most profitable business in the world. It's one way to lose money a lot of the time. But it's a very difficult industry. And it's a declining industry of a lot of things unless you're in the packaging or specialty. So driving out cost is what's moved manufacturing out to Asia.
Anyone else want to leave?
I wanted to add something on cost. I didn't mention that in my presentation, but just to give you a perspective, George had mentioned, there are literally tens of thousands of printing companies in the United States. It's one of the largest industries that you've never heard of or never realized existed. But on average, the average printer at the end of the year makes 3 to 4% profit. So in terms of absorbing huge cost increases, it just isn't there. And as the printers go back to the ink companies and play one off at each other, the vendors, customers go back off printing companies and play one off each other. So there's always a downward pressure cost curve that's occurring. So where that suffers is in profits. Now, there are profit leaders that make more than that, but the average printer is around 3 to 4% profit at the end of the year. And so, we have jokingly say, when CDs pay interest, you make more money on putting your money in a CD instead of buying a $2.5 million printing press. And some of these printing presses are very expensive. They're not inexpensive. It's a major investment. And a lot of these companies are family-owned. So it's everything they have in that business. So, clearing that level of profitability, it's very difficult to say, oh, we'll just increase costs, because that becomes a challenge.
I think this is also interesting, and maybe Kat, you want to speak to this, but we talk about incentives for innovation and where we need to intervene in the supply chain. And I think you're bringing up an important point of who should those incentives go to. And I'm not really familiar with that at this point, but that's something we want to talk about in our procurement discussion, in our regulatory discussion. Do you mind speaking to that? Or? Well, just you had said there were some incentives.
Can you come up here and speak near the phone, because that mic isn't picking up for WebEx. Yeah. Their mic. Well, you can just speak by the speakerphone. That's fine. Okay. So, like I said, I work for the Pollution Prevention Program. We're the non-regulatory side of the house for EPA, and within that, there are a couple of tools I think that this particular community might be interested in. And one is the Green Chemistry Challenge program, to basically incentivize exactly what we're talking about here. Are there ways that we can design a challenge for a no PCB pigment, and what would that look like? I would be interested to know if there are players in the academic space or in the industry space that are actually working on something like that, because, it sort of takes two. You have to have the incentive, but you also have to have the folks that are doing the innovation that want to then get incentivized. And so I think that's something that we might want to think through if we're thinking through pollution prevention opportunities. What levers can we pull that are actually ripe, and are there enough players in the innovative space to have something like a green chemistry challenge actually work, or who would come in under that?
So that's one thing that I'm curious to learn more about. Same goes for other programs like the Small Business Innovation Grant Program. These are grants essentially to take new commercial technologies or new innovations and then commercialize them, make them, put them out into the commercial space and ramp them up in a way that they actually can be competitive. And so again, that's another opportunity to start thinking about ways that we can start conversations with different programs within the EPA or within other agencies and engage both the industrial folks and the academic folks and then us, the federal folks, to think about ways that we can design challenges or awards or grant programs that might, set us down a particular path.
Isn't it correct that the majority of the winners have been technology and not new chemical substances?
So for the Small Business Innovation Grant Program, this is it's not housed under the Pollution Prevention Program, and I know, maybe just enough to speak a little bit about it, and I can't speak to the history of who has been successful with that program. I do know that over the last couple of years, there have been categories like greener plastics innovation, which definitely is a more of a chemistry focus, not necessarily a technology focus. That's what I can offer, and I'm curious to have conversations with folks in the room that are interested in thinking through some of these opportunities. I think I still have a lot to learn about how we might use them and when is the right time to use them, but I'm really curious to start those conversations.
Thank you so much. Yeah. Does anyone have a question at this time?
Doug does.
Of course. Kathy's got my wheels turning also on something else. Just go ahead and talk then.
Be loud enough. The speaker for the WebEx is up here.
Okay. Just quickly, Dr. Mott, I had kind of led you in on a question before about the number of pigments that are actually in commercial distribution, 1,000 at one time, and for whatever reasons have decreased over time to now 300. And the question was, well, how many of those are chlorinated substances? And you were saying a couple dozen. So I won't hold you to 24, but somewhere within plus or minus of that. So that was actually encouraging to me because I didn't know if we were dealing with 50% of all pigments produced were chlorinated, which would make it much more of a heavier lift to try to actually find alternatives or substitutions. Of those 24, I'm going to go out on a limb and assume that most of those are probably widely used within the industry. Those chlorinated substances, they're probably blues, greens, I'm going to guess, and the dilurid yellows. So a good portion of that 24 probably accounting for a good portion of what's actually being used out there in the world. So what is the opportunity for being able to substitute or pick a different pigment, a non-chlorinated pigment, for various applications?
By far, from a tonnage point of view, if you're going to make something yellow, you're going to use diuryl yellow. It's not even close. In fact, what did you say, Mark? The top 5 or 6 yellows are all diuryl yellows. Yeah, 12, 13, 14, 17, 83, 126, 176. 74 is just sort of nudging its way into that group, but all those others are diuryl yellows. The only phthalocyanate, the only green, as a practical matter, there's 2. One's brominated, chlorinated. The other one's just chlorinated. Green 7, green 36. Printers don't use those colors very much. The reason why is easy to think about. Green 7 is roughly twice the molecular weight of phthalo blue. Okay, that every time you add 35 to that chlorine, it doesn't make the color stronger; it just makes it greener. All right. So as a rough approximation, that means green 7 is half the strength of phthalo blue. So you can mix in a lot of yellow and accept the dirtiness of the shade mix before you are willing to pay for the strength loss. Green 36 is even yellower, but now you're putting bromines on. Each one of those is 80 and 79 instead of 35. So the strength gets even weaker. So if there's a printing application using green 36, they really, really want a clean, bright shade green for that application, and the substitute doesn't exist as a practical matter because they would have done anything to avoid using it.
Yes, it's going to be difficult.
It'd be difficult.
Try to replace the blue? I don't know. I can't think if you would say I want to replace phthalo blue. Phthalo blue is the blue everywhere. And, in plastics there's another blue, but you can never use it in anything.
They must have been using iron blue or something, or alkali blue or something back in the 20s.
Okay, well,
But the rate of the printing was really, really, really slow compared to the printing today.
How does Mother Nature synthesize these colors?
They don't.
Obviously, it's not using chlorinated processes to make that happen. So
these are synthetic colors. They're not made in nature.
okay, but they're beautiful yellows, there's blues, etc. So do you study how Mother Nature synthesizes colors?
Oh yeah, a lot of the color that you see around you in nature, in part, is perceived, especially if it's in birds and butterflies and moths and stuff. Because what you're seeing refractive color. You're not seeing absorbed color, if you will. The other thing is that things like chlorophyll, carotene. There are people that use naturally occurring pigments that they've extracted from beets or carrots or whatever, and use them to color things. They aren't as light fast. They aren't as bright. They aren't cheap. And they have very limited applications. But there are people that do that for certain applications. And is there the possibility that over years technology could change? The answer to that is Clarke's third law. I don't know if you read science fiction or not. Arthur C. Clarke had 3 laws. The most important one was his third law. And his third law was if an old experienced scientist says something is possible, it's true. If he says it's impossible, he's invariably wrong. And that's why we continue to do research.
So a question for the panel members. I think on one of your slides, so there are quite a number of color standards. You mentioned ISO and half a dozen other standards. So picture this. You've been given the task to come up with your own color system. How would you convene the right group of folks to come up with a standard that would go towards these lower levels of PCBs and convening that process?
Yeah, that's a very difficult question. I mean, these industry consensus standards have been developed over decades of research and development.
Well, pretend you're like 23, just out of school.
You don't know what you don't know.
George? Yeah, I think one of the aspects too is, don't be mistaken as to what the standard is. The standard doesn't say take this much of this, of blue 57 and this much of green 6 and and this much of yellow 150, and that's not what it says. That's an appearance under a certain light source. And how, so when they go to the customer and they say that I want this Pantone color, the customer goes to the printer or the ink manufacturer, I want this Pantone color. Depending upon, who they went to, they might end up with a slightly different formulation. That's why the formulations are proprietary. Okay? As are, if you ask a pigment company who your customers are, well, it's all the ink companies and all the pigment manufacturers and all the and I also buy from them. All right? So we buy buy from each other, we sell to each other, and we compete against each other. But we don't go around sharing who our customers are. And the ink guys don't go around sharing their formulas. They don't go around sharing who they buy their pigments from. Sometimes they might be buying them from Dominion Color in Canada, and they might be buying from Sun, and they might be buying them from a Japanese company and an Indian company, and they're buying the same pigment type from each one of those companies. But for this application, they use the Sun product. For this one, they use the BASF product. For this one, they use the Indian product. For this one, they use the Japanese product. So even if you told each other, I'd sell to that customer, you may not actually be directly competing against them.
I think Ken's question was a little different, though. I think you're kind of trying to look forward and say, if you were to convene a group of people to create a new pigment, who would that be? And especially if you were also concerned about some of the inserts. I think that was just more of a little bit more, can I quote you, Ken, a little more of a hypothetical future question.
Create a new pigment? You're talking the colour standards, like a Pantone.
Right.
Yeah.
So, I guess, a color standard, it sounds like you do collaborate throughout the value chain. How do you do that in a non-competitive way, antitrust, kind of situation? I know that one of the organizations has a research arm, and you've convened groups in the past around certain issues. Would it be possible to convene a group around this particular issue, or are we just wasting our time? So that would be kind of the question I would have, because we've tackled some tough issues in the past, and so this idea of either creating, I've worked on standards before. I know they're a very challenging, stakeholder-driven process, take a long time, and very exciting. But that's one approach. There may be other approaches. How do you collaborate, or is it more this informal thing that you're kind of talking about here?
Yeah, well, that, as Robert indicated, that's kind of the industry art, right? I mean, you're trying to hit a target that has been established, and how they do that is their intellectual property, and it differs from one company to another. So, I mean, when I mentioned to the color scientists about, trying to hit these color targets without the use of thiocyanine or diarylated pigments, they just shrugged their shoulders and said, well, you just have to decrease the color count, the gamut, that's all, because you won't be able to hit these targets without the use of those pigments. I mean, it certainly is an issue that we could more clearly identify what the ramifications of that would be if you say, well, let's formulate that any of these and see where does that leave us. I'm sure there's enough guys in the ink industry who can look at that issue and say, okay, well, yeah, you could do it, but this is what you would end up with in terms of your ability to match all these Pantone shades of colors. Yeah. So is it impossible? No, it's not possible. You're dealing with a whole different kind of palette of colors that would be available to you.
I wonder sometimes if, where would you even focus those efforts? It seems like the bright colors are very essential for some applications, and then it seems they're nice to have in others. And are there places where the color is good enough that it doesn't need to be quite as bright? It doesn't need to last for a long time, right? So are there areas that you could think of where there could be impacts to, say, a company like IEP, where, maybe a magazine inserts don't need that application, but a car paint certainly does. You know what I mean? Like, is there somewhere to intervene that could impact?
Let me add to that. I think, there's a possibility, say, for example, if you're going to be printing a pizza shop has a sale, and they're going to, buy one pizza, get one free, and they're going to print a coupon. Well, maybe you can be okay with that. But if you have Lands' End, and they're selling a yellow sweater, that's their storefront. I mean, so you want to buy, if you were going to buy a yellow sweater, you want to, that's going to be pretty darn close. The other, furniture,
make their living is through catalog sales. And they're going to say, by the way, you can't have these in your pallet. And they're like, well, we can't sell our product because it has to be pretty darn close. I mean, you think about it, if you purchase the product, you say, hey, what I bought wasn't what was in the catalog. You know, I'm sending it back, you know, and that's a challenge.
So today,
Turn on.
oh, there, okay. Yes, now it's working. Is it working?
No.
No, it's not working. Okay, here we go. So today we're talking about PCBs, and it's all about PCBs. But in the real world, there's a bunch of different endpoints that we worry about, and one of the ways we do that is through life cycle assessments, and they have many different endpoints, you know, eutrophication, toxic chemicals is one, greenhouse gases is another really big one. And so I'm wondering, has there been any push within the pigment and printing industries to do life cycle assessment in a broader sense? And if so, has the issue of toxic chemicals come up? And if so, are there trade-offs that have to be made? Like, for example, I'm not sure I want to reduce PCBs if it means increasing greenhouse gas emissions. So is that under discussion at all in the pigment and printing industry?
You know, the only life cycle assessment that I'm aware of that even peripherally relates to printing ink was the Soybean Association about 10 or 12 years ago did a life cycle assessment on the use of soy oil in printing inks. And essentially, my personal opinion is they have an agenda that they wanted to determine that they were more environmentally friendly than others. But what they finally concluded was that it was pretty much a wash between the use of petroleum hydrocarbons and soy oil for printing inks, and that might seem a little bit counterintuitive. But essentially, when you do a life cycle assessment, they looked at things like the environmental impact of farming, soil depletion, water usage, pesticides, herbicides, and then compared that to petroleum hydrocarbons. And said, wow, they're cheap to get out of the ground, they've got a lot of energy content, they're easy to use. And so, you know, and couple that with the fact that there really isn't any industry consensus standard on how to do a life cycle assessment. It's, as you guys know, it's kind of like peeling back the layers of onion. How deep do you want to go when you're doing one of these life cycle assessments? So, yeah, that's the only, I'm not aware of any other. Gary, maybe you are?
I mean, I've seen, there's been some studies done comparative. Obviously, print competes with electronic distribution of information. As you guys know, everyone has a cell phone in their hand and consume a lot of information that way. So I've seen a lot of comparatives, not a lot, but some comparative studies on the print versus the electronic. And what's interesting, as George indicated, you know, when you look at scope and assumptions, there's a lot to be said. So I had a few questions for someone that concluded that the electronic delivery of annual report was way better than printed because, you know, you're killing trees. And so then I'm like, well, how did you get the computer? Well, that wasn't factored into it. We didn't consider that in our scope, but yet you looked at the fact that you had to harvest trees and then had to process it in paper, so therefore there was, you know, it weighed against the printed. And I'm like, well, your electronic information just doesn't parachute into your head. You have to have it stored on a server. You have to have a computer. You have to access it. So what's the impact of the computer? So, but to answer that question specifically, in terms of the chemical assessments, there's been a little bit of information on a chemical by chemical basis, but nothing. You know, there's some issues that come up with, as George mentioned, some of the photo initiators and some energy has become a concern. So when that gets flagged, I give credit, 100% credit to our supply chain. When those things get flagged like that, the supply chain reacts, I think, quite rapidly. There was an issue with some photo initiators on Europe and some concerns with how those are classified, and those got formulated out. So there is a lot of, you know, the supply chain is very responsive, if it's possible. You know, I'm learning probably as much as you guys are about pigment manufacturing as part of this process as well. So because from our perspective, as I said, the this on the line. So,
the thing that always comes to my mind is we have to be careful about mandated solutions. The two examples that I would use is two organic solvents that are fairly common in laboratories, and you may have used them if you do a lot of chromatography. One is tetrahydrofuran. All right. When I first entered college, a long time ago, we didn't have colleges in the United States, and tetrahydrofuran cost about $50 a pint. It was being manufactured as from waste byproduct, and from all through the Midwest, all this corn. There's all this corn, excess biomass being converted into something. They generated a demand for it. They figured out a way to do it cheaper. The technology improved, and therefore it became much, much less expensive, and it still is a viable solvent. The other one that I like, which is a mandated solution, is methyl T-butyl ether. When we took tetraethyl lead out of our gasoline, we had to do something to improve the efficiency so that it would burn properly in the automobiles. I mean, they weren't just putting tetraethyl lead into the gasoline so that they could spread it around, the world, lead oxide after the combustion process. They were doing it for reasons. They put in methyl T-butyl ether was a mandated solution. It's really wonderful. It improved the firing efficiency of the automobile. Wonderful concept. Slight problem. Gasoline storage tanks are primarily in the ground, especially in California. Anything that you put into the ground as a tank tends to leak. Anything that leaks goes into the groundwater. Methyl T-butyl ether happens to be particularly resistant to bioconsumption. Doesn't particularly biomagnify, by the way. It just doesn't tend to go away. So it ends up in the groundwater. So that's an example of a mandated solution that had an adverse consequence.
Can I ask a question and actually revisit a question that Lauren asked just a little earlier on the panel regarding kind of incentives, like how could there be potentially an incentive? And she asked you guys, and you said, well, ask the supply chain, ask the packaging folks, ask the paper printer next level after you. And I'm going to put someone on the spot here because Songren Packaging, I believe, the person from Songren left, but Jim Kilday from HP is here, and I just thought maybe you could speak to that a little bit before we left your topic. So unfortunately, I think we've learned that this mic isn't tied to the WebEx, so if someone's way back there, they can't hear you.
Do I stand here then, or?
Anywhere in this system.
Okay, I'll stay there.
Well, maybe I'll start by telling you something shocking, because the topic came up earlier. But so we have. So I'm from HP. So I'm the digital guy and the packaging guy too. I'll go through tomorrow. You probably know HP is document printing, home office printers, that kind of thing. We're also in the commercial space too. The Indigo, actually, it was mentioned a couple times today, is an HP division. But we also, one of the things we've done in the office and consumer space is we've got a program that's called Instant Ink. It's a subscription program for ink supplies. So all of our consumer and office printers now are hooked up to the internet. They've got an IP address and everything. They've got ink level sensing in the device. So this Instant Ink program will sense when your printer is running low, and it's a subscription program, so you automatically get ink in the mail when you're running low on ink. So you never run out of ink, and it saves money in the process. So the shocking part is you can say that you actually heard a guy from HP tell you how to save money on ink. So I thought I'd throw that in. The one thing, and I can't remember who asked the question, because all these topics are very germane, very familiar. Every topic has been very familiar. And this might show my age, but my team at HP manages the chemical compliance for all of our inks, and we have a team of toxicologists making sure all of our inks are safe for the environment, safe for consumers, showing my age. I feel like what we do is, do you remember the plate spinners? Remember the guys that would have the plates on all the? It seems like that's what we do. Because is it regulatory set of regulatory issues we're trying to manage? Yeah, absolutely. Is it availability issues that we're having troubles with and we're trying to find alternatives? Absolutely. Disruptions from China the past few years that have been really troubling to our business. We have materials that are reclassified out of the European community, the ECA community. It's incredibly difficult to develop alternatives. We manage inks in my team for all the inks that we've ever developed. So some of the inks have been on the market for 40 years. Okay, so it's not like you can take an ink that we developed 30 years ago and come up with some new replacement or new components. It's incredibly complex to find, I guess what I would, complex if not impossible for us to find, quote-unquote, drop-in replacements. Generally, we can, when we need to and we have to, when we're forced to do it, I talk about like photo initiators, some of these materials that are reclassified and whatnot, we have to find some creative solutions to work through those. And it's always challenging. With some of the materials, it's especially challenging to find alternatives. We use probably, we have about 300 or 400 different ink formulations, different ink recipes, and we probably have 500 ingredients. We ship to 145 countries around the world, so a lot of the job is to make sure all of our inks and toner, all of our inks and toner are safe for all of our customers, all of our employees, safe for the environment. So yeah, it feels like we do a lot of plate spinning because it's trying to balance all these things. We don't talks about our ink and whatnot. We don't buy the least expensive pigments. We use pigments and dyes, and we do know the difference. So I don't know. So just from a digital perspective, a lot of challenges, a lot of what was described here, that our challenges are different, but we have a lot of the same, sets of challenges, I guess.
Procurement standard, that's a little less than TSCA, right?
Yeah, it's a lot less than TSCA. Yeah, we're going to talk about that tomorrow too. But we set about a year ago, we said we have what we call the GSC General Specification for the Environment. So it's something that we expect all of our suppliers to meet, all of our suppliers for all of our materials. And for, I'm still getting inadvertent. We call them not intentionally added PCBs. We set the standard at 0.1 ppm. And we do that mostly because, and we'll talk about this a little bit tomorrow too, now that we're getting into the commercial printing space, commercial printing, which is still what we would call, it's digital, but it's 2D printing. We also are doing 3D printing, right? So we're actually making product. So we're getting more and more stringent requests from our customers to just get greater and greater purity in our products and also make sure we really understand what the contaminants are that are in there. And a lot of the brands that we work with, look for certification that we don't have any of this or any of that in our ingredients. So again, like one of the examples, we make one of our big customers on the 3D side is they're called Smiles Direct. They make retainers. So we need to make sure that we know what's in everything we make and sell. We make some of our inks. We sell some of we buy ink. We buy all of our raw materials. We make our print heads. And we'll talk about that a little bit tomorrow too.
But just to get to Lauren's question, which was, is there a way to incentivize, what are the incentives for trying to reduce those PCB levels in the pigment that would then be used downstream?
Well, I wanted to add something to what he just said there. Okay, he mentioned that he's got ink formulations that are 40 years old. Okay. Us guys that manufacture pigments or the guys that make inks or whatever, we have research guys, all right? The one thing we never let the research guys do is go to a customer and say, I have improved the product I'm selling you today. You can't possibly improve the product I'm buying from you today.
unless you told me that you'd narrow your range of variability within the specifications has gotten narrower. That's improvement. But if anything else that you did to that product, you changed it. That means his formula might not work anymore. So new products is different. You have the guys come in, you talk about the new product. But changing it is not something that people really want to hear.
Yeah, I've been with HP a little over 20 years. Before that, I used to work for Dow Chemical. And we took some contaminants out of our polyethylene resin years ago, thinking that was going to be a real big improvement for the customers. The customers really started complaining because this is generally like linear low and low density polyethylene, so it's usually like bread wrappers, and people couldn't get the packet open anymore because we took the contaminants out. The seals were so good they couldn't open the package anymore. But now, as far as incentives, I mean, the incentives for us is that we're really trying to grow, as I think was mentioned, we're trying to grow our presence especially in the packaging space, and some other spaces as well. But our incentive really is to meet our customer expectations. And, I mean, you can kind of go through the list of the brands and the end-use customers that we work with, and it's kind of a who's who of, all the big corporations around there. And especially you look at companies like Nestle and Unilever and M&M Mars and some of these other companies that are in the packaged goods business. And it's like Indigo does a lot of consumer packaging, and the companies there just can't tolerate contaminants. So they're constantly pressing us to take more and more out of our inks and really understand what we have in our inks and how can we reduce that and minimize that. So I think the real incentive for us is to grow our business and do that in a way that meets the customer expectations. But it sounds simple, but it's not. It's not that straightforward.
But so as you move back up the supply chain, then, what is the incentive for you folks to manufacture, some combination of pigments going to work for your packaging that's going to work for Indigo, for example, right? So I guess that's where I was trying to go with that, incentivizing as you go up the chain. Yeah. Last question, and then I'll do my second.
Yeah. Oh, okay.
Yeah, but I didn't.
I'm off the hook.
You're off the hook, but thank you for putting yourself on the hook.
Sure.
So I appreciate it.
Sure.
Sure.
Can you share any of your impressions around the transition towards digital printing? Like, I know it's a pretty vague question, but it sounds like you see that as an opportunity for HP. Do you see it moving into types of applications that wouldn't normally be digital?
Well, definitely. Well, and this is, I think, what some of our panelists were talking about too. So depending on the market, digital has had a very different, market acceptance or penetration or something. So like as an example for the signs, like exterior signs, I think it's essentially all digital today. Packaging, I think, is like 2% or something, or 3%. It's very small. Packaging is a huge market, and digital is a very small portion of it. So that's one reason why we're pursuing that one. I mean, honestly. But it seems like at the end of the day, if I think it's got to make good business sense, right? So and someone talked about the ability to synthesize new pigment. Well, that's step one. Is what one of the things my team does is make sure we're compliant on a regulatory basis around the world, and there's hundreds of thousands of dollars invested with every single chemical. So it's a big investment. So I think at the end of the day, there's got to be value in it, up and down the supply chain. If you've got a material that you're selling that offers advantages to the customer is willing to pay more, and they can in turn get higher prices or improve market share for their products. In the end, I think at the end of the day, it's got to be good for all involved in the supply chain.
Would it be safe to say a good incentive would be to reduce the regulatory barriers for approval?
No. Yeah, that would. No. That would be.
I mean, if
absolutely
you're asking for incentives, right? To me, if you want to encourage new products to get on the market and they don't have the attributes that we're discussing here today, you've got to reduce the barriers to regulatory approval for products coming to market. And to me, that would be a huge incentive. In other words, flip it around and say, how can we make it easier for you to bring these products to market and obviously ensure that they're safe, right? That's the key challenge. Is you don't want to put an inadvertent issue where you create a bigger problem by trying to solve one.
Yeah, and like one of the problems we've been wrestling with the past couple of years, probably 15 years. So we make a lot of water-based inks and we use biocides, right? So a lot of pressures on biocides. We've looked at probably 50 or 60 biocides over the years for our inks, and we've got, I think, a handful that'll work, let's say. But increasing regulatory pressure all around the world for biocides. So it's kind of, you get into these trade-offs of, we think the water-based chemistry inherently is, at least customers will perceive this as maybe a safer chemistry or safer alternative, but then you've got the things like biocides that go into our ink that we've got to manage as well. So there's constantly all these trade-offs. So that's why I kind of think about the spinning plate.
Yeah, I was just wondering, so what's the practicality of going to a company like Starbucks and asking them to make their logo a little less brilliant? I mean, what you guys are saying that, yeah, we could probably change the industry, but we'd have to get everybody to agree to do it at the same time, because if you're making printers and ink and you decide you just limit the palette and you reduce the amount of brilliant colors that you can get out of your printer, but your competitors are not doing that same thing, then you're going to lose market share. There's no doubt about that.
Well, the answer to Starbucks is they couldn't show you the door fast enough. You know what I mean? So, that's just half jokingly. I don't know whether they'd be receptive or not, but you're asking for a monumental change.
Yeah. Just to get everybody off the hook that's here, because we're all primarily talking about printing all day. But in 1985, I changed plant locations, basically doing the same job, just happened to be different, went from South Carolina to New Jersey. The first things that the sales and marketing guys that were up there told me was that within 5 years, the majority of high-performance paint sold in the United States for automobiles is going to be waterborne. Well, you can go to any of the major paint companies today, and they will tell you that within 5 years, the majority of automotive paint will be waterborne. This is not dissimilar from the conversation that took place with Standard Oil in New Jersey about economic conversion of coal into gasoline. If the price of oil would just double from 1920, prices, just double in 1920, when it was like, $50 a barrel, 50 cents a barrel or something, some ridiculously small number, that it would become economical. Well, it's gone up considerably in price. And if it would just double, doing it from coal would be economical. So the target doesn't seem to ever get any closer.
Yeah.
But
we also have a request that if the speakers and guys aren't using like all of that, you just speak up, just not go on with it.
Okay.
But one thing I was going to mention that back to your question is that at some point, maybe the conversation starts shifting a little bit. So, like as an example, we've started using we made a commitment to use a lot more recycled resin in our products. And I think today we use like 7% or something. We're going to jump it up to 30%, but it's across all of our personal computers and printers and whatnot. But we're starting to have a conversation with the marketing folks on, hey, do you really need that white printer? Because that's really, really hard to use recycled resin with So we're starting to change the conversation about product development, what's important, what's the impact from a sustainability perspective, right? So I think at least some of those conversations are starting, but it's
So a couple things. One, I actually work quite a bit with Amazon, and I think they would be more amenable than you think in terms of, because they're so recognizable right now, they could just do an outline of their logo and people would know what it was. They don't have to have all that deep green on there. Couple of questions. One is, what is the most expensive pigment? Is it yellow or is it something else?
The most persistent?
Expensive.
Oh, expensive.
Costly.
Most expensive. None of the ones we've talked about today.
Okay, but of the ones we've talked about today, like
the blue and the yellow, it's sort of 6 of one, half dozen the other.
They're both the most expensive?
Oh, domestic, I mean, they're all in the same ballpark.
Oh, they're all
Maybe the blue's a little bit more expensive. I'm trying to do the maths. They're all in the same area.
Okay.
Yeah.
I mean, I was wondering, because I was just thinking that, people would, are they paying a lot more for another color that's a premium color?
No.
You need the microphone.
That's the microphone.
Microphone, hold on.
Sorry?
The amount that's used of the yellow?
So the cost per pound are roughly about the same, but diarylite is so much stronger that you use less, so the cost in use is less.
Ah, okay, so they are saving money right now by using the yellow, that yellow.
Yes.
That type of yellow.
Yes.
Now that's my question. Okay, so since we want to promote recycling, and because the most of the paper you're going to be getting into the recycling, with the exception of those high-end catalogs, is stuff that actually doesn't need to have a permanent color that's going to be so great forever. Is there something to be done with just looking more at, say, the pigments used for paper, since that's the recycling thing, versus the pigments being used for plastics?
No, I mean, the diarylite are used across the board in regular printing inks. So, and it's because they have the performance in all printing ink systems.
I'm thinking we have a lesser quality.
Well, I mean, even in packaging ink, they don't last forever. It's the same pigments. You're not talking about durability in printing for the most part. Digital gets a bit more complex. But across flexible packaging, newsprint, magazines, so you use diarylite. These are not what I would call as a chemist permanent. You stick them outside, they're gone within I'll call it a month, 2 months, 3 months. So it's just faded. So you're not talking permanent. Is there a way to use a lower cost pigment or a lower... You're talking major compromising in terms of performance. I'm just not sure you would get there.
I believe we have a web question. Is that correct?
Yes, we have one other comment regarding that current question, I believe. Thank you, Jim.
So in this case, it's economics, right? There have already been a number of examples that this industry has been beat up for the last 30 years. And if the pigment manufacturer and the ink manufacturer could find something cheaper that performed, it'd be done. Because there's just no money there. And they've been looking for and been very effective in that already. So the innovation there's not a possibility for innovation because the money's not there. If the university were to pick something up, maybe they could innovate. But there's no money for R&D. When you're making 2 to 3%, they're just trying to keep the doors open. And actually, the printing, not the printing, but the manufacturing, but also the ink manufacturers, that market has shrunk in America. It's gone overseas, a lot of it. But it's shrunk in America. And the ones that are existing today, they're just basically trying to survive.
Okay, so we do have a question from the webinar.
Which printing processes are most compatible with the low/no ICB pigments? Or in other words, which processes would make for the best starting point in trying out these alternative pigments that already exist?
I don't think there's any significant difference between flexo offset in terms of compatibility with, it's all about the color, really. When the printing industry, and I mean, Jim Kildare mentioned a couple of times about safety and ink, or the conception really when an ink company or printer thinks about safety is it a danger to my employees? Is it a danger, is having an adverse environmental impact to my employees making the ink, to my customers using the ink, and then to the end user? Is it a hazard to them? And that's their conception of safety and environmental impact. Now, you're taking it one step further when you say, well, how about when you get rid of your product, is there an environmental impact there that you need to be? And that's a whole new kind of mindset for them to really start to think about. And then, you know, when you start talking to them about, well, changing your color process because of a recycling issue where you could conceivably have, you know, a couple of parts per quadrillion of a non-intentionally added substance in your product, it becomes a difficult conversation. I mean, I've got to be completely honest. It's a very difficult conversation. I mean, right now, the biggest concern that all these people have is food packaging safety. I mean, that's where all the emphasis is today. And I talked to you a little bit about what FDA's perspective is in terms of human health impact from migration of ink components into the food product. And you know, that's kind of the mindset today. So, I mean, you'd have to kind of raise this with all the way through the supply chain, from the brands all the way back to the raw material suppliers, to get some type of, you know, incentive there to change what they're doing today. And I've got to be honest, I think it's going to be very challenging to get them to pay attention to this issue, especially if they're not hearing it from anywhere else. I mean, this is an issue here, of course, and I'm sensitive to that. But, you know, I meant to ask Doug, are there any other of your competitors that have similar types of concerns or issues from a recycling perspective?
Well, I mentioned the one plant that was north of us here that actually went out of the recycling business.
Right.
I didn't say it was solely due to this issue. This issue was definitely on their radar.
Right.
And there are other pulp and paper mills in Washington State that are watching very closely what is happening here. Right. So coming to a venue near you, basically, right, in this state. I can't speak beyond that. Okay. Oregon has a similar water quality standard as Washington does. And there are mills in Oregon also. And this PCB concern is becoming more and more highlighted because of the Orca issues, a lot of Puget Sound contamination problems. So I did a presentation for Nicazi a couple weeks ago called Life at the Tip of the Spear, which, for whatever reason, I don't know why, perhaps the colleagues you can explain to us why, you know, Spokane is a microcosm of these, the launch of these very significant regulations, but we are, whatever the reason may be, we are there. And so I think we're just the predecessors of what's coming soon. You're going to be hearing more about it.
Right, okay.
Okay, at this point, we definitely want to wrap up. Does anyone have a final burning question before we?
I have
okay.
one. So, of course, I just want to kind of explore this regulatory rabbit hole a little bit further with you, just to kind of get my mind for thinking about our workshop tomorrow, what opportunities might lie there. I talked about, you know, not one solution is going to solve this, you know, silver bullet issue. But, however, you know, you talked a lot about quality control measures, temperature control, being able to get PCBs down from 1,000 ppm down to whatever the number may be. I know a lot of the industry has shifted outside of this country for labor cost reasons, more than likely, but is there a market opportunity for your industries to consider in saying, hey, you know, HP, Apple, they've developed lower requirement specifications for PCBs in their products. Is there an advantage to your industry to say, hey, you know, we can do this better than anybody else in the world from a quality control standpoint? I don't know what the number is, 25, 1.1 I think is theirs. Would that potentially be a market advantage, that we can produce these products here in the U.S. with a lower PCB concentration, to perhaps bring more of that business back to you, regardless of the labor cost savings that are enjoyed elsewhere in the world?
Sadly, the short answer is right now, no, there's no market drive. Could we even reduce? Not based on the Dow, as I see, not so much. With a bit more R&D dollars, could it get there? I don't know. Right now, there's no market drive. And that would be where it would have to come from, just to even think about looking anymore. Because, you know, we're doing research on various pigments. The PCB is not the issue. It's more generally more about transparency, opacity, depending on the actual color application. casing regulatory. There's no market drive right now. So, sadly, we maybe want to do it, maybe, but there would have to be a push. Steve?
But is the R&D?
Sorry?
Is the R&D equal, or is it plastics or some other?
In ink world. Oh, we haven't been for a long, long time. It's all optimized. The question was, would there be a market opportunity should you come out with a low PCB? Or lower, not seen it so far.
Well, thank you very much. Is there anything that any of you would like to add before we wrap up? Thank you so much. Give us back those pictures. Well, thank you for coming. We'll be getting rolling again tomorrow morning at 8:30. So we will see you then. Hopefully you know how to get in the building now, so it won't be as problematic. And if you haven't filled out this breakout group chart, please do.
Folks on the WebEx, we'll see you tomorrow. Thank you.